Welcome to Cloud Applications 2. This is our second course, and we're really excited about bringing all this new material to you. We have organized it, so we're going to cover quite a lot of the new activities in clouds being applied to data systems. I'm Roy Campbell.
I'm Reza Farivar.
And we've worked hard at trying to get this together. So where do I come from? I've been a professor here for 40 years. I've been teaching systems, and all of a sudden the whole systems world really got very exciting when cloud computing came along, cluster computing came along, and all of a sudden there are just simply sort of lots of innovations and inventions going on, and the whole big data area is exploding. Applications are increasing, jobs are increasing. This is a great time to be in computer science.
Oh, absolutely. Oh, absolutely. Well, I'm hoping to bring some industry expertise into the class. I'm a manager of data engineering pipelines at the Capital One company. I'm also adjunct faculty at the university, and together with Professor Campbell, hoping to bring you lots of interesting information in this segment of the market, which is, oh my God, exploding. It's just so much interest in big data and clouds these days.
We've got a number of different modules for you. We'll take you briefly through those modules right now, and then each module will introduce the particular topic and get you into depth on each of those aspects. The first topic is really sort of, well, what about clouds now? What's happening, the big data world and so on? We're going to do it by example. What we're going to do is to choose Spark because it's so pervasive, and because pretty much if you want to get started, Spark is a great way to start. You can do it on your laptop, but then you can move those same elements onto cloud computing, and you don't have to change too much to actually make it all happen. So we'll go through that motivation for Spark. Actually, Reza, why don't you tell them what you're going to tell them?
Oh yeah, absolutely. So before talking about the details, I want to mention that Spark has seen tremendous amount of support in the open source community in the past couple of years. And previous versions of this course, when we started teaching this course at the university, Spark wasn't there. The whole course was based around Hadoop and that sort of world. And of course, we still kind of mention Hadoop and talk about Hadoop, but Spark has been so great and tremendous in the community that we've reworked the course, and a lot of the examples, hands-on work on the course now, we are doing it in Spark. So we talk about, in the first module, we start by talking about Spark. We provide some examples on how you...
Well, you're going to do some mining.
Yeah, we definitely do some log mining. We do some
logistics.
Logistic regression.
Some fault tolerance with the hard... Well, one of the things is as you write this, a lot of the software that you would have to put in the system is already there. So we have these reliable data sets, RDDs, that provide you fault tolerance when you write to them. And then we're going to talk about whether you can, how you interact with it. And what you find is that both interactive systems and batch types of systems, you're going to mention that. And then because we're an academics, I guess, well, fairly academic at heart, we'll lift the covers a bit and just talk about what's underneath Spark that makes it all work.
Yeah, we definitely want in this course to kind of give you a knowledge on how to use a lot of these systems and write applications and, from a hands-on point of view. But we also want to give you an overview of how these distributed systems work, what sort of algorithms are underneath. So we definitely will go a little bit into Spark's implementation in this course and other systems that we'll talk about in a couple of minutes. So
once we've done that sort of motivation and introduction, I'm going to sort of introduce you to platforms that are around. They come in distributions, distros as they're called. And there's three that I really want you to get familiar with. One is Hortonworks. Hortonworks was one of the sort of founding Apache members when Apache moved to look at cloud computing. Hortonworks has two great suites, one for streaming data and one for actually just building MapReduce and databases, big table type of operations. So we'll talk about Hortonworks. Then I'm going to talk about Cloudera, which is often what people actually get their hands on when they sort of go to a commercial, or in a university, if you take a course, you might well end up using Cloudera. And that is a package that you can use pretty much all the things that you will find in Hortonworks, but they'll just be organized and presented in a different way. And then we'll talk about MapR Distro. Again, pretty much repeating it, but in a different sort of distribution framework with different emphases slightly. So I'll overlay those, and you can sort of pick them up, put them on your laptops, play with them. But those systems are really the basis for what you see out there on the cloud systems running. And then, of course, we've already introduced Spark. So you, by then, have a good feeling for what sort of systems you're going to meet.
Exactly. So just to put a wrap on the distros, it's for you old-timers, it's kind of like Linux, how it used to be like 20 years ago, when you could actually download source codes from like different parts and build this driver or build that driver and build the kernel. And you still can do that, the same mentality as here. You can download Hadoop and install it on your cluster, and then you can download Storm and install it on your cluster. Or, like Linux, you can just have them all packaged together. You install Hortonworks Sandbox, everything comes with it. You know, Storm, Hadoop, Spark, whatever.
It just makes life too easy, right?
Exactly.
Okay, then what we're going to do, we talked about RDD earlier on, but we're going to sort of emphasize a little bit more how you get reliability and how you get really massive data sets. We're going to talk about HDFS and that file system for Hadoop and for a lot of other different types of big data operations. HDFS is kind of unique. It's early days that it happened. It's kind of like file systems you already know, but boy, can you move data with HDFS.
Oh my God, it can store massive amounts of data, and it's really a building block for a whole bunch of these systems that we talk about. All of them can support HDFS. You put files in HDFS, you like petabytes, multiple petabytes of information. It can easily handle them. And it all goes down to how they architected the system, right? It's all about how they designed the system.
So if there's somebody you want to impress, then HDFS is there. Right. Then we're going to move on to talking about infrastructures for doing some distributed computations like Hadoop and like sort of some of the other systems that we're going to discuss, Storm and so on. They're all based now on a framework. It's kind of moved along from our first course. It's all of those implementations are now being put on top of this very, very smart sort of infrastructure called Yarn. And it's got scheduling, it's called MESOS, that will organize all of this. Basically, what it's looking at is all the interconnectivity of the parts as a sort of graph, data dependencies, whatever. And then it builds schedulers on top of it to actually make all the parts work together. And that part of it is just, well, you'll find it in the really big 10,000 node systems.
Exactly. I mean, when you go to industry applications and you look at real clusters with 20,000, 40,000 nodes, that's where you really need something like Yarn or MESOS to handle resources. And these days, a lot of the frameworks that sit on top of Yarn or MESOS handle everything else. I mean, you have, MapReduce on Yarn, Storm can use Yarn, Spark can use Yarn, but Yarn is a kind of like the operating system that sits down there.
So now you'll get the idea of exactly how we're going to present these modules. As we go forward, we're going to be doing the same thing. We're going to move on now to sort of looking at MapReduce. And we start off with a Spark implementation and describe how it works, what the motive for it is. We're going to describe the programming model and then some examples. Reza, you're going to handle that one. Are you going to?
Yes, absolutely. So MapReduce is really a foundational way of thinking about distributed algorithms, right? So before MapReduce came along, and it was about 10 years ago or so, more or less, before MapReduce came along, people would write MPI programs for distributed systems, and it was messy and it was hard to write. And MapReduce came, the whole idea of MapReduce came along and changed things. And we'll talk about how you can think in terms of MapReduce. We'll provide some examples, and then we'll show you how to write a MapReduce example in Spark interactively, and you'll see how easy it is to write a program that does, lots of work in Spark and MapReduce.
So as you will have realized, it's not just about the algorithms, it's also about the data structures. So we're going to then, in Module 3, launch into just what are the data structures that you have to manipulate big data, and what's the support you have to do this. And I'm going to introduce large-scale data storage and talk about the problems you get when you take data and you spread it across 10,000 nodes. That provides a whole problem about how do you, if you change anything, how do you get it all consistent? How do you actually look at all that data in a consistent way, even if there's going to be nodes that are failing, even if you're updating some of the data in the system, how do you look at it consistently? So we'll look at eventual consistency. We'll look at sort of trade-offs with different types of approaches. We'll talk about acid, base, Zookeeper, Paxos, their techniques for keeping things consistent, and that will lead up to then a sort of good background to tackle the next chapter.
Oh yeah, and that stuff is actually very interesting, very exciting, to be honest. When you want to scale into large distributed systems, you can just think, okay, I'll just copy paste my machines. I'll have, instead of 1 machine, I'll have 10 machines. But that whole idea introduces so many different challenges. And Professor Campbell is going to cover a lot of those.
That reminds me of a good example. When you take an algorithm, like one of the Grass algorithms we'll be talking about later on, and you want to scale it from 100 nodes to 1,000 nodes, how exactly do you do this and keep the computation running?
Yes. Proving that something, the liveness of an algorithm, when you have 1,000 machines, it's guaranteed that at each time, 1 or 2 or 3 or couple are in failed situation, right? And how can you make sure that your algorithm can actually even move forward? So that's a lot of interesting stuff, and Professor Campbell is going to cover them.
Then we'll get into details about how you program it, and we're going to give, like all the other chapters, we're going to start off with, how do we use Spark to actually do things? So we'll describe why not sort of use a database, why not use SQL. Then we'll describe, a database that is actually scalable, HBase, and then we'll use Spark to write some SQL to play with those sort of databases and get a feeling for what's happening. Now, there's some really trendy things happening in databases.
Oh yeah, that space is also seeing a lot of attention. We have picked up a couple of very popular ones. We will talk about HBase. We will talk about Spark, which has now the SQL engine. And we'll also talk about some in-memory key value stores.
Tell me about Redis, Reza.
Right, so Redis here is actually an interesting system that solves a very interesting challenge. It has a niche, and it does very well in that. So databases, distributed databases, we talked about them, and we will talk about, of course, in detail all the issues with like cap theorem and consistency and everything. Redis solves an interesting problem, how you can store key values in memory across a distributed cluster, and how can we make sure that it's extremely fast and very usable.
Oh, you keep it in memory, right?
And you can keep it in memory, but of course it's not that easy, and there's a system Redis that handles that, and we'll talk about it. It's a very interesting building block. It's used in batch systems and databases, as we talk in this module. It's also very extensively used in streaming in the next module that we talk about. But before we talk about streaming, let's talk about Kafka.
Kafka now, so everybody wants to write systems that pass messages backwards and forwards. You're picking up all the mouse clicks all over the world. You need to put them into your databases. You need to count them. You need to sort of tell your advertisers. You need to build statistics and all sorts of other things. How are you going to do this? So Kafka really underlies how you do this. what it would do is sort of like a big messaging system built on publish-subscribe systems. There's publishers, like the mouse click guys, that sort of feed you all sorts of counts. Especially, I was just thinking about the Olympics. How many mouse clicks were there in the Olympics? Just incredible numbers. Exactly. Coming in, being processed, the advertisers get money, and that's a stream that's processed off them. The company providing the video streams gets its revenue. That's another set of streams. So this is all organized. They would be consumers of this data that Kafka was absorbing. So Kafka will be taking the mouse clicks as production, processing them, and then producing counts and so on as streams to the consumers. In this case, the people actually putting the show on or charging the advertising. So we'll be talking about that. But it leads, Kafka itself leads to this notion of how do you actually build streaming systems? One of the things that's interesting about Kafka is it handles the redundancy. If you've got streams coming in and you want to have redundant copies of that stream, Kafka will take control of that and do that for you without you having to worry about how that operates. And the other aspect of that is if you get failures, it's going to account for that. So it actually uses a log file system, which is really cool to keep the messages in.
Oh, yeah.
So, yeah, we're going to have some excitement.
I really like Kafka. I mean, I think of Kafka like a duct tape of big data. Whenever actually you really need to connect one thing to another thing, and we have a video on that later on in the course, you want to connect things and you will need to something in between these two. You always use Kafka. It's kind of like a duct tape. It's great. It works. It's reliable. And it's fast. I mean, it can handle hundreds and thousands of events per second in like a couple machines. So that actually now gets us into streaming. Right, so streaming is important.
I've got a lot of PhD students, and they're all off over the summer working with streaming companies.
Right.
So you've got, for example, all of the LinkedIn data flowing. And everybody's sort of looking for jobs, adding their profiles, adding pictures, adding all sorts of facts about their jobs. How does that all get distributed? Well, it's all through streaming systems, and they're just fabulous. Wait, I wonder how many of the audience actually use Facebook. There's another sort of big streaming application. So we don't really need to motivate it, but it's just, if we look back 10 years, well, streaming would be, a whole hum. But now,
everywhere. Back in so up until maybe 2012, if you stretch it 2013, everything in the world was batch. Companies were happy with batch. Consumers were happy with batch. Nowadays, we're in 2016, 2017. Everybody wants millisecond level responses. You wanna apply, a search for I want to find a car. I really want to see the inventory of all the car dealers right now, right? If there's a car added to a car dealer's inventory, the dealer wants to be able to show me that car right now compared to tomorrow, right?
So what better name for a streaming system than Storm? Just because of the way all of their streaming is taking everything by storm, effectively. Yes. So we're going to discuss some of that. We'll give you some examples of using Storm, doing word count, simple stuff, and then we'll go on from there. We're going to look at how Storm gets used in some companies as well. So we're hoping to plug into how Yahoo uses Storm to look at incoming mouse clicks.
Right. So we take Storm as one of the common streaming processing engines these days, and we kind of go into details of how you can write a program for it and how the engine itself, how the platform itself runs as a distributed system. So we kind of try to cover Storm in detail, and then we kind of move on to some of the other alternatives to Storm, right? So again, we did a couple times before. Now we go back to Spark. Spark is great. Spark is covering everything these days.
Yes. So sort of anchoring and building spouts and all those good things. We'll discuss all that and how you actually build sort of exactly once processing with Trident. That's going to be a sort of interesting aspect to that whole thing. We're going to look then inside some of these systems, so we've got inside Apache Storm, open the covers and look down there. We're going to look at how you build Storm clusters, what they look like. Do you want to talk about Thrift a bit?
Yeah, but I will definitely show how Thrift works in Storm. Thrift is actually kind of a foundational software package, not only used in Storm, but also in a lot of these other streaming systems. Not streaming, big data. You're using, pretty much anything that is network related and it's distributed system. These days, it might actually be using Thrift. So we will talk about Thrift and how you can use Thrift, and then after that, we'll kind of move to how schedulers work in Storm.
So tell us about Spout, the ecosystem that surrounds it. Right.
Right. So of course, after Storm, I kind of like talk about Spark streaming and how Spark streaming can also be an alternative to Storm. After that, I have an interesting talk about ecosystem, right? So you have we introduced a whole bunch of different tools. We introduced Kafka, we introduced Storm and Spark streaming, and there's a whole bunch of other things. It might be confusing these days. I mean, you might think, okay, should I use Storm? Should I use Spark? Should I use Kafka? Should I use, and there's some other things that we don't talk about, at least in this course, much, but at least I'll mention them. Should I use NiFi? You might have heard NiFi. Should I use NiFi? Should I use Druid? Right? So where do you need to use which of these platforms? So we have an interesting talk that tells you the strengths of each of these platforms and the weaknesses.
And how to plug them together.
And how to plug them together. How to use duct tape.
Right. That's great. So we're going to move on from there to another great topic that's emerging. This topic really sort of was just on your desktop for a long while, and it was just very sort of, I won't say academic, but it didn't really grab everyone. But nowadays, with social networking, with the complexities of some of the systems, it's just become enormous, and that's graph processing. So we're going to go through early days in graph processing, looking at Pregel and what Google had introduced to do that. We're going to move on to looking at Giraph, which is the Apache release, and the beauty about that particular system is then I can talk to you about how it works. So then we will go on to Spark again, Spark GraphX, where you can actually play around with graph processing.
Yes, so I'll introduce Spark GraphX again. It tries to reuse the whole RDD model to process graphs. It's kind of like a slightly different model than Pregel and Giraph, but both of them are kind of gaining popularity, so we decided to talk about both of them. And then we move on to machine learning.
Yeah, that's a really cool topic,
all right,
especially when you've got lots of data. Yeah. So we're going to look at some of those packages that allow you to handle big data. Mahout is one of those, comes out of the Apache Foundation, and you can get to play with it. It's a particular install all by itself, but that doesn't really stop anyone from using it. Now, if you really want to use it in sort of programming with lots of other bits and pieces, then what I would suggest is back to Spark. Back to Spark.
And Spark has been seeing a lot of activity in the ML machine learning part of Spark. So we'll talk about Spark ML itself, and then we have an example on how to use Spark K-means, for instance. And then probably some other examples that you'll see in the course.
Well, you're going to cover naive Bayes and a little bit of FPM, right? Just to show you how universal it is. After all that, we're going to sort of wrap it up with looking at deep learning, because I think probably no course on big data is, or at least cloud applications, is actually sort of complete without a little touch of big data.
So the deep learning stuff is actually quite interesting, right? So it's been it's really exploded in the last 2 years. I mean, the whole idea was there for 20 years, right? We're talking about artificial neural networks. But you might actually think about, why are we talking about deep artificial neural network in big data? But this is actually the reason big data is really the reason that neural networks are now working compared to a couple decades ago that they were not.
The beauty about the deep learning is that you can actually draw parallels between all sorts of different things. You can look at, is this particular event sort of got any relationship to this other types of event over here? you can really do a lot of comparisons. Now, you do need to do oftentimes learning in order to be able to do this. Sometimes you can do it without that. It just depends. We'll discuss some of that topic. The nice thing is that the packages now allow you to do this very easily. And some of the packages we're going to be talking about, like TensorFlow and so on, can run on your laptop or they can run on really powerful machines.
Right.
And they allow you to do all sorts of things, like sort of images. If you want to recognize, I was looking at that. If you take photographs of yourself, stick them up on Facebook, and then it knows who you are. And it knows who you've taken a picture of. And that's all the deep learning packages.
That's all the deep learning stuff.
So
yes.
we'll be covering that.
And it's using, on the back end, it uses large clusters of GPU-enabled machines that churn through massive amounts of data to do the learning. So
I think we've been talking low enough. What they should do is to start the course.
Oh yeah.
So good luck with the course.
We are excited.
We'll see you as you get into the introduction.
Oh yes. In this lesson, we are going to cover Apache Spark. Before talking about Spark, though, I would like to talk about the motivation behind Spark and the sort of computations that it tries to cover. And it's not the only framework that does this sort of thing. I'll mention a bunch of others, but Spark is the big one these days. The reason, the goal of Spark is to cover iterative algorithms or interactive data explorations. These are things that are commonly used in a lot of domains, data sciences, IT today, scientific computing does a lot of data exploration. Iterative algorithms you can find in many, many domains. And we want to be able to cover these set of algorithms. Now, traditional MapReduce, and by traditional I mean things that we talked about in our second week of lectures, Hadoop, MapReduce, those sort of stuff. Those sort of frameworks, they cannot quite efficiently solve iterative algorithms. Now, the question is why? Consider something like Hadoop. If you want to write an iterative algorithm, what do I mean by iterative? Same algorithm ran once, and then on the same data set or almost the same data set again and again and again until you reach an answer. If you write this on top of Hadoop, what you will end up doing is repeated access to data that is stored on HDFS. That means repeated access in each iteration to hard drives, to physical, slow, high latency devices. And Hadoop doesn't provide any optimization for caching the data. It says, this is one MapReduce job, starts from HDFS, ends in HDFS. Doesn't support any sort of data caching in between different iterations. I'll talk about this a little bit more in my upcoming slide. Now let's say you take just bare bones MPI. There is no natural support for fault tolerance in a program written in MPI, so the programming interface is quite complicated. The programmer, meaning you, have to consider all of the implications of writing the application, whether it's reliability, whether it's fault tolerance, all sorts of crazy things that the programmer has to consider. So none of these traditional frameworks handle this class of algorithms in a good way. So if you try to go ahead and basically retrofit iterations on top of MapReduce, well, out of the box, it doesn't support iterations. But well, we still want iterative algorithms. What was one iterative algorithm that was quite famous we covered in one of our lectures before? PageRank, right? PageRank, you remember there was two different MapReduce jobs. There was the propagation phase, and then there was the aggregation phase. And you would run the first job, second job, again first job, second job, first job, second job. You would keep doing that. And that was actually the first use case for Hadoop, for MapReduce itself, right? Remember, Hadoop actually came out of the Notch project, which was doing the PageRank algorithm. So iterative algorithms have been retrofitted on top of MapReduce frameworks. So as I mentioned, Notch, the indexing and search engine, Apache Notch, or Apache Mahout, does a lot of iterative computations. Now, the obvious solution, if you want to implement this on top of MapReduce, is to split iterations into multiple MapReduce jobs, write a driver program for orchestration, one job, another job, another job. Each job is the same thing, really, just with a slightly modified input data set. Why slightly modified? Because the last iteration slightly modified it, got it closer a little bit to the answer. So let's take a look at what would be involved in running a iterative algorithm on top of MapReduce. So the sort of algorithm that you're talking about, you can see here, we have inside a basic loop, we iterate. Inside each iteration, we do, say, a map job, a map phase, and a reduce phase, together becoming a MapReduce job. In the map, basically what you do is you run a certain computation for all input data elements, and then in reduce, you do a reduction. And you basically repeat this until convergence is achieved. So job 1, job 2, job 3, all the same. And basically what happens is that in each iteration, you use the data set inside your mapper functions and come up with a slightly modified answer, hopefully a little bit closer to the final answer. And then you write back the answer and repeat. And there are many problems in this model. You have repeated reads of constant data, basically data that doesn't change in each iteration. Typically, it's the larger of the two data types. So you have constant data type, and you have small amount of data that changes from every iteration to another iteration. Each time, you have to read the constant data set again and again. For each iteration, you have one MapReduce job. So there is overhead in launching every MapReduce job. If you've, in our previous weeks, when you were running the programming assignments, if you were adventurous and just tried to see what happens if you have an empty map job and an empty reduce job, you would have seen that even with no computation, when you launch a MapReduce job in Hadoop, it takes 15, 20 seconds to do nothing, basically. So when you have iterative set of MapReduce jobs, in each iteration, you have just a 20 seconds of nothingness happening. Well, of course, there are lots of things happening for the framework, but for the user's computation, nothing happens. So aside from that, when you have MapReduce, there's a lot of intermediate communication. Remember, there is a shuffle and sort phase. And there's a lot of communication that puts a lot of traffic on the network subsystem of a cluster. And each time around, you do almost the same thing again and again. So now that we have seen all of the issues in implementing an iterative computation, or interactive computation for that matter, on top of MapReduce, or a framework like MapReduce, Hadoop, Yarn, let's see what we have for solving these issues. In the next video, I will introduce the Apache Spark project that allows you to do lots of cool things with interactive and iterative algorithms. Let's introduce Apache Spark here. What we are trying to achieve in Apache Spark is to extend the MapReduce model to better support iterative algorithms like, for example, machine learning, graph processing, database access, SQL access, or just general custom algorithms that deal with a lot of data. You want to be able to support interactive data mining. And what do I mean by interactive data mining? I mean sort of an interactive console for the user, so that instead of writing a program and compiling it and hope for the best, and if it doesn't work, again, modify the program, compile it, run it again. Instead, you have an interactive console say, hey, load this data set, done. OK, now what should I do? Let's filter it. Filter. Oh, that's not quite what I wanted. Let's filter it with another set of parameters. And you can do this interactively. What you want to try to do is, in Apache Spark, try to enhance the programmability. So you want to be able to use a nice programming language to be able to play with the data. And in Spark, the system is written on top of Scala. Scala is a nice language written on top of Java, kind of like Clojure was written on top of Java. Scala is also written on top of Java, so it allows interoperability with Java. And it has a nice interpreter, a REPL, that you can interact with. So we want to be able to do iterative and interactive algorithms better and has programmability. But the question is how? To answer that question, we need to figure out why the current frameworks aren't working as good as we really want to. The issue is that many of the current cluster programming frameworks, Yarn, others, they are based on this idea of acyclic data flow. So the idea is that you have data that flows from one stage of computation to another, from the second stage to the third stage. And it's acyclic, so you do not have loopbacks on your data flow, which helps the design of some of these frameworks. So data basically flows from one stable storage to another stable storage. Data starts its life on HDFS. We do a little bit of computation on it, ends up in HDFS. Well, this model has some benefits, of course. The runtime engine, the scheduling algorithms, they can decide where to run tasks based on the data locality, therefore trying to optimize the runtime. It can also provide nicer failure recovery semantics because it's easy. I mean, we know where each task started from. We know where each task is supposed to end. If there's a failure, we can restart. But the acyclic data flow paradigm is not quite efficient for applications that use the same set of data, the same working set of data. Iterative algorithms reuse a lot of the data. So you can think of an iterative algorithm. What happens is that you have this huge data set. You look at it, you have a huge input data set and also something called an answer, right? And then in each iteration, you consider this big data set, you consider your answer from last time around, you do a little bit of computation, tweak the answer a little bit, push it back. So for the next time around, your constant input data set still remains the same. Your answer has changed a little bit. So you can see that a huge part of the data doesn't change from iteration to iteration. Another example is, again, interactive data mining, right? A lot of times, you load up some data, you do some search on it. OK, I did a search. Then I want to do another search with a different set of parameters. My data hasn't changed. The input data is still the same. Why do I need to read it again from hard drive, the very slow hard drives? So see, as you can see, acyclic data flow paradigm could be very good for its own use cases. But here, for some of these use cases, it becomes inefficient. Now, the solution that Spark provides is a data abstraction, data and computation abstraction called resilient distributed data set. What do I mean by that? Resilient. This means that once you load it into memory, it remains into memory until you say, OK, I want to get rid of this. It's a data set, obviously, so it contains data. It's also distributed. So when you have a cluster, you, as the programmer, can think of a data set, an RDD, as one logical thing. In reality, pieces of this RDD are spread all around the cluster. OK? So in your algorithm, you say RDD1, load from disk. RDD2 is RDD1 filtered by this parameter. RDD3 is RDD2 sorted. RDD4 is RDD3 something else. All of these RDDs are distributed across the cluster, and the framework manages them. OK, so we introduce RDDs. But we want to retain the attractive properties of MapReduce. We want to have all the nice things that you have in a cluster programming framework. We want to have fault tolerance, scalability, be able to use locality as much as possible. And these are things that are considered in the design of Apache Spark. By using all of these features, Spark allows you to do a wide range of applications. So it can do regular MapReduce, although Yarn still has its place when you are dealing with huge amounts of data that don't necessarily fit within the total amount of RAM that you have in the cluster. Hadoop is still the king. If you have a pure data flow algorithm, you have log processing. You just have a huge amount of logs. You want to process them. Fine. You don't want to iterate. Hadoop is the king. But you can also do those in Spark. If your data set is slightly smaller and you can load them within the memory of your cluster, Spark becomes actually much faster. You can do machine learning. You can do database access. Remember that we talked about Apache Hive in previously, and Apache HBase. Well, in Spark, you can load data from Hive and HBase, and then you can do interactive search on the data. You can do graph processing. You can do other nice things. So we'll get to some of those. Getting back to the programming model idea, the RDDs, the resilient distributed data sets that were introduced, they have a couple of interesting properties. One, they are immutable, right? That means that once in your program you define one RDD and say RDD1 equals something, fine. You cannot change RDD1 again. You cannot go and say, OK, now RDD1, change it to something else. You can use other RDDs, but one RDD, once it's done its computation, it's immutable. And it lets the framework handle these things much better because it doesn't need to worry about overwriting data in RDDs. So once it's done, it's done. RDDs are typically created through parallel transformations, right? So for example, you have data that's stored in one RDD, and you can say, hey, my RDD2 is map of this function on RDD1, right? In reality, what happens is that RDD1 is stored in a distributed way across all of the cluster, the system can say, OK, I'm going to create a distributed RDD2 across the cluster, run each computation transforming data items locally in individual machines. So I don't need to do bring all of the data into one machine and then get it back to the machines on the cluster. You can do all of these in parallel at the same time. And the last interesting thing about RDD is that the data is stored in memory, so it can be cached for efficient reuse. So once you have an RDD, you can say, I want this RDD to be cached. The system doesn't get rid of it. And then you can say RDD3 is also using RDD1. When you say RDD3 equals some function on RDD1, RDD1 is already in memory and it's cached. So you can do a number of actions on the RDDs. You can, for example, do count. You can do join. You can reduce items like MapReduce, save, collect, filter. You know, really nice sets. OK, so in the next video, I will show you one example of how to use RDDs in Spark. Let's look at an example computation in Apache Spark. This example, we show some log mining algorithm, right? So the idea here is you have a huge amount of logs, and you want to load them into memory, find the log messages that contain an error, so a string error, and then interactively search for a couple of different patterns within these errors. This is a very, very common sort of computation in enterprise computing, and people do these in IT industry every day, a lot of times. So let's see how you can do this in a very nice fashion in Spark. So of course, I have a cluster. I have a lot of worker machines and, say, a driver machine that is orchestrating everything. Writing the program, the first thing that we do is loading the data stored on hard drives into one RDD. So I'm loading it from hard drives into memory, distributed across the cluster. So the first thing I say, hey, lines is spark.txt file, and here's the location of my data on HDFS, so a certain path. This lines RDD here becomes my base RDD. And after that, I'm going to build on top of that. So now that I have loaded all the log lines in memory, the next thing I want to do is find the ones that say error. So I can say RDD called errors is derived from the previous RDD lines, filtered. So apply this filter on every single element of the lines RDD, and find strings that are starting with string error. Now, two things here I want to discuss before continuing. So Spark uses Scala, and Scala is a functional programming language. So it allows you to write inline functions, very nice semantics. So one thing here is that in Spark, which is using Scala, when you see underline, like here, this means a single element stored in the RDD. So it says, this underline says, hey, take this line, take one single element, and run this filter sort of function. So take this function, use it as a filter, and run it on every line, every element on the RDD. And the other thing is that Spark uses the builder pattern, builder programming pattern. So you can have an RDD, say RDD2 equals lines dot, say, filter dot join dot another computation dot another computation. And in every, and the builder pattern ensures that these are all running on one after another on the same RDD being lines. So now errors here is now my transformed RDD based on the lines RDD. OK, what next? Now I can do some interesting data exploration on this. So I can say now messages are the errors that basically I take every single element of them and I split the whole string based on the tab character /t into two different parts. OK? So now messages, each element in messages will have two little strings. One is the part before the tab character. One is the part after the tab character. Now here's where it becomes interesting. You can do caching on RDD. So I can say, hey, OK, cached messages is messages.cache. OK, I'm telling the framework to not optimize things. In other words, do not remove cached messages from memory when it's looking for memory, and it will remain in memory. Now, what else? I can now filter again, this time the cached messages, and find lines that contain the string foo. And then, on the result of this filter, run the count command. Again, this is where the builder pattern is in action. And it's nice because you can say one operation after another operation, and it just happens very nicely. All right, so up to this point, all of these things that we did on RDDs were just transformations. Transformations do not run in real time. So in other words, I can tell Spark to run to make another RDD from the first RDD, and it kind of acknowledges it, but it doesn't necessarily do it. It does a lazy evaluation. It waits until we do transformation, 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 action, right? Once it reaches an action, and there is a set of predefined actions in Spark. I showed you, for example, counting is one of them. Once you reach an action, Spark says, OK, it's enough to be lazy. I need to do something. So it starts and say, OK, let me distribute this computation across the cluster and do all of these transformations, 1, 2, 3, 4, 5, and the action all together in the different machines. So each worker machine does the computation now that it's received an action, and basically returns the results to the driver machine. Now I can do a different filtering operation now. Remember, the cached messages is cached into memory. So I can now say, hey, take my cache messages, this time filter based on a different string, this time filter based on bar, and then do this action. Again, when it sees, Spark sees the action, it tells each node in the cluster to do stuff. Each worker works on the cached items and sends the results back. And here, for example, we have a nice result. You can see that you can do a full text search of Wikipedia in less than a second. If you wanted to do this on Hadoop, it would take 20 seconds. And it's because you have the overheads, and then you can do multiple different cache message searches, and never you hit the disk again. While if you wanted to do the search on Hadoop MapReduce, each time you had to reload the whole Wikipedia data set from HDFS again and again and again. In this video, we will show another example of using Apache Spark, this time for more of a scientific computing. It is definitely an iterative algorithm that we want to show how Apache Spark can be used for. Let's say our goal here is to do a logistic regression algorithm on a data set. So here's an example. Let's say you have a set of data points, and let's say each one has a label. Some of the data points are positive, some of the data points are negative. They're just, say, random bits of data. Now, you and I look at this and we say, oh, it's very obvious. These stuff are one class and these stuff are another class. But of course, we are humans, and computers have a little bit of harder time trying to figure this out. So logistic regression is one algorithm that tries to do this. And to be able to do that, it starts from a random guess. So it says, hey, so this is my target. And it starts by a guess saying that, hey, this is my initial guess. I think whatever's above this line is one class, and whatever's below this line is the second class. So the initial line is random. Well, we can look at it and say, hey, this is obviously wrong, but it doesn't matter because the algorithm iteratively works on the answer and fixes itself. So the first iteration, what it does is it finds, in each iteration actually, it finds the distance of every single item to the line, and then it fixes the line a little bit by saying that, oh, it's not quite balanced. Let me fix the line a little bit. So in the next iteration, we have this slightly slanted line. Again, we move a little bit more, a little bit more, a little bit more, a little bit more, until the algorithm says, oh, OK, I like this. So let's see how we could write this algorithm in Spark. And here you'll see the power of Spark in doing iterative computations on huge data sets within very few lines of code that look very easy to understand. So let's see. I start by creating an RDD, saying Spark, read from a text file somewhere on HDFS, for example, I assume. And again, remember, we are using the builder pattern, so we can take one RDD and do dot something, dot something, dot something, and it just works out very nicely. So I load the data. On each input item, I run a map function. What function do I use? I use the read point function to read the data points. And then I say, hey, let's cache this. OK, fine. So now data RDD contains a cached set of data points. And I can run iterations using information stored in data. So you can see inside my loop here that I'm running an iteration. I am using data RDD. And it doesn't need to load the data again and again from hard drive. Once we have cached it into memory, it remains in memory. OK, let me clean this up and continue. So the next thing I do is I say, let's have, now that I have the data, let's create a random line. So here I'm saying that let's take the vector package and create a random line, and let's call it the W line. That was the line that we saw in the previous picture, turning around. Now I start my iterations for I from 1 to the total number of iterations that I want. I can do iterations. Inside each, I can say, hey, let's make a new RDD. Let's do a map transformation on the first RDD, on the data RDD. Inside my transformation, I run the regular algorithm for logistic regression. I'm not going to cover that. There's lots of different places. Just you can see Wikipedia page for the logistic regression algorithm. But basically, it just does some sort of a inverse distance computation. So it finds the distance of each element inside the data RDD, and we show this by P. So we say, hey, take one element from the RDD and by this operator, equal this. I say take one element and do the rest of the operations on that. Okay, so what's the operation? I take that element. I take the x out of it, and then I take the y out of it, and then I multiply by w being my line, exponential 1 divided by that. That's the mathematical computation. Doesn't matter much here. Just the idea is that you can run this function over and over on this data set. Now, the interesting thing is that you can do a map and you can do a reduce. Reduce being an action makes the Spark engine go ahead and do the computations in parallel across the cluster. So just a couple of lines, and we can see that writing such a, these number of lines is actually not that hard. I don't know, maybe it'll take you like 10 minutes, 15 minutes, half an hour to write this. And you can get your data, insight into your data very quickly. More importantly, running this on Spark compared to Hadoop gets you much better performance. This is because you have cached the data in memory. And if you were running it as multiple jobs on Hadoop, each time you have to load the data again and again from hard drives. So let's talk a little bit about the fault tolerance in Spark. As we've been talking about throughout the course, providing fault tolerance in cluster computing environments is very, very important. And the reason for that is the fact that a lot of these infrastructure data centers, they just use COTS, commercial off-the-shelf components. And these components are not as reliable as engineering allows. You can probably design and engineer a hard drive that doesn't fail in like 20 years, but it's going to cost you $20,000. You don't want that. You want to just use hard drives that are $100 each, which means each of them has a certain chance of failure within a year, more chances of failure within 3 years. After 5 years, it's pretty much almost guaranteed that it's failed. So we are dealing with components that fail easily and fail commonly, and therefore the frameworks have to be able to respond to that. Let's see how Spark does this. RDDs which is really at the heart of Spark, they maintain lineage information about the data, right? So remember that when I was talking about the transformations and actions, said that Spark evaluates transformations lazily until it reaches an action. So it kind of just keeps that data around. So when it actually creates a new RDD, it just stores somewhere there that, hey, by the way, this RDD was created from this previous RDD plus transformation 1, transformation 2, transformation 3, and this action. Okay? It's just a little bit of data stored somewhere. If there is so for example, let's take a look at this example. You're creating a new RDD, messages. I'm saying that, hey, it's being read from the text file, and then let's apply a transformation called filter. Filter based on strings that are starting with word error. And then let's do a map on these. Let's take each element, apply this split function on every element. That's the meaning of map. Let's split them by character tab. Okay, so let's look at the diagram here. The data, the RDD, starts from an HDFS, the file, the data stored on HDFS file. And then once we load that into memory, we do a filter, and it becomes a filtered RDD, and then we do a map on it, and it becomes a mapped RDD. So the framework kind of just writes down these little bits of information here along with each RDD. If a certain part of the cluster fails, that means that an RDD is affected. In the worst case, what we can do is we can load up data from HDFS file again, apply these filters and these maps and all the transformations necessary, and we can recompute an RDD anytime that we require. And that's why that's how Spark provides fault tolerance. It keeps lineage of transformation, and if there's a failure, it can redo the computation. OK, so now that we've looked at Spark a little bit in detail, let's talk about some of the things around Spark that help you in addition on just RDDs and writing programs. The first thing I want to talk about is interactive shell. Basically, the interactive shell of Spark is a modified Scala interpreter that allows the user to interactively use Spark from command line in real time, right? So of course you can write a program like we saw in the previous examples, though, to load up an RDD and data, transform, map, blah blah. But you can also load up an interpreter and just interactively type those commands. RDD1 equals this, 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 enter. And it takes maybe 2 seconds, 5 seconds, whatever. And it says, OK, I'm done. RDD1 is memory. What should I do next? So to write the interactive Spark shell, the developers had to just slightly modify some parts of the Spark engine. They just had to make sure that as you're typing lines, it kind of keeps reference to objects that it's using. So there was just a little bit of modification there. And also, when you create a new class, it should be generated over the network across the cluster. So there was a little bit of work in there, but now the interactive Spark shell is there. It's a very powerful tool, and I definitely urge you to look into that. A couple of other interesting things. There are couple different frameworks built on top of Spark. In our last week, in the next week of lectures, we will talk about some of these. The first one is GraphX. GraphX is a graph processing framework, kind of built on top of the idea of the Pregel paper. Pregel is a framework introduced by Google in a paper, and there was an open source implementation of Pregel. Of course, there is Apache Giraph and other frameworks. So the same framework and ideas were implemented on top of Spark as well. Originally, it was called Bagel. Now it's called GraphX. And it provides the power of RDDs with some specialized RDDs for graph processing. Similarly, we have Hive on Spark. So Hive is a database querying engine, if you remember from our previous slides, previous lectures, weeks. We introduced Hive as providing the HQL language, Hive query language. And the same sort of engine is now implemented on top of Spark. They call it Spark SQL. At some point, it was called Shark, but now it's Spark SQL. And allows you to do some load up data from SQL-like data stores like HBase or Hive and into Spark. Provides you a very powerful tool. Just so you can imagine that in the interactive shell, you can say load data from an SQL sort of store, and then do some sort of RDD filter on it, and then you can just run a GraphX algorithm right after that. So that's very powerful. And the final thing I want to talk about is the MLlib, the machine learning library. It's also implemented on top of Spark, and we will cover that, so I won't talk about it much more here. OK, so in this last video, I just very quickly talk about the implementation ideas of Spark. So Spark, being like a distributed computing engine, runs on a cluster. As you can remember from our second week of lectures in this course, we introduced the fact that Hadoop 1 at some point was basically mixing the execution engine and the resource management all in the same framework. And there was downsides to that, so eventually people moved it to Yarn, where you had disjoint frameworks. Yarn was just managing resources, and then Hadoop on Yarn was managing the data flow of MapReduce on top of Yarn. So this is kind of the same here in Spark as well. You have Spark running on top of a resource management framework, for example, Yarn, or there's another Apache open source project called MESOS that can be used for Spark as well. So you can have different execution engines, being Spark or Hadoop or maybe even MPI, running on top of a resource management framework, for example, Yarn. And then, of course, Yarn is managing the physical nodes on the cluster. And another thing that I want to talk about is the Spark scheduler. Basically, what it deals with is the directed acyclic graphs, DAGs, kind of similar to what another framework from Microsoft, Dryad, used to introduce. So what really happens in Spark is that it takes your RDDs and transformations and the rest of these things and creates graphs of data flows out of your algorithm, and then passes that graph to a scheduler module. The scheduler module can try to see can try to identify stages within the computation. And each stage is a set of transformations followed by one last action, right? So that's why I talked about lazy evaluation of transformations, because a couple of transformations together plus one action become one stage, and then the scheduler schedules one stage after another stage after another stage. The scheduler also is cache aware, because in RDDs you can say rdd.cache, and therefore the scheduler can utilize that information and say, okay, RDD1 is cached, RDD2 is using RDD1, so let me try to schedule the computation for RDD2 on the same boxes that are caching RDD1. And finally, the Spark scheduler is partition aware. Therefore, it tries to consider the partitioning of the data to avoid shuffle. So, for example, it says, hey, some of my computations are requiring a group by operation, for example, in this picture, and then some other of my computations are using unions and whatnot, and it tries to consider that information when it schedules different tasks, so that it minimizes the network access traffic, so it minimizes shuffles as far as possible. Of course, I'm not going to cover everything about how Spark is working under the hood. There are, of course, courses on that you can continue learning about Spark, as well as documentation on the Spark Apache page that is quite comprehensive.
So let's get started on cloud computing applications. What we're going to look at in this section is big distributions of cloud computing applications that actually work together, and you can place them in a packet, well, place them in your system to give you the overall effect. So what can you combine MapReduce with? What databases? What sort of, let's say, streaming systems? What we'll look at is distributions of systems produced by several different companies that allow you to do a lot of flexible cloud computing applications and see exactly how they frame everything and what they provide. We can always go back to Apache. All of the applications, or at least most of them, are open source. So if you actually want to piece together your own package, you can. But this sort of way of distributing things that I'm going to show you is very convenient and allows you to download optionally to your desktop or to a cloud computing the actual frameworks, everything else, to do a lot of cloud computing applications in a sort of coherent way. So it's really worth taking advantage of. So first, I'm going to list some of the more, well, three really sort of important distributions of these cloud applications. One is Hortonworks, and that was kind of the original. It produced Hadoop, and then it went on to build more and more tools around Hadoop, and then it changed the underlying framework of Hadoop to base it on Yarn, and then it's moved on to not only do massive data computations, but also to do fast data that's streaming. I'm going to move from there to Cloudera, which is more a sort of focused effort. It usually is oriented around MapReduce application users, but they do provide some other features. And Cloudera is a really sort of solid platform. It provides a cloud support for Cloudera if you want to use it, so you can actually sort of run your applications on Cloudera. It's very sort of friendly to universities in particular. And finally, we'll talk about MapR, which is a recent effort to package things together. They have a slightly different take, But again, they're a company that provides these packages, and you really have to explore it to see what fits your better mood. But to summarize, each of these three are going to talk about open source Apache software systems integrated in different ways, and each of them allow you to download those complete packages to run. So let's start off with Hortonworks. Hortonworks is probably the granddaddy of the cloud computing application distros. What it provides is a very flexible, very dynamic, and very up-to-date environment. You can download it, as I said, to your laptop or to a cloud, build your own cloud type of thing, and you can either ask them to help you support that cloud, or you can just work with what they give you as open domain. Either will work for you. Hortonworks is certainly one of the distributions that you should look at, and it's, on the whole, I found very easy to work with. So, what do they provide? They have developed over the years a data connection strategy. They have two main thrusts. One's called HDP, and I'll talk about that a bit in a minute. But really, it's software based around Apache Hadoop. It's open source. It provides distributed storage, processing large sets of data, and runs on commodity hardware. That's its focus. Hadoop really has been instrumental in allowing businesses to quickly gain insight from masses of data, and Hortonworks has capitalized on that in building up a reputation, and it actually acts as a sort of resource to many different industries, companies like Yahoo. HDF is a new wrinkle on top of the connected data strategy. What it's trying to do is address real-time data collection, curation, analysis of data that's being delivered, and it can come from any device, source, or system, either on premises or off cloud, but the notion is to process these streams very effectively and then integrate those streams, the data coming in those streams, with your HDP, with your framework for storing large amounts of data. So this is what we're going to talk about for a second, and then we will see how other companies relate to this. But first, what does Hortonworks provide? This is their diagram of tools, and as you can see, it's very complicated, it's very flexible, and what they've done is to build layers of tools. So you don't just get Hadoop by itself. What you're getting is operating systems to manage it. You're getting distributed file systems. You're getting all of the things to manage life cycles for the data. You're getting workflow software. You're getting security with this system. And you're getting operations. So you can actually manage how this thing is occurring, how the whole scheduling of your Hadoop jobs go, all sorts of issues. And there are additional tools hidden behind the back that keep everything consistent and working in the way that you would reckon they ought to work. So just sort of giving some of those tools, it starts off with providing you an environment, a toolkit, a Zeppelin, which is a notebook. Now, electronic notebooks are kind of recent. What you do is in that notebook, you keep notes of what experiments or what computations you've done. You can actually write code into those notebooks. The system that Hortonworks uses is called Zeppelin, and it's a very, very new sort of notebook system. You might have heard of other ones. I think there's a Jupyter notebook as well out there, but this is the Zeppelin is the one that comes with the package. It allows you to write all sorts of interfaces, or you can just ignore Zeppelin, you can go straight to the tools. The tools, well, all sorts of data access tools. There's batch like MapReduce, there's script like Pig, there's SQL like Hive, there's beyond SQL, HBase and Accumulo, And now coming up a new item there, Phoenix. There's Storm, which is used for streaming. There's Search in the form of SOLR, in-memory, Spark, and then there's some other pieces that are more focused on specific platforms like Microsoft platforms, Azure platforms, or whatever. All of these use HDFS, which is a distributed file system, and it resides under all of this. That allows you to increase your data, to store it safely, to be able to retrieve it. What we're going to be showing in the next few slides is just how all these things fit together, how you can piece and match these different tools to build your application. From the top, Zeppelin. It's open. It's a web-based notebook. It allows you to have interactive data analytics, so you can actually put scripts into Zeppelin, and those scripts will execute and create little data analytics on your, well, little compared with the amount of data on your screen, and it will do that sort of interactively in real time. Beneath that, on another HDP tool that's being packaged with the system is Ambari. It's used quite a bit. LinkedIn uses it. And what it does is source management platform for provisioning, managing, monitoring, and securing Hadoop clusters so that you can actually see how your Hadoop cluster is behaving. Look at how Zeppelin works. It takes a lot of different languages. You can write Zeppelin scripts in Python, Spark, or Scala, or a lot of other ones. What it provides is a web display of the results of your computations, and you can see that you can put visualizations into the notebook, you can put bar graphs, you can just list tables, but this is all the mechanism. If you look above that, those diagrams, what you'll see is some scripting code that gets invoked to actually do those particular diagrams with a particular data set using some of the other tools. Zeppelin, you can have different views of what's going on under the lid. So you can take TES, and that would tell you about your cluster resource or usage. So if you want to know, do you have a network bottleneck, or is the file system a bottleneck, or do you have spare cycles on your machine? TES will actually allow you to see what you can do to accelerate individual jobs and do some optimization. There's a Hive view, which allows the user to write and execute SQL. Now, Hive is interactive, and it's built into Zeppelin so that Zeppelin can script and interact with you as well. Shows a history, allows you to see all sorts of views, source views, JDBC, ODBC, CLI. It allows you graphical views of the query. So it's sort of helping you really sort of get on and produce the products that you want. Pig is a scripting tool. Now we've talked, well, we will be talking about MapReduce. The Pig view actually allows you to combine all sorts of different tools like MapReduce into multiple occurrences of use of that tool, and you can use it for iteration with MapReduce. You can use it for saving and loading data sets, all sorts of nice sort of additional tools, but the Pig view allows you to see this and to script this and to manage this. Under that is a scheduler. They allow you to see the capacity scheduler from Yarn, and we'll talk a little bit about that in a second. But when you set up your workload management, you enable multi-tenant, multi-workload processing. How do you schedule? Well, you obviously want to use full capacity of the system you've got. This view provisions cluster resources, allows you to see them, allows you to create them, and allows you to manage them. That's another useful tool in this notebook. And then last, file view, that allows you to manage and browse all the software that you've placed into HDFS. It can be very, very useful when you've got lots of files. So moving from there, if we want to talk about data access, it's worth in Hortonworks mentioning all of the steps that have gone on to producing this distribution. We will be talking about MapReduce and Pig and all these other good things. And MapReduce will be based on Hadoop. But underneath all of this, there's been lots of work by the Hortonworks people to simplify the management and to provide a very flexible management system, and that's called the Yarn. They like to call it a data operating system. So Yarn is, if you like, underlying all of these applications and enables these applications to talk to each other. You might sort of argue, well, Yarn is a bit like Office is to Word. Yarn is to sort of MapReduce. Underneath all of this, the glue that allows you to build very, very interesting flows of data from one application to another, that would be Yarn, and it would be doing the scheduling and allocation. So it takes, or it has APIs for MapReduce, Hadoop. You don't have to change your Hadoop, it's the same API, but it will run those MapReduce jobs in batch for structured or unstructured data. Pig, we've mentioned a bit, but it's really sort of a scripting language for building data pipelines. So you can sort of imagine almost like a shell script of doing MapReduce jobs and doing other sorts of processing on it. You can describe this with a script and then run it whenever you want. So Yarn supports Pig, and it supports the data flows that occur in Pig using the other tools. There's an SQL. Hive has this interactive SQL query, and you can make queries over petabytes of data in Hadoop. And again, Yarn is the underlying fabric that connects these things together, so you can take your output from Hive and put it somewhere else, or so that you can use input to Hive from some HDFS. There's a NoSQL or beyond SQL or whatever you want, not just SQL. HBase and Accumulo are two non-relational NoSQL databases. They're written on top of HDFS, so they work with huge files, but they allow you to almost sort of SQL-like queries, even though the data is absolutely huge. In the case of Accumulo, there's additional column and cell information that you can store, so that you can actually provide access controls to some of the data in your database. Next, we have Storm. Storm is a distributed real-time, large volume, high velocity data. It's really sort of pushing the limits. But this allows you to take, say, lots of mouse clicks and process them, feed them into a database, or it might be that it takes Olympic results or results from car racing or whatever it is, and stream all this stuff in real time and record all of that data. It will take images, it would take all sorts of different data formats, and you can process them. And they're clearly in memory processing, but it processes huge amounts of data in either sort of streaming or sort of just stationary data. Spark allows you to do those. It's got a nice, easy language and lots of libraries to do that. And again, the coordination between Spark and HDFS and all the other parts of the system is all done by Yarn. Underlying all of the Yarn, the data, that resides in your HDFS, and we'll be discussing that in a subsequent lecture. Just reviewing quickly, MapReduce, why would you use MapReduce? What's the purpose of having that in a distro? Developers can write applications very fast. They can use any language they like. And what you use is an API to actually do your MapReduce. That allows it to manage a scalable number of computations from a single stream. It allows you to do really sort of fast parallel processing, and MapReduce will sort of knocks off days of what used to perhaps, well, knocks off weeks of what perhaps used to take months to do. You can get things done in a few days that are really remarkable. It allows you recovery, it supports recovery of the system. So if one of the processors dies, you don't have to worry about it. The MapReduce system will actually try and recover and continue without you even noticing that any of the data's changed or anything else has happened. And it also minimizes the way that data has to move around the system so that you get the maximum performance out of all the system. You're not just waiting for memory copies or things. This really offers a very sort of economic way of performing your computations. So that's what you get from MapReduce, and it's in the form of Hadoop in Hortonworks. And again, if you've learnt Hadoop from Apache, this Hadoop on Hortonworks is exactly the same. The interfaces are all the same. Pig, well, we described a bit about that, but some key factors. It's extensible, so you can add custom functions to Pig to make it do all sorts of interesting things. It's easily programmed, and you can have tasks involved in data transformations. They can be simplified, encoded as data flow sequences. This is really cool. And then it's self-optimizing. There's actually tools that will go through and try and optimize your Pig expressions, because they may not be the best way of writing it, but there's self-optimizing code that will actually reorganize it so it is efficient. Hive, that's the database, that's the interactive database we talked about. First of all, it's using SQL, so it's familiar. It's fast, it will give you results very quickly. You can run it from the command line. Scalable, extensible, so you can have 10,000 disks with data on it and still be using Hive. And it's compatible with all of the other tools and systems that we've been talking about. No SQL, HBase, that's our big semi-relation, not, well, beyond data relational in a sense. It's fault tolerant, it replicates itself, it can provide you atomic updates, it can provide you strong consistency at the row level operations. It's highly available, so it's really cool for sort of interactive services. It provides automatic sharding and load balancing. It's fast, gives you near real-time lookups, in-memory caching, server-side processing, so it's rather cool. And the main thing is it's usable. And the data model accommodates a wide range of use cases. It's reasonably understandable. You don't need a PhD to understand it. It exports metrics via file or Ganglia plugins, and then it has an easy Java API to use. It's coupled with Thrift, REST APIs, so that you can actually build web interfaces, or you can have data transformations on the information you're providing to get it into the right format for putting in HBase. So that, again, is pretty cool. Accumulo is an addition to these databases. It was provided by the NSA. It has a table design and configuration, allows cell tables, and gives you cell level access control, which is very important for some applications. It has integrity and availability. There's a master failover, and Zookeeper, which is this consistency software we will talk about later, provides that. It has write-ahead logs for recovery. It's scalable, and it really performs very well. Relative encoding to compress similar consecutive keys, so you find the keys stored near to each other in the big data center. It speeds long scans if you're trying to look through lots and lots of data, and it caches recently scanned data if you want to write iteration over some data rows or columns. And then it is really good at sort of managing data, group columns within a single file, and so on. So we'll be looking at some of those things in the future. Really sort of now edging into the the new features of Hortonworks. You've got Storm. This is a streaming system. It's been benchmarked. It can process 1,000,000 100-byte messages per second per node. It's scalable, has some fault tolerance, it's reliable, and above all, it's easy to operate. So you can actually use Storm very simply to build the customized applications you want. Solar is a search system, uses standard-based interfaces like XML, JSON, and HTTP, provides statistics, linearly scalable. So that gives you an entree into doing your own search systems within all of the data that you've collected. Last, as I say, we've got Spark, which is this in-memory programming core. They actually call it Spark Core. It allows you to program with Scala, Java, Python, R. It has the APIs to link those to libraries, and those libraries are quite extensive now, which makes it very exciting. So you get mlib, you get Spark SQL, Spark Streaming, GraphX, ML Pipeline for data science workflow. And we'll be coming back to that Spark system later on. But for now, this is all maintained and running on Yarn in the Hortonworks, and you can match and mix between all of them. So now let's move on. We talked about HDP, but if we want to look at what Hortonworks is doing with data flow, well, they have a lot of offerings. They have something called NiFi. They have, and NiFi is a way of managing data logistics and event processing. They have Kafka, which is a messaging system, and systems can break or go down, but you're not going to lose the messaging in that. We have Storm, again from Latin. I talked about Storm before, but it's integrated into this platform as well, and it provides you your linkage between HDP and HDF, so you can go backwards and forwards. You can stream data into your big data stores, or you can stream data out of your big data stores and analyze it and pipe it out, or you can integrate in any which way those systems together. What HDF does, real-time data collection, real-time curation, analysis, delivery of data to and from any device. And it doesn't matter, it can be on-premise or in the cloud, it all works. It's all open source. Moving right on from there, there's a picture of NiFi and the way it organizes things, and that's probably very small, but we've got a lecture on it later on. If you're interested in NiFi, you're looking at the, well, I won't say the bleeding edge, but this is really new stuff. And as I say, we're going to have a lecture by Reza on NiFi, and I think that'll be really sort of interesting for you. But what it does, you have objects moving through the system, a flow file representing it, NiFi keeping track of these key pair attribute strings as they move through. You have sort of black box flow file processes, allows you to do different sorts of manipulations. You have buffers and connections that you can make, and you can decide how much buffering you want in there. Has flow control schedulers for the buffering, and process groups that you can schedule, and you can have subnets connecting those processes together. So it's fairly a flexible system, but as I say, it's really new, very exciting, and lots of things that NiFi can do are still sort of bleeding edge. People are working on using those. So what you've seen today is an introduction to all of these distributions. Now we'll move on to Cloudera, which adds, well, which is a different approach from Hortonworks. So Cloudera when you're ready. Cloudera is an alternative version from Hortonworks. It's still using many of the same components from Apache, but it integrates them differently. And it allows, well, it provides an environment on the cloud. It has its own cloud that you can use, or you can actually download that environment to your desktop and use it there. So this is what Cloudera provides. And as you can see, they have a smaller offering from Hortonworks, but nevertheless, it's a very solid production-oriented version. If you like, Cloudera is a little bit more conservative than Hortonworks, provides a little less systems that are on the bleeding edge, but those systems it does provide have been very well thought out and very well integrated. So it has, for operations, its own Cloudera manager and its own Cloudera director. It has several tools, the batch, Spark, Hive, Pig, MapReduce, the stream, like Spark. It has SQL, like Impala, and then search, Solar, and it has other offerings which are not in Hortonworks, things like Kite. It has a set of unified services, so a platform, so you can actually integrate these things together. You can pass one to the other. It uses Yarn to do that. Sounds familiar from Hortonworks. It provides security. It uses slightly different software for security, but essentially providing the same thing. Then underneath it, it has the HDFS file system. It also offers a Kudu relational database. If you want no SQL, then it runs HBase, and it provides other things like object stores, should you want those. And the integration, you can run batch or you can run real-time. On batch, you've got things like Scoop, somewhat similar to what Hortonworks does. On real-time, you have Kafka and Flume, again, something like Hortonworks. And as I say, this is packaged. A lot of the universities use Cloudera. It's a very sort of nice and easy system to use. So that's another package for you to consider. Finally, we'll talk about MapR Distro. This is a new startup. It hasn't quite got the same sort of breadth as the other two, but nevertheless, it's a growing business and it provides many of the similar tools that you've seen before. So it will do MapReduce, but the Hadoop in this case is really optimized. It's written in C and C++, so it runs very fast. It uses the NFS file system instead of some of the other approaches that we've seen. So being integrated with NFS, you can easily do sort of distributed computation. Doesn't quite have the same sort of HDFS-like nature of it, but NFS is often very familiar to a lot of people. I believe you can use other, well, you can probably use HDFS with it as well. It's interactive. It has interactive SQL, a system called Drill, has Hive, Spark, SQL, Impala, again out of the Apache open source folder. Its database is slightly different. It has an optimized database called a MapR DB, and so this is its sort of niche, if you like, compared with the other two. It has its own sort of form of doing those databases. It again uses SOLR, and again it uses stream processing, but this time it's using sort of MapR streams. And that's really based on the effort that they've put into actually representing data and managing data inside their big data system. So this MapR systems is something you want to watch and see how it develops. Feel free to go download it, try it out, and feel the differences between these three different distribution systems. Thank you. All right, we've been talking about large-scale data processing, but clearly you have to have a large-scale data store to do the data processing. What we've seen is that we can build many tasks, processing lots of data in parallel. We can create lots of data from lots of data. And that large-scale data processing is based on using COTS. We want to use thousands, tens of thousands of CPUs. But what we want to extract from this, or step back from this, I should say, is actually having to think about each individual machine. We don't want to manage storage. We want an automatic storage system. Now, fortunately, we built distributed storage systems, and distributed file systems are well on the go. They've been used for a while. What we haven't built is really large-scale distributed systems, distributed storage systems, and that's what we're going to talk about with HDFS. And it's sort of like one of the first in its kind, and that's why it is very important to understand. It's the main engine, data storage engine under Hadoop, so that makes it very important. Now think about your storage device is a disk, say, and it's going to fail, 1.7% of the time, according to Google, some of Google's analysis. So that kind of constrains you. Now, if you go to 3 years, it will be about 8.6%. So the percentage rate of failure increases. Okay, now let's suppose you have 10,000 nodes, and each of those nodes is designed as a storage node. And that's a kind of typical thing that one might do in a big system, in a big cluster. You could have 7 disks per node, so the disks can keep up with the CPUs, so 6 CPUs on a node. Just think of that, 7 times 10, you're up to 70,000 disk devices that fail 1.7% of a year. So you're looking at something like 1,190 failures per year, or about 3.3 failures per day. So if you're in that building, you're skating around replacing disks at least once every couple or 3 hours. Clearly that's a mess. Just think what that does to your software. So we don't want to know about this. We want to hide this. HDFS, what its beauty is, it's going to allow us a distributed file system that matches all the parallels, reads and writes, and just removes the headache of understanding disks that fail and don't fail, because it's going to provide fault tolerance. So we got MapReduce. MapReduce is going to give us user functions, automatic parallelization, fault tolerance, I/O scheduling, status monitoring, and now we've got HDFS, and it's going to work with Hadoop, and it's sort of inspired by MapReduce. It's also inspired from the Google file system. Its idea is to have massive throughput by making lots of things in parallel, and it's distributed parallelism. The throughput scales with the attached devices you've got. As you increase the disks, as you increase the CPUs, the throughput scales of the file system. And you can have very, very large production clusters. If you want to look at some of the bragging rights, Facebook, Yahoo, they all have very large systems. Doesn't pretend to look like a Unix file system, although, as we will reveal, it's actually built out of simple Unix file systems. So one must forget a little bit all of the POSIX requirements. What it gives you is just enough POSIX to actually do your MapReduce jobs competently and correctly and quickly. So it's optimized for reads, especially for sequential writes and appends. And the other parts of what a file system would normally do, it ignores because it's focusing on big data. So if you would like to read about how this approach came about, the Google file system, SOSP 2003 is a good article. Or if you want to dip into Hadoop, the Hadoop distributed file system, there's a description of that in 2010 symposium, or you could just go to the tutorials that are on the web. So what we're trying to do is to ignore failing systems. How can we store data persistently without worrying about the devices? So the distributed file system gives you access to multiple file systems. It obviously allows you to replicate files. It allows you to have a big namespace, a global namespace, and there's lots of distributed file systems around. Typical usage pattern is huge files, hundreds of gigabytes to terabytes. The data is rarely updated in place. Multiple copies allow you to have availability, because if you can't get to one node with all of the information on, you can get to another. And reads and appends are commonplace because you don't really want to copy huge amounts of data if you can avoid it. The data node servers a file. What we're going to think about is just how do you achieve the parallelism in a distributed file system. And the data node servers are the way to do that. What we're going to do is to take a file, and it can be a huge file, and we're going to split it up into lots of little chunks, and we're going to put those chunks on lots of different servers. Now, I say little, the chunk is between 16 and 64 megabytes. The reason for that size is that you can distribute them in a nice even way over lots of different machines. All of these data node servers that take care of their 64 megabyte chunks send a heartbeat and a block report, and there is a central coordinator called a name node. It's going to gather all of these heartbeats and block reports and keep a tally of what the actual file system state is with all of the failures and all of the updates that are out. There's going to be a specific replica placement algorithm. It's going to take your data and it's going to put your data exactly where it should be, if it can do it, right where you're going to use it on a node. So if it can find a place on that node, it's going to place a copy of the data right close where you're actually going to use the data. It's also going to keep a copy of that data in the local rack. The racks are lots of storage, lots of nodes in one rack space. It's going to keep a copy there so that it only has to go through one switch to get to where it's needed. And it's also going to keep a copy in a different rack. And there's logic behind this. If your node dies, you can get hold of the copy somewhere else. If your rack dies, you can still get hold of it. It's in a different rack. So there's lots of backup. It looks like this. You have your application reading, writing HDFS. It's going to be using TCP/IP protocol to actually talk to all of the different devices. It's going to be accessing what it needs by going to a name node, a centralized node that really sort of orchestrates everything, that provides a file structure and directory structure for everything in HDFS. Now, it can have shadow copies so that should name node die, it can be replaced. And those shadow copies would typically be either checkpoints or incremental updates from name node to other copies of name node. If the main name node dies, then you would switch in a replacement. Name node then talks to individual data nodes in order to accommodate all of the storage. And these data nodes actually read and write to their local file systems these chunks we've been talking about, 16 to 64 megabyte chunks, and they keep track of where they're putting them in their file system. All of that information is recorded so that should you need to rebuild this system, you can do so, and should you want to rebuild the name node, if there's a catastrophic failure somewhere, you can still do that from all of this information that's already stored. So there's lots of redundancy in this so that the redundancy allows you to rebuild things so you don't lose all of that big data. Now we're going to describe how this operates, and one of the things we're going to emphasize is this has got to be efficient. So when we're actually writing files, what we're going to do is to write to local file systems on the node that does the computation. Then what we're going to do is to take that data and enter it into HDFS. So if you like, as your computation here does its thing, what it'll be is producing files that need to be updated into HDFS, and it's going to gradually, incrementally do that and spread it across this distributed system. So we've seen it as a master node called name node, stores this metadata, could be replicated. The client library knows about file access, it talks to the master, it talks to the data node chunk, connects directly to the data node service to access the data. We've seen some of the tools to build that type of web system in the past, and it would be used here. What we would like to do is to make sure that that replication that's going on in HDFS doesn't impact the clients. So when the client receives a response from the name node, what it does is to flush its block in small pieces, 4K chunks, to the first replica, and then that in turn copies it to the next replica, and so on. So it chains down through the list, through the replicants of that particular 4K block, the copies, and thus the client itself doesn't actually have to do the duplication. It's all done by the back-end system. Thus the data is pipelined from the data node to the next, to the next, to the next, all taken care of in the background without you having to program that. Staging is a really important thing. Client requests to create a file. It's not going to reach a name node immediately. What's going to happen is you're going to cache it by copying it into a temporary file locally, and then you're going to send that copy over through name node to the appropriate data node. So the name node will insert the file name into its hierarchy when you've created the file. It allocates a block for it, data block for it, which will be on one of these other locations. The name node responds to the client with the identity of the data node and the destination of the replicas, so it doesn't get in the way of you transferring all that data. And then the client flushes the data from its local memory out to the data node where it will be stored. So in this way it gets very efficient, very fast for the writes. The reads are exceedingly fast because you've again got separate data pipes from those data nodes. So what's the bottom line on this? What does it look like? Well, HDFS does provide a file system lookalike. There's a Java API for applications to use. Python Access is also used in many applications. C language wrapper for Java API is available. What it looks like is this down here. What you'll be running is Hadoop, and then you'll be running its distributed file system. So you say Hadoop DFS, and you'll be giving it various commands, and these commands are what you know pretty much from normal file systems. Make directory, ls, whatever. You have all of those operations available to you, except it's going to be doing that in parallel in a distributed manner. And here's the directory that this directory is the HDFS directory, and it's known by name node, and it's going to be distributed. The actual storage is going to be distributed for footer over a lot of sites. So you can use an HTTP browser to browse the files. You can access it through normal commands using this type of approach. It's very flexible, and it's the building blocks for all of the other different tools that we've been talking about, like, for example, Pig. Next, talking about big data systems and the data operating systems, I want to introduce you to Yarn and MESOS. They're kind of different systems, but they do the same function, and you'll find a lot of similarities between them. That over time, they've evolved to have similar features, probably through competition. Which one you prefer to use is probably up to you. But let's go through and see what features they actually provide. So MESOS was built to be a scalable global resource manager, and it would encompass that entire data center. You could build systems to do Hadoop or to do MPI, the scientific messaging system that's very popular. Yarn itself was built a little bit later. It came out of the success of Hadoop. Hadoop was so sort of useful, and some of the tools associated with Hadoop were so useful that it was felt to actually provide another basis for building Hadoop, so you could extend it and so you could connect other tools into it, and Yarn is that sort of product. So let's look at the Yarn Resource Manager. Yarn has all sorts of pieces in it. It has a scheduler, it has an applications manager, it has a node manager, and then its API is completely compatible with Hadoop, MapReduce. You don't need to make many modifications to run your code on it. So it has a scheduler. The scheduler provides pluggable partitions, policies to actually manage the resources to schedule items on queues and on applications. There are two main schedulers. One's capacity scheduler and one's the fair scheduler, and they've been rather popular in the past. That scheduler is sort of kind of in the central place of the resource manager. There are node managers actually out on all the individual machines in the cluster. They take instructions from the resource manager and manage the resources available on a single node. So that's where you're sort of drilling down to what the capabilities of the individual machines in the system are. There's application managers, and those negotiate resources with the resource manager, and they work with the node managers to start up containers. The containers will contain the actual jobs that are to be run, and they put them in containers so they can be moved around, and so that they can be streamed together, they can be managed together. So you have multiple levels that are organized, coordinated by Yarn. You have a container system under this. You have the applications on top. Now, if you look at that diagram, what you'll see is that the clients negotiate, they talk to the resource manager saying, oh, they want whatever jobs. The resource manager then goes off and looks for the application manager to see how to do that, but it's also collected all the data from the node managers, so it knows what can be done, and it's going to pass out bits of the jobs into the system. You can see that there's containers created. Those containers will actually be pieces of the job that are talking backwards and forwards to each other. The containers are responsible to the application manager. The application manager is going to be coordinated with the resource manager for the clients. And then the node manager is going to be feeding into everything, saying those resources are still there. If something fails, the node manager will disappear. The resource manager will realize that, and it would start some sort of recovery mechanism and redistribute the load to make sure that things really work. So that's your Yarn resource manager. If you step inside the system, the Yarn system, what you'll find is it has a whole bunch of other services in there. It has a resource tracking service, and I think this is one of the key ones to understand it a bit. It's connected by RPC to all of the nodes, and it responds to those, and it uses those RPCs to keep a information system about how all the nodes are behaving, what they're doing, whether they're still up, whether they're still talking. If you get new nodes in the system, it would register those new nodes. It would reject requests coming from invalid or decommissioned nodes, so it sorts out what's actually alive in the cluster. Really, at the bottom of this, one of the important factors is just how does your cloud fail, and can you recover from it. And if you're going to look at that, because it's a distributed system, you really need to have some mechanism to know that everything's still working perfectly. The system uses heartbeats. Each node sends heartbeats. They're collected by this tracker service. Then the Yarn scheduler examines what is actually alive, and if it needs to make adjustments about how things are being scheduled and run, it will do so. But now I've sort of glossed over lots and lots of details in there. We might come back to that later, but mostly a lot of this is best, certainly in this course, best sort of just assume that it works in the way it's described without looking at too many details, because it would take you another semester course to actually go through all of the details. MESOS is a sort of command and control type of thing. It was built by Berkeley. The master decides how many resources to offer each framework. It's given an organizational policy, say fair sharing, strict priority. It has more different sorts of schedulers. It has a scheduler for MPI. It has sort of standby masters. When you want to run something on MESOS, then there's going to be an executor that takes it and runs it. Of course, there will be lots of tasks associated with it running, but there will be an agent responsible. And so you sort of get a hierarchy of systems operating under the MESOS master. MESOS operates in a sort of a different way from Yarn. Let's suppose, well, here's a picture of how it works. Let's suppose agent 1 wants 4 CPUs and 4 gigabytes of memory free. Then it would send a request to the master, invoke an allocation policy. It tells it that framework 1 should be offered to all available resources, and so then you get a communication 2 on this diagram. The master sends a resource offer describing what's available on agent 1 to framework 1, and then subsequently the framework scheduler replies to the master with information about the 2 tasks to run on the agent. Says, oh, I used 2 CPUs, 1 gigabyte RAM for the first task, and 1 CPU, 2 gigabyte RAM for a second task. And then once it's all sorted out, the master sends the task to the agent, allocates appropriate resources in the framework, launches the 2 tasks, and away it goes. Much more sort of a sort of controlled environment using all of the resources in the system. You might say, well, that's very interesting. Are there any cases where I can take advantage of MESOS and Yarn, the Yarn flexibility, the MESOS MPI and all the other bits and pieces? And indeed there are. There's frameworks out there which allow you to build composites. Project Myriad allows you to put MESOS with Yarn and basically have the best of all worlds in that approach. And the way it does is it provides a distributed system that negotiates between the MESOS and the Yarn to actually decide how to allocate resources. This diagram sort of illustrates exactly how the control flows are operating in that way. And as you can see, both the master and the Yarn are sort of interacting through messages to allocate resources. Yes, you can have very, very complicated distributed operating systems managing those data systems in your application, and this allows you really sort of the best of both worlds, because first you don't have to worry about the underlying framework. You've either got MESOS or Yarn to help you do that, or MESOS and Yarn to do that. You can concentrate on your applications. Well, welcome to Module 2 in our Coursera program. What we're going to look at now is large data storage, large-scale data storage. What is interesting, and I want you to appreciate it, is the difficulty of actually having huge amounts of data on common everyday COTS devices. So what we're looking at is huge amount of data that exceed disk sizes being spread over distributed systems. Perhaps each node has maybe 7 up to 12 disks attached to it, and those disks might be 1 terabyte, they might be 3 terabyte disks, they might be 8 terabyte disks, depending upon just what the configuration is, and they're still not big enough. So you have to spread them across multiple, not only multiple disks, but you also have them on multiple nodes within the cluster. Now the question is, when you read these, everything's fine. What you get is pretty much what you would expect. When you update these disks, and there's the possibility that some of the updates fail, there's the possibility that you may update things while other processes are reading these disks. Just imagine the case where you're sort of inputting a huge amount of mouse clicks, updating your data with these mouse clicks, and somebody's trying to read. So you have consistency problems within all of this big data set. What you would like it to do is to represent really what's happening, the truth on the ground, but the update properties might take a while to propagate through the caches and all the other bits and pieces. And so there could be some problems. So this large-scale data storage is non-trivial. And I'm going to step you through what we're going to talk about. First of all, it's big enough that you need to think about what is the consistency of those systems. And we could build transaction systems, we have done in the past. If you do it on a single disk with a single database, it's kind of easy. Nevertheless, there's a lot of literature about transactions. If you do it at this scale, it's very complicated because the transactions themselves, the overhead in doing those transactions will slow down what you're trying to do with all that data. Because you've got so much data, you're going to have a big penalty in latency. So what we're looking at is techniques to make sure that you can actually do the data operations you want on that huge amount of data and get the sort of results you want, and sort of methods to do that. And one of the approaches is to relax that whole notion of atomic transaction and get sort of an eventual consistency model. So I'll be talking about that first. And then after we've done that, I'll be talking about trade-offs on this sort of consistency model, what you can do, what you can't do, what's good in the consistency model, what presents a problem. And we move on, we discuss it in terms of ACID, which is this sort of transactional approach. We'll discuss it in terms of, well, okay, maybe you just code it very carefully to avoid some of the races, some of the problems with consistency you will get. We'll discuss BASE, which is this technique for programming that way. And then once we've done that, we'll go back and sort of say, well, now what are the big systems actually doing these days? So you have these systems coordinated to do sort of things like eventual consistency or whatever, no SQL databases and so on. They're all relying on certain properties of the system that are maintained, and those properties at a sort of second order have to be kept in sort of step consistent. What we find is that there are algorithms that can be used to do this, and Paxos, very famous algorithm, is one of those that's used very frequently to build, that's been used to build these type of systems. Now, Paxos is complicated, we'll explain it, but if you want a simpler type of approach, you can look at something like Paxos. Zookeeper is a sort of a cut down, more sort of easy to comprehend, less distributed algorithm that you can sort of really appreciate and see why it works, and much easier to argue about. So at the end of this section, what you'll have is an appreciation of the difficulties of having large data, and then different sort of approaches that we can use to solve that, and the current sort of schemes to provide these sort of consistency for this big data and what techniques, what sort of subsystems are being used to actually do that. And we'll wrap it all up, and that's then move on to the examples of these systems in Module 3. Thank you.
In today's computing world, a lot of computing tasks are actually composed of processing massive amounts of data, right? We're talking about big data, of course, petabytes of information produced per day. You need to process these information and create other massive data sets. And this chain keeps going, right? So you really have large-scale data processing. You want to use thousands of machines. Large companies, Silicon Valley companies, they have clusters of hundreds of thousands of machines, sometimes up to millions of machines, working on tasks, of course, in parallel. And just you can imagine, when you have 100,000 machines, how will you manage these many machines? When you have a single machine, something could go wrong in a year. When you have 100,000 of these, every hour, every minute, there's something going wrong. How would you manage so many machines? That's basically the motivation behind these programming frameworks that we are talking about in this course. This lesson, we talk about MapReduce. Later on, we'll talk about other things. What MapReduce tries to provide is a set of user-defined functions that fit within a larger framework. The larger framework provides functionality already written that could work for many default cases, and the user-defined functions that the user provides specify the specific functionality that the user programs. If the user adheres to the standards of the framework in return provides automatic parallelization and distribution of the work. It also provides automatic fault tolerance. So when any minute one of your 100,000 machines fail, the framework will automatically take care of the job. Of course, the machine has failed. It announces this information to some admin somewhere so that a hard drive has to be replaced or something. But the job doesn't fail. The framework figures out that, hey, that machine failed, I need to go around it. It provides facilities for I/O scheduling so that the programmer doesn't need to load its data, the program's data, and then figure out how to store the data. The framework takes care of it in the context of hundreds of thousands of machines. And it also provides for status information and monitoring so that you can figure out in a glance how your whole large cluster is working, and is your job having progress on this large infrastructure or not. So in the next video, we will start looking into the motivation and, really introduction of the MapReduce programming model and really its implementation, Hadoop, that we will talk about in upcoming lessons. So in this lesson on MapReduce, we will, of course, talk about the motivation for why you would need a MapReduce model, something like a MapReduce model. Then we will introduce the programming model, specifically the MapReduce. What is map? What is reduce? How to think in terms of MapReduce. And we do that by providing a whole bunch of examples. Start with word count, then show you how pi estimation calculation could work out in MapReduce. Image smoothing is something that could be used for image processing, and that's one of our examples. And finally, we spend a little bit of time on introducing PageRank. PageRank is one of the well-known algorithms in the web area, and a lot of the web search technology is really built on top of PageRank. So we will take our time and talk about PageRank and how it can be implemented in terms of MapReduce. And then in our upcoming lessons, of course, we will talk about MapReduce execution. So speaking of the motivation for MapReduce, let's actually first look at what was there before MapReduce, right? That helps us to draw a picture of why we need to move towards something better than what we had before, right? So originally, when you had a large cluster of machines, and this was more common in the context of supercomputers, but supercomputers, after the very first years of computing, they turned out to be just a massive number of computers as well. Now, of course, supercomputers have specialized networks, specialized I/O, but anyway, they are a large number of individual machines, very much like our today's clusters, right? So the very common programming framework for distributed systems in general used to be, and it still is in some circles, MPI, Message Passing Interface, right? What does MPI give you? MPI basically, at its most basic level, gives you two basic blocks, MPI send and MPI receive, right? So one program running on one machine can say, hey, send this bit of information to machine number something, and the other machine can say, receive that information from the first machine, right? And that's all it gives to you. I mean, there are other functions built around it, but that's the most basic idea. Now, the problem is that this abstraction is too simple. Deadlocks are very possible. Whenever you have a block in communication, it can cause deadlock, right? So let's look at an example. Let's say your program says that, hey, MPI receive from process 2 message A. And this happens in process 1. Now, once you are done receiving an information from process 2, then send message B to process 2. This is a simple program, right? And process 2 does the same thing. It says, hey, wait for message B from process 1, and then once you receive it, send back some other message, A, to process 1, right? So you would think everything works, right? Process 2 wants to send information to process 1, 2 wants to send information B, and 1 wants to send information A, and it's just a simple information exchange. Well, unfortunately, this can very easily end up in a deadlock situation. Process 1 can just wait for information from B, while process 2 is also waiting for information from A, right? So in this case, you have a deadlock. And of course, this is a simple situation. In more complicated algorithms, it becomes very hard to figure out, and all the burden is on the programmer to figure out what situation happens when. There are some solutions, of course. I'm not saying MPI doesn't have solutions. There is, like, for example, MPI send receive that try to do something. But you get the gist of it, right? It becomes hard, and it becomes the responsibility of the programmer to figure out all of these details. So this would result in large overhead from communication mismanagement. You would waste your program time, your CPU cycles, basically waiting for something so that it doesn't block. You can try to overlap computation with non-blocking communication. That's one solution. Again, more complexity. Load imbalance becomes very possible. What happens to dead machines? As we said, when you have 100,000 machines, it's guaranteed every minute one of them is going to go down. what are you going to do with it? Well, you're going to do something. The programmer has to decide and has to program that in the program. So it's not impossible, but things start to look hard to code. And that's why you want something better. Now, something else happened as well in the last couple of years, or maybe say last decade, really. Web data sets started to become very large, right? So you started to have web graph data, web servers all around the internet, and information, really starting to expand in size. You have tens to hundreds of terabytes of information, and you really cannot data mine this sort of information on a single server, right? So what people started to do was to put regular, and the term is COTS, commercial off-the-shelf machines together as a cluster of commodity Linux nodes, put Linux as a free operating system on top, and just connect them with gigabit Ethernet interconnection networks. So putting these machines together wasn't that hard. At first, about 10, 15 years ago, people would call them Beowulf clusters, and then they just started to calling them just clusters. So putting them together is not that hard. How do you utilize this infrastructure? And that's the issue. Especially when you have regular commercial off-the-shelf machines that are not built to the high standards that used to be there in, say, supercomputers. Now you have your regular hard drive that you put in these machines. You have way more hardware failures. You really need to figure out a good way to handle that. Now the solution is to come up with a better abstract way of storing data on these machines and then pushing the computation to them. So what you do here is you use a distributed storage model to begin with, right? You have a cluster. Say each machine has 6 to 24 disks attached. We call each server sometimes a blade. And a whole bunch of blades, of course, are in a rack. What you do is when you want to store information, you divide up the information, and we'll talk about that, and store a piece of them, a piece of each information in different machines. Now, you have stored the information across all of the nodes in your cluster. How do you do the computation? What you don't want to do is to say, hey, I'm on machine A, go to machine B, grab the information, bring it back to machine A so that I can process it. That's never going to work because you are making your network a bottleneck. What you have to do instead in these sort of standardized cluster architectures is to push the computation to data, right? So what you do is you ask the machine that has the data piece to say, hey, you're storing the data and you have a CPU. Why don't you kindly do my process for me on the very same machine that has the data? The data on the disks is usually in these programming models read sequentially from beginning to end, and where there's a very good reason. Typically when you have hard drives are spinning, right? There's a notion of sequential access of the disk. If this is your hard drive head, the hard drive is spinning one direction, so you can read some data stored on a sector of the hard drive from beginning to the end. That basically, that physical reality you will see is implemented on the programming frameworks, so that now our frameworks adhere to the standards dictated to them by physical resources. Now, one thing that you want to make sure is that in these clusters that we're talking about, clusters of off-the-shelf machines, how would you handle failure? So in a cluster, as I mentioned, you have a whole bunch of blade servers. Each blade server has CPU, memory, and a bunch of disks. You have a number of these in one rack. They are usually connected to each other by a top-of-rack switch. Sometimes the network between these is connected through gigabit Ethernet, very commercial, off-the-shelf, cheap hardware. And then you have many times more than one rack, and they are connected through a two-level interconnection network. Now, what can happen is that sometimes a machine can go bad. So your programming framework has to be able to handle cases where one whole machine is out of commission. Sometimes a switch can go bad, as you can see here. And when a switch goes bad, what happens? A whole rack of machines get disconnected from the rest of the network. Your programming framework has to be able to handle this situation as well. So back to the question of storage. You really need a stable storage in the face of this unreliable hardware. Storage becomes a first-order problem. If nodes can fail, how can you store data persistently and make sure your data isn't corrupted? The answer is in distributed file systems, which is really the foundation of a lot of these big data technologies. What you can expect from a distributed file system is a global file namespace. What do I mean by that? I mean that the storage is distributed. A single machine only contains a little bit of the file system, right? But the file system abstraction provides you a global file namespace, right? So we can say, hey, I want file A. And the distributed file system knows how to grab the file from across all of these machines that store little bits of information. Sometimes even file A could be chunked up among multiple machines. But the distributed file system abstract takes care of that. An example of this is the Google GFS file system design and Hadoop HDFS file system, which is really based on the Google GFS design. And the HDFS file system is very common. It's what Hadoop is really built on top. The typical usage pattern that you have here are huge files. Again, remember, we're talking about big data. So a single file could be hundreds of gigabytes. In your usual day-to-day work on your laptop, your whole hard drive could be like 1 terabyte. Here we're talking about a single file being 1 terabyte, right? One communication pattern is that data is rarely updated in place, right? So you have a file. In a regular program, say you write a program in C, you can say, hey, open my file, seek to this certain location of file, do something, update the data, write that in that very same location of the file. Here in big data storage, we don't do that. Your data is rarely updated in place, and this assumption is really used in the design of the distributed file system. You can assume that reads and appends are common. So you want to read your data, do something, maybe append the results at the end of the file. You don't touch the file itself, but you can append some information to the end of it. So all of these assumptions that I talk about, especially about the storage, they all impact how MapReduce framework is going to shape. And in the next video, I will start looking into the MapReduce programming model itself, and you will see how a lot of these assumptions about the storage, stable storage, the failure models, impact the design of this programming framework. So first, we will talk about the programming model, right? So how to program this. And then once we have that, and we know now about this information, we will move on into the next lesson, which happens in the, after this, to see, OK, how would you build a framework that provides this programming model under this certain conditions. All right, so we've talked about the ideas behind why we need something like MapReduce, but let's see what MapReduce is. In this video, I'll talk about MapReduce, the abstract model of computation introduced by MapReduce. And in the next couple of videos, we will go through this example by example, figuring out really how to think in terms of MapReduce. So MapReduce is a programming model. The idea actually originally comes from functional languages such as Lisp. The important thing here is that many problems can be phrased using the abstraction provided by MapReduce. Once the programmer does this, once the programmer takes the problem of thinking in terms of MapReduce, which is not, at least doesn't come easy at first. So the benefits of MapReduce that it can provide you in return of you thinking in terms of MapReduce is that it becomes easy to distribute code. It hides the difficulty of writing parallel code, which, as I talked before, you have deadlocks that you have to think about, all sorts of communication mismanagement that you have to care. It hides all of those difficulty. It takes care of load balancing. It takes care of dead machines, provides reliability. It has actually a very nice retry and failure semantics. So when there's a failure, it automatically figures it out. It can do an automatic retry without corrupting the computation that has happened so far. But what is MapReduce? Let's actually delve in and talk about it. In a MapReduce programming framework, the programmer, that's you would write mainly two functions. One function, of course, is map, another is reduce. What does the map function do? Map function performs a certain computation, whatever you want, on individual values. This is the key point here. Map works on individual values in a data set and creates a new list of values. But this is the most important part. Your map function gets one data piece. You might have 10 petabytes of information. I don't care about that. Each data item, however large or small that is, that's what a map can work on. What does reduce function do? Reduce function combines the values created by maps. But to make it more broad, you provide a set of values to reduce, and it works on a set of values and can create new values, right? So what's the difference again? Map works on a single item, reduce works on a set of items. Map always happens first, reduce happens after that. Let's look at this example here. Let's say your computation here is square x. So what you really want to do, if you have x, you want to multiply it by itself and give it as output, right? And let's say you have a input data set, an input data set 1, 2, 3, 4, 5. You want to apply this function on all of these the items of the input data set. All you need to say is map this function square on my input. What it does, the framework, it starts going through the items in the input list. So it takes 1, applies it to this function, 1 by 1 becomes 1, produces the output 1. Then takes 2, provides it to this function, 2 multiplied by 2 is 4, produces 4 in the output list. So on and so forth, creates an output list. Now let's look at an example of reduce. Let's say the computation you want to do in a reduce function is sum. You want to take all the values in an input set, say your input set is an array, and what you want to calculate is the sum of all these values. So in this case, you would say reduce this set of 1, 2, 3, 4, 5, apply function sum. What it does, it goes and say, hey, 1 plus 2 plus 3 plus 4 plus 5 returns number 15. Let's make it a little bit more detailed now as well. When you're looking at the map function, what is really the input? As I said, map works on a single item. In the MapReduce world, pretty much in the whole big data world, really, now and the rest of the course, most of the times when we say one data item, we are really talking about a pair. You will always have key value pairs, and this is one input item. So your map function gets one key value pair, which are really individual items, but they're always come in pairs, and then does some computation on it. It creates a set of key value pairs as well. So the output is a list of keys and values. They can be different. So for example, your output, your input could be, I don't know, key 1 and value 1. This could be your input. And your output can be key 2, value 2, key 1, value 3, key 8, value 15, whatever. So your map function can do all of these. But remember, the input is only one item. Now, more importantly, notice that you only write the map function. You don't write the functionality that goes and reads the input data and gives you key values. That's done by the framework. So the framework does that, reads it, parses the input data, grabs a little bit of it, and just tells you, hey, map, this is one key value pair, do your processing, give me a list. We tend to call the output of map as intermediate values, intermediate pairs. Now let's look at reduce. What does reduce do? Reduce gets a list. Remember I said reduce works on a list. Here, you have one key and a set of values. So let's give an example. You can call your reduce function by saying, hey, my reduce input has key 1 and then a set of values, value 1, value 2, value 3, so on and so forth. All of these values have key 1, K1, as their key. Now, your reduce function can do whatever it wants. It can, again, create a list of output keys and intermediate values, just like the map. Right? Chances are your function, basically what it does is it combines all of these intermediate values for a particular key. But remember, it's for a particular key. So when you call reduce, the key here is one single item. Value here is a list of values that all have the same key. Typically, you would see in MapReduce programs that reduce typically creates one output item, but it doesn't need to. It can do more than that. The description that I gave you in the previous video about map function and reduce function was a little bit abstract. Now, in this one and the next couple, we will try to figure out really how this works by looking at a bunch of examples. So let's start by thinking about the word count problem. So what is a word count problem? Let's say you have a large file of words. Well, sometimes you have many files of each one, really big size. They're all text, so they have words in them. And each line of text has many single words. What we want to do here is write a MapReduce program that counts the number of times each distinct word appears in the whole file. right? So let's say, if this was your file, this slide was your file, you have, let's see, one occurrence of the word have, one occurrence of the word large, you have two occurrence of words, so on and so forth. So you want to actually create an output that shows like large, comma 1, words, comma 2, so on and so forth. So why don't you pause the video here for a second, think about this, and when we return, we will work on figuring out how this works. All right, so hopefully you've thought about it, and your solution probably looks something like this, but let's go on and see how we can solve this problem. So the map function that you can write here, you can have your input coming into your map. You can say my individual data item that I want to process on in my map function is a line of text. So key, for example, could be line number. In this very particular example, we don't use it. That's fine. So this is a good example. Sometimes you can just ignore one of your input arguments. You don't really need to use both key and value. Sometimes you can get a key value and just throw away the key or the value, or vice versa. It's up to you. You're writing the program, right? Now, in this case, value is the contents of the line. So what I can do is I can say, so this is a line of text, and I'm writing pseudocode here, of course. So I can say for each word W in values in the line, you can emit an intermediate key value pair. The key I use here is the word, and the value is 1. So here's another interesting thing. In MapReduce programming, your key can be anything you want. Well, basically, any object that is serializable, and a lot of them are there in the Hadoop framework. So you have serializable numbers, integers, doubles, whatnot. You have serializable strings. You have serializable regular objects, right? So basically, anything can be your key value, your data type. So OK, here what I do is I use the word as my key. Now, what happens once I do that? The framework, after it takes the input data, say this is the input data, all of it. It chops it up, passes each one to a map function, a separate map function 1, map function 2, map function 3. It calls map function for each of these. It will just listen and wait for map function to finish. When map function says emit, it will say, oh, good, I'll take over the value. So it gets a hold of the intermediate value pair and keeps it. Once all the map functions are done, all of them, all of these are done, it says, OK, now it's my turn. Before it starts running your reduce program, reduce function, it says, now it's my turn. It does some sort of processing, distributed processing, figures out in this space of intermediate key value pairs that were created by map, which ones had the same set of keys. So it actually does a grouping operation. And it says, OK, there were 5 different keys created by my map functions, for example, 5, 6, whatever. It says, hey, I had key 1, key 2, key 3, key 4, key 5. There were 18 values associated with key 1 across all of the maps. So map 1 could say, have key 1 and value 8, and map 5 could say, hey, key 1 and value 9, right? So the function says, hey, key 1 had a value coming from map 1 and a value coming from map 5. That's still fine. It groups all of these and creates those lists. So now your key 1 will have value 8 coming from map 1, value 9 coming from map 5, so on and so forth. Once the framework is done doing that, it says, OK, now it's your turn again. It starts calling reduce functions. Remember that I used plural term? So it instantiates a number of reduce function invocations across the cluster of machines. How many invocations would it use? In our example, we had 5 different keys created by the user. So it will say, I will instantiate 5 different invocations of function reduce. For function 1, I will pass key 1 and this list of values. And function 2, reduce function 2, key 2 and its own associated list of values, and so on and so forth. OK, so now what I do in my reduce function for my word count problem, I get 1 key and a list of values, right? So let's say in map, what did I use for keys? I used a word. So here, my key would be a word, 1 word. Values, what did I use in my map? Anytime I would see a word, I would use value 1, right? So here, I would have a list of 1, 1, 1, 1. For each time that word was appearing in the line, I would see 1, 1, 1, number 1 in this list. All right, so now it's easy, right? I would just say, hey, go over this list of values and add them all together. The result is the number of times that specific word, this word, passed to me by key, was repeated in the input data. And now we can say emit, again, pass it back to the framework. Of course, emit here is pseudocode. In real Hadoop, it's a different thing, I'll tell you. Use key as the word as the key, and the result value that I calculated as the result. Let's see how this really works in action. So let's say your file was this guy. It had 3 lines of code. When your map function would go through these lines, it would start to see separate the words and create intermediate key value pairs of word and number 1. So it would see, hey, I see word C. Let's create an intermediate key value pair, C, comma, 1, Bob, comma, 1, run, comma, 1, right? So on and so forth. And then the framework would put them together and would say, hey, let's call reduce with 1 value, run, and C gets 2 of these. OK, so this was a simple example. It's almost a classic example. In the next video, we will look at 2 more detailed examples. One would be how to estimate the value of number pi, and the second exercise would be an image processing algorithm. Let's look at some more detailed examples of MapReduce in this video. We start by pi estimation. So we want to estimate the value of pi. And then we'll move on to an image processing algorithm. So in our first example, what we want to do is use what is called a Monte Carlo simulation method to estimate the value of number pi. The idea is actually very simple. It's based on throwing darts at a board, right? So let's say you want to estimate the value of pi. You can draw this board. You can, as you see on the right-hand side, you have a square and you have a circle right in there. The radius of the circle is 1. It's just a simple shape. We know that the area of circle, in this case, is PR squared. R is equal to 1. So the circle area is pi. The square area is 4, right? Of course, you have 2 multiplied by 2. Square area is 4. So if you want to calculate the value of pi, you could basically divide the area of the circle, denoted here as value c, by the square area, denoted as s, multiplied by 4. That gives you the value of pi. How can we do that? How can we estimate pi given that you already know the value of c and value of s? You already know the areas of the circle and area of the square, right? So we already know how to do that. The only question remaining here is how can you find the circle area and the square area? And now that's why we start throwing darts at it, right? So here's easy. You assume that you have 1,000,000 darts and you have this dartboard, right? You start throwing darts towards this dartboard, and let's assume you're really good. You will never miss the board, right? So your darts will start landing here, right? And assume that you have 1,000,000 of these. You can imagine after throwing 1,000,000 of these, the whole area will be filled with darts, right? All you need to do is throw 1,000,000 darts and then count how many of them landed inside the circle and how many you were totally throwing. The ones that didn't land inside the circle obviously landed outside the circle, which is, outside. So in other words, to find the values for c and s here in this formula, you just need to have a count of the number of darts that landed inside the circle and the total number that you threw out. Once you have those values, you can compute the ratio of the darts landed within the square versus the darts landed within the circle, and evaluate whether a particular dart landed within a circle or not. All right, so at this point, I would like to invite you to pause the video for a bit, think about it, and then once you're done, we can move to the answer. All right, so you thought about it. Hopefully, your solution will look similar to mine. But let's look at this solution for pi estimation. So the MapR function in this case, the way I've written it, is that the MapR itself generates points, which really is a pair of x and y, in a unit square. So you can have values between -1 and +1 created for x and y. So the map function creates these as random numbers, and then counts the points that are inside the circle. And to find whether a certain point is inside a circle, it's pretty easy. All you need to do is to find square root of x squared plus y squared. If it's less than value 1, that would indicate that the point is within a circle. If it's not, it's outside, right? So once you do this test in your MapR, all you need to do is emit an intermediate value pair saying that inside value 1, if that's the case. If it's, and then aside from this, you can also emit something else as total 1, right? That means that I created 1 dot, so I can keep a count on it, and it was also inside. If this condition does not hold, you just emit this total and 1 intermediate value. You do not create inside and 1, which says, hey, I threw a dart, but it was not inside. Fine. And in your reducer, you just accumulate the points. You find out the number that were inside. The other reducer finds the number that were in total. You can run this for 1 billion numbers on 10 machines, 100 machines, whatever, and calculate pi to any number of accuracy that you want. The more random numbers that you create, the better accuracy your pi value will have. So to calculate the pi, all you need to do is calculate the ratio of number of darts inside divided by number total. All right, let's move on to our other example here. We're talking about an image processing algorithm that is typically called image smoothing. If you have any experience with image processing applications like Photoshop or things like that, you know that there is a sharpen function and then there is a smudging function, right? You can smooth an image by basically reducing the sharpness, right? Now, one algorithm that I'm showing here uses what is called a sliding mask, right? And using this mask, you take this mask over all your picture and replace the values of each pixel. So let's look at this, how it works. The mask that you have takes 9 pixels, right? As you can see, there are 9 pixels here. It considers 9 pixels. It averages the values of all these 9 pixels and then replaces the value of the center pixel with that average pixel of every pixel around it, and itself, of course, included. So you can imagine an algorithm would start by, a serial algorithm would start by going through the first, the first 9 pixels, and then it would move one to the right, then it would move one to the right, and then you can kind of scan the picture line by line, pixel by pixel, and once you're done, this algorithm is finished. Okay, let's implement this algorithm with MapReduce, right? So let's assume your image is really large, 100,000 pixels by 100,000 pixels, or maybe even more, 1 million pixels by 1 million pixels, which is not that uncommon, especially in astronomy, when you have telescopes that scan the sky and they do create really, really high detailed values. Now, of course, this is an example. In astronomy, I wouldn't know why you would want to smooth an image. You would usually want to sharpen it, but this is just a simple example. To make it a little bit easier for you to think, in a serial implementation, you can assume that, hey, if I apply my mask first here, then move on to the next one, the new values are taking effect. Let's ignore that. Let's say that you want to process all the pixels in this image in parallel using one certain snapshot, and then you want to create a new image with new values. So forget about the dependencies of the algorithm, if it's scanning or not. All right, so this is a good time to pause the video and think about this algorithm a little bit. Once we come back, we'll talk about the solution. The way I solve this problem is by assuming that the input key is a pair of x and y coordinates, and the value to the map is a triple pair of red, green, and blue values. That's very common in image storing formats. You usually store a red, green, and blue value for each pixel. So that's what we have, right? Now, remember, this is what it makes it a little bit hard. Let me go back to the previous slide and talk about this in this picture. You might have actually started to think in terms of how can I process 9 pixels, right? But remember, what did I say? A map function gets only one input value. in a map function, you do not have access to 9 pixels. And it becomes very, very hard, very possibly impossible, to trick the system into somehow getting the values of neighboring pixels to you in the maps. So don't go after it. What you have in your map function is 1 pixel and 1 pixel only. You have to play tricks to get your algorithm working, but map is what it is. So what I do instead here is, instead of looking at my data flow, let me show here again, of values of different pixels coming in, I'll actually start thinking reverse. Let me wipe this out. I'll think in reverse. I'll actually move information out of my pixel into the other neighboring places, right? So what I do in my map is I emit 9 points. What do I have? I'm given x and y. Now I can create x minus 1 and y minus 1. That's information I have. So x minus 1, y minus 1. Emit with the same RGB values. X and y minus 1 RGB values. X plus 1, y minus 1 RGB values. So on and so forth. So now then you have, again, x minus 1, x minus 1 and y. X and y. X plus 1 and y. So you emit 9 different values. What have I done here? What I've done is basically I send the information in the intermediate key value space so that the framework can do its job. The framework can pair the 9 pixels in the right place. Now, who's doing the real computation that I want? Remember, the real computation is bringing the information in. The guy that does this is Reduce, right? Framework finds all the intermediate key value pairs that have the input key as x plus y, not x comma y. And what it happens that it goes and finds all these values that were emitted from all the neighboring pixels that come to this pixel for Reduce. And inside it computes the averages of those 9 pixels. So this is actually a good example. You don't need to do your processing always in map. I mean, that's kind of like a tendency that programmers that are new to MapReduce usually think. I should do most of my work in map. Reduce just wraps up things, right? Not necessarily. A lot of times, and we will see actually in our next example as well, map might do less work than Reduce. So to wrap up this example, once your Reduce function computes the average RGB values for all the pixels, it just emits using its given key, x and y, and the value being the average RGB that it just computed. The result that will go in a file will have the smoothed, the average value inside the output file. In this video, we will look at a rather famous algorithm called the PageRank algorithm. This algorithm was implemented by Google to rank any type of basically recursive set of documents using something similar to now what we call MapReduce. Now, of course, remember, this was developed before Hadoop, before MapReduce. Basically, MapReduce came out of this work, but we'll see how this works in the upcoming slides. So it was initially developed at the Stanford University by basically Google founders, Larry Page and Sergey Brin, in '95. And in '98, it led to a functional prototype named Google. Now everybody knows what Google is. Its definition is this, and I'll go through it, although in the next slide, I'll show you graphically what this really means. So PageRank value for a page U. Say, assume you have a graph of pages. One is U, let's call one page U, another page V, and million other pages. So this page rank value, we just want to give it a number to page U, number to page V. If page U's number is larger than page V, it means page U is more important, which means if you search for something, chances of page U showing up in the results is higher than page V. All right. So the page rank value for a page U is really dependent on the page rank values of each of the pages, now let's call those V, out of a set. Which set are we talking about? BU. This is a set of all the pages linking to page U. So let's say within the code, within the HTML code of page V, there is a link to U. And then there is another page on the internet that also links to U, right? Let's say there are only these two pages in the whole internet that link to you, okay? So we call this set B of U, which is, set of pages linking to page U. To find the page rank value of U, we really need to find the page rank values of these other pages first. And then add these values and divide them by the number of links going out from page B. Okay, this sounds a little bit complicated. Let's actually really look at it, what it really means. I'm going to show you how this works in this animation, assuming there are two phases to the algorithm. The first phase is called propagation. So let's look at this page, this diagram here. We have a set of web pages. If a web page is linking to another page, it's being shown by a link from page A to page B. Each of the pages has a certain value. Let's say, for example, for this web page, its page rank value is number 8 at a certain point of time during the algorithm's run. So this guy is 8, this guy is 2. In the first phase of the page rank algorithm, that we can call the propagation phase, look at the animation happening. The value of the page rank, in this case, for this page, which is 8, the value of this page gets divided by the number of links going out of it. In this case, 2 links are going out of this page. So this value gets divided by 8. And the 8 is divided by 2, resulting in value 4. And this value 4 is assigned to each of these edges, each of these links that go out of that page. That's all propagation phase does. Let's look at this again in the animation. This node gets divided by 2. The result is 4. The number 4 is assigned to the outgoing edges. Now let's move on to the next phase. The next phase is called aggregation phase. In the aggregation phase, what you want to do is look at all the incoming links into a page, add all of their values together, and assign them as the new value of a page. So let's say in this step of the algorithm, the page rank value of this node was number 6, for whatever reason, was number 6. Now that we have computed new values for these 2 edges, that might change. So it considers all the links that go into that certain node. The values are now 1, 4, and 2. In aggregation phase, we add them up together and give a new value to that node. So instead of 6, now it has value 7. This is an iterative algorithm. We keep running phase 1, phase 2, phase 1, phase 2, phase 1, phase 2. How long do you do that? Until there is no more change to the values. Or typically when you've run 100 iterations and you're saying, OK, fine, I'm good. OK, let's start thinking about how we can implement these two phases as two different MapReduce algorithms. Of course, maybe you're really figuring you can figure out one way of doing all of these phases in one MapReduce, maybe. Typically, these are done in two different sets of one MapReduce for propagation and one MapReduce for aggregation. All right. Now, let's assume your input is a pool of objects, right? So objects can be whether an edge or a vertex, right? So a page or a link are both objects. And an object can say, if it's a vertex object, what you can assume is that it has a URL. That's the name of the page. And a page rank value. If it's an edge or a link, you can assume that it has a beginning URL, ending URL. So beginning, ending, and a page rank value for the link. OK, so let's pause the video at this moment, and you can think about this. When we come back, we will look at the solution. All right, so the first phase of the algorithm, propagation. How do we do this? The map function here, what it does is that it receives an object. So all the objects are read by the framework. Each object is passed to a map function invocation. Within the function, what we do is first we check if the object is a vertex or whether it's an edge. If it's a vertex, all I do is emit a key value pair, set the key to be the string of URL of the vertex. That's the web page's URL. And the value, the whole object itself. I can do that. I can send the whole value, the whole object, if it's serializable, which for those of you who are good with Java, if it basically implements the serializable interface provided by Hadoop. You can just do that. Now, if the object is an edge, what I emit here as intermediate key value pair is the source URL or beginning URL, and the value being the object itself. So similar to our previous example of image processing, here again, map doesn't do much. Map just sets the stage for reduce function to do its real processing. It just makes sure that the reduce receives the proper set of objects to be able to do something. And if you had trouble figuring this out, let me go back to the previous slide. And here's the hint. Remember, what do you need to do for the propagation phase? You need one page and all the links going out of it. So that's the keyword. Something and something. You need more than one thing. So that's your hint. It cannot be done in map. It has to be done in reduce, right? What about the aggregation phase, this phase 2? Again, you need a page and all the incoming links to it. Again, there's an and, so you cannot do this function in map either. It has to be done in the reduce. OK, let's move back forward. OK, so in the map function, you send, if it's a vertex, you send the object itself out with the URL as the key. If it's an edge, you send the object with the source URL. Within the reduce, what will you receive? The framework will group all the intermediate key value pairs by key. Our keys are URLs. So when you get here, the input would be one web page that has a URL, and all the edges, all the links that had that URL as their source. So all the outgoing links of a page plus the page are going to the reduce. Now that you have all you need, from here it gets really easy, right? So you just find the number of edge objects. That's the number of outgoing links. You read the PageRank value of the vertex object, divide it by the number of outgoing. That becomes your new value. You assign that new value that you just computed to the PageRank of edges. Let me quickly go back to the previous slide. Remember that in the first phase, once you compute the new value, you assign them to the edges, right? Okay. So you just assign this value to edges and emit them out. They will go into the file system, HDFS file system, whatever. Moving on to the next phase, the aggregation phase. Again, the map is very similar, right? If an object coming to a map is a vertex, you emit a key value pair, key being the URL, the value being the object itself. If the object is an edge object, is a link object, the key value that you emit, key again is a URL, but this time you use the destination URL, right? And just the value, you just emit the object itself. Now this time, what we will receive in the reduce is one web page with that URL and all the links that had that URL as their destination. In other words, all the incoming links to that page. Okay. Now again, in reduce, we're happy. We have all the objects that we need to play with. So you just add the PageRank value of all the incoming links together and assign that to as the new value of that page. And you're done. Basically, keep calling these two MapReduces one after another, and you have your MapReduce computation. Now here's an anecdote. Basically, this algorithm was implemented in a distributed way, exactly like this, in a project called Notch. Notch became Apache Notch. And then people thought about it and they said, oh, you know what? This way of thinking about problems, this way of solving a problem in a distributed way is pretty cool. Let's get out the gist of it, the part that executes a map and reduce, and let's call it Hadoop. So let's wrap up our discussion on MapReduce. What we saw was a very general, interesting programming abstraction that allows you to easily write programs that run on many, many CPUs. In the MapReduce abstraction, basically the communication management is completely done for you by the framework. So it's effectively gone. You don't need to worry about that at all. I/O scheduling is also done for us. So as you remember throughout this video, we never read data from the disk or write back to the disk. We just hand it to the framework and it will take care of it. The framework provides for fault tolerance. It provides for very nice monitoring of what's happening in the machines. So if there's a machine failure, if there are machines that are just suddenly acting slow, these are all handled by the framework. It becomes much easier to design and program your algorithm that runs on tens or thousands of machines. What you can do is you can also cascade a couple of different MapReduce algorithms one after another. As we saw in our PageRank example, you can have one job running after another MapReduce job running after another MapReduce job, and that's totally feasible and simple. Now, these are all advantages. What about some disadvantages? It restricts the set of problems that you can attack, right? It might be hard to express the problem in the MapReduce abstraction. As you remember throughout this video, this lesson really. We talked about multiple examples. And what we learned is that you really have to start thinking in terms of maps and reduces. Now, not every algorithm is prone to that. Sometimes you have algorithms that really have different communication patterns, and it cannot be done that way. So that's one shortcoming. Really, data parallelism is the key here. If you have data parallelism, that means you can, in parallel, process different pieces of input data. That problem might be a good fit for MapReduce. Not all problems have data parallelism. That's one of the shortcomings. So MapReduce is a proven useful abstract. It's being used in industry everywhere. If you look at the trends, you'll see that basically most of the programming languages for the last decade, their popularity has either remained constant or, like, Java, C, whatever, goes slightly down. Hadoop exponentially increasing, and still the trends show that there's lots of interest in Hadoop. Greatly simplifies large-scale computation based on functional programming paradigms, but now it's much simpler to apply that mentality to large data sets. And basically, it lets you focus on the problem and let the middleware and framework handle all the messy details.
Transactions have been a basis for much computing, especially in parallel systems, for a while. So revisiting transactions and talking about consistency that isn't perfect is perhaps a little strange. But the reason for doing it is cloud computing nowadays actually really does depend upon scalable solutions, and those scalable solutions make transactions sometimes very difficult to implement. So we're going to be talking about eventual consistency, a form of consistency that works very well for large-scale computing, but overcomes some of the difficulties that we get with transactions. Why is consistency just such a big deal? Our model for computing is state-based, Turing machine, step-by-step, transaction-oriented, but that's on a single machine. Now we've got machines that have multi-cores, that have lots and lots of parallelism within them, and then we replicate that on multiple machines, say 10,000 machines. And so there's a question about how do you achieve it. If you want to get consistency between that sort of scale of machines, it can be quite slow because of the messages needed to actually conduct a transaction. So the natural feeling is, well, is it really necessary? Can one make do if, for example, the systems will never get too much out of step, but eventually will reach a consistent state? Could that not be used instead of a transaction? Can we design systems to eventually reach consistency and not have to worry about putting transactions into the cloud? A good issue is just, where would this apply? Which parts of the cloud computing? Do we have to apply that to file servers? Do we have to do that to scheduling? Whereabouts do we need to worry about this? As I said, there's lots of existing models, and to list those, ACID is the classic sort of transactional type of consistency. BASE is a way of programming systems to make it behave as consistently as possible. Paxos is a distributed protocol for achieving eventual consistency. It's not sure how long it will take, but eventually Paxos will allow you to decide what is a consistent view of the state of the system, and it uses a protocol to do that. Paxos is the basis for a whole ream of different solutions which are now in use in big cloud solutions, because what it allows you to do is have parallel systems. It allows you lots of asynchronous updating and so on, but it keeps everything consistent. The protocols within Paxos are organized to maintain an eventual consistency in the way that they operate. How are components in the cloud built using these solutions? What are the practical issues on building consensus, consistency inside systems? Eric Brewer made a great impact on the world by challenging some of the issues about consistency in big data systems. What he queried was, well, can you achieve consistency? Can you achieve that at the same time as availability and partition tolerance? If you want consistency, can you make it so that it's fast, that you achieve consistency quickly? Because otherwise, while it's achieving consistency, you don't have the values available, perhaps, to do sort of things that you would like to do. And then partition, as you're trying to achieve consistency, is your network partitioned? Is it broken so that there are two sets of systems performing operations on data and they can't be kept consistent with each other? So this is a big problem. Data centers need to be very responsive. They need to have, they need to be able to cope with transient faults, making it hard to reach some service. You still need to be able to get the data. They can use cached data to respond faster if the cached entity can't be validated, but it might be stale. How exactly will these data centers operate? And the notion is, well, you could weaken consistency for faster response. Say you use cached values, provided you don't do anything wrong. So if you're sort of adding things to people's accounts, say money-wise, it might be okay to delay adding some money to an account. What it would be obviously wrong to add it to the wrong account or let a deficit occur before adding something to the account. That would cause a problem in the whole system. So as long as you manage to get some sort of weak consistency in the system, you can use it. But there's always the question, you want to avoid some conditions, and those would be, that's what constitutes the meaning of weak consistency, that you want to avoid those particular conditions. So Peter Deutsch sort of wrote down some of the assumptions that you do have in large cloud, large distributed systems, that the network is reliable, that latency is pretty much zero, which of course it's not. The bandwidth is infinite, and of course it's not, because of our networking uses wires and they're restricted by the speed of light. And not only that, but the bandwidth is often shared between lots of people, so that bandwidth is more restricted. The networking is secure, that the topologies don't change, and of course failures do change policies, and so you do need to, well, you do need to worry about topology. That you have one administrator, you don't have two administrators deciding what to do and having a conflict. That the transportation cost is next to nothing, but again, with bottlenecks and so on, transportation cost could be challenged there. And then the networking is homogeneous, that everything works in the same way at roughly the same speeds and has roughly the same properties. If you make those type of assumptions, because, well, you see a working system, it leads to a number of fallacies, and those fallacies can lead you to basically make mistakes in implementing the system. So if you have unbounded traffic, for example, then you can actually add to the number of dropped packets, the number of wasted or the amount of wasted bandwidth to the network. You can increase the latency, you can increase packet loss, and that will greatly affect your applications. Next, the sort of network security, believing everything works well and is all sort of contained, that allows malicious users to perhaps challenge some of the security measures you've got, adapt to what's there, and bring your system down because you didn't expect the system to behave in a particular way. When you've got multiple administrators, they may not necessarily agree. They may have conflicting policies. They may want to compete over bandwidth or something. So you have problems with sort of multiple authorities controlling the system. When you're building and maintaining a network or a subnetwork, there can be large hidden costs, such as copying data in and out of memory and so on. So understanding about that is important. And then there's bandwidth limits on part of the traffic senders, creating bottlenecks and over frequency multiplex media, bringing lots of data into one particular server or something can cause bottlenecks and exceed queues and create huge long queues that add to latency. All of these things can challenge those 4 attributes that you would like out of a system. So Brewer's conjecture, and this was stated very, very informally as the CAP theorem, but was later shown to have some sort of relevance in theory, was introduced. It's known as Brewer's theorem, and it states that if you have a distributed system, it's impossible to provide all of the 3 of the following guarantees. Getting consistency, as in the sort of notion of transactions, all the nodes see the same data at the same time. Making things highly available, a guarantee that every request gets all of the every request receives a response about whether it's successful or failed, and partition tolerance, if it breaks in 2, that you can survive that sort of condition. And as a consequence, what we've introduced are components in big data systems, in cloud systems, in big data centers to overcome these problems associated with Brewer's conjecture, and they do that by implementing eventual consistency. In the next slides, we'll talk about how that's done. So in this lecture, we're going to look at eventual consistency and why it's such a good thing inside a big cloud system. We sort of dealt with some of the higher level views in the previous lecture. In this lecture, let's talk about actually sort of how the rubber meets the road in a cloud system. We'll also look at what some of the pioneers in cloud computing have to say about eventual consistency. System that has these attributes, that we have consistency, we have availability, and we have a theorem that says only 2 of those is actually viable. Looking at some of the definitions there, what you're saying is that in order to get the computation done, it's got to sort of match in a state machine, a Turing machine or whatever. There exists some total order for all operations so that they look as if they were completed in a single instant, that every request that's coming in by a non-failing node has to return some sort of response, and that no set of failures less than sort of complete destruction of the network is going to prevent you from actually responding incorrectly. That's what we would like to have in our data center. We're going to sort of go through and see the Brewer's conjecture here that you can only have 2 of these. You can have consistency or availability, or consistency and partition fault tolerance, or partition tolerance and availability. You can't have all 3 at once. What we're going to do is to follow a sort of intuitive argument about this, and then see that there are sort of orders where you can have eventual consistency providing a lot of these features, and that is actually the way that cloud providers think about offering services these days. If you go back to basics and to sort of 101 in computer systems, what you'll find is that there are actually a number of theorems, useful theorems about knowing what the state of an asynchronous system is. And one of the more sort of well-known results is perhaps that it's impossible in an asynchronous model to implement a read-write data object that guarantees both availability and atomic consistency. And by asynchronous, what we're referring to is that it doesn't have a clock, that it's sending messages from one place to another, say in the network, and the actual packets that traverse the network or the communications that they're not acknowledged, they are assumed to actually have crossed the network and work. And of course you could actually lose some of those, or they could be delayed, causing you problems about how do you know whether results have been produced for something, or how do you know that all the values in all the systems have been updated. So in all fair executions, including ones in which messages are lost, you have a difficulty with asynchronous systems. The decisions made with local computations or messages can't sort of incorporate what happened to all of the rest of the systems involved in that asynchronism. An observation you can make, which sort of underlies all this, is that really if you have a message and it's asynchronous, you have no idea whether it's just lost or arbitrarily delayed. Now remember, we were talking about partitions as part of Brewer's. So if the network is broken, if it's separated into two pieces or whatever, actually messages may be lost as they could try and traverse between the two disconnected parts of the system. So yeah, you can't tell that from just sort of arbitrary delays, and you get arbitrary delays because the messages aren't clocked, they're asynchronous. So that's really sort of the underlying cause here. And you can picture that in the way of, here's a computer, it's attached, well, here's a display at least, and it's attached to three machines, three PCs, looking at three different values, V1, V0, V0. If your network is broken, there's no way to know that these values in the system are consistent across the systems. In this case, V1 and V0 are different. If we partition it, choosing how we sort of partition the network, we could have, well, the first two processors having V1, the other processor having V0, and there's actually no way that you can observe that the value in that broken part of the partition is the wrong value. So this is really sort of the problem. In partially asynchronous or partially synchronous models, each node in the network is given a clock, and all clocks increase at the same rate. So we can use clocks as timers to know whether they receive the message. And this gives us some advantage and is the sort of basis for a number of different algorithms. Again, it's impossible to know in the partially synchronous network model to implement a read-write object that guarantees the following properties: availability and atomic consistency in every execution that you get. Again, it's because some of the messaging has this arbitrariness about it. So partially synchronous is okay. There are stronger sort of concerns you can say about it, but it's still not ideal. If you look at what's happening in those partially synchronous algorithms, then if you say, well, I'm prepared to wait and see what happens inside those systems, you can get a better feeling for getting all of those three properties, Brewer's properties, to actually sort of operate together. So there are partially synchronous algorithms that will return atomic data when all the messages in an execution are delivered, for example. So if all the messages actually get across, then you can say something. And it'll only return inconsistent data if messages are lost. And if messages are lost, you could be informed about the fact that they are lost. So an example would be a centralized server to receive all the messages and have that server respond to all the messages from all the nodes. And then using timeouts, you could prompt if you don't get all of the messages through. If there's in order to predict completion of a successful message transfer, you can set your timeout and see what happens. If you don't get that, then there might be a problem with atomic consistency, but if you know that, then you can accommodate that information, perhaps. So we get to a notion of T-connected consistency. If there are no partitions, then the system's consistent. And if you get a partition, then the system can return some data. And it could be stale data. It could be data that you know isn't up to date necessarily, but nevertheless, you know something about the data that's there. And once the partition heals, you have the opportunity that the messages can update the system, and there will be eventually reaching consistency. The only property you need to know is that the message eventually can get through because the partition heals. So this notion of eventual consistency takes that and runs with that idea that if you're exchanging the messages, then okay, if it's asynchronous, you couldn't do anything about it. But if it's partially consistent, then what you can do is to take account of all these states and reason about whether you've received all the messages that you needed to. And so you know when it actually has all worked, that your state is actually consistent. And in between times, you know that there's some problems that need healing. Given a time window, an observation that things can heal, you can have, it can vary from people running along or automatic sort of systems doing the healing. You can ask, well, how much consistency is really needed if you're building a cloud implementation to provide service? And depending upon what the service is, you can come up with different solutions. So if you're doing YouTube videos, what's the consistency issue? All right, people are uploading those videos, but they don't know how long that's going to take, and they're probably prepared to wait until it's uploaded. If you're downloading videos, you're prepared to wait for a little while to get the videos. And so there's time for healing to occur in terms of what happens in the system. If you're buying from Amazon and there's a number of units available and it's sort of counted, well, you buy something, as long as you don't buy something that doesn't exist, you're probably happy if those counters aren't actually exactly accurate. As long as you don't go below zero and sold something, have to pay money for non-existent entity, that doesn't really matter. So in terms of Amazon then, if you can have eventual consistency and avoid the case that you don't have any items to sell, you're not too badly off. So can you come up with a general policy for knowing how much consistency you need for a given type of service that you're providing? And can you use that effectively? So the client will always see a snapshot of the database that's, if that's internally consistent and might be valid, then can you proceed doing your sales or service or whatever it is? Internally, the database might be generally consistent, but the states the client saw aren't tracked and might become invalidated by update, but does that matter? Inconsistency can be tolerated because it yields such sort of big speed ups, although clients might see the wrong results. So if I'm buying from Amazon and I happen to see 250 units for sale and I buy 3, and then it's not updated immediately, well, or even if the 250 was wrong, as long as it's got 3 units, I don't care terribly much about that inconsistency. So if we look at an example, you've got caching, say replicated data, and then you've got some core memory that holds these replicates, the original data. You can read cache data quite happily as long as nothing happens that would invalidate it. If you actually want to sort of update cache data, you can do that, provided it doesn't interfere with the person reading it. So if I sort of write to location 23 and the other person looking at it reads from location 75, does that really matter? As long as those two locations aren't connected by some sort of dependency, some sort of invariance, things can go on in parallel and everybody's going to be happy. And so I can be buying things from Amazon. People can be looking to see what's for sale on Amazon. As long as those are consistent from a sort of client point of view, we're all fine. Here you see this transaction. It's updating the core, writes values, and then it would update the cached replica, and that will be fine. There isn't really any sort of objection to having this sort of out of this notion of eventual consistency being in operation, as long as it doesn't interfere with what the client wants. So how much can you actually support with this? What does it allow you to do? And the answer is, well, it depends. If you have a lot of contention over sharing of data, then a little bit of inconsistency, if you can survive it, if you build systems that are eventual consistency and the clients are happy with the way that works, that can buy you a lot of sales, a lot of services. It all depends. So the root challenge is to understand just how many updates occur, how often those updates conflict between concurrent reads, concurrent updates. In most cloud applications, the contention is rare because there's a huge amount of data and a huge number of people, a huge amount of clients, huge amount of services, in which case relaxed consistency will work just fine. You really have a sort of case where you can get things to run much faster with that notion of relaxed consistency. So is consistency in clouds dead? Well, it depends, because there are things for which the clouds would have to be consistent. There are other things which aren't. So you really need to look at a very sort of deep analysis of what is going on in that system. eBay, for example, lives, if you like, by trying to make sure that things don't interfere with each other, and they try and separate everything out. They try and live with eventual consistency. They partition everything. They use asynchrony everywhere. By partitioning it, they give different sort of sets of data, and so there's less interference from one customer to another. They use the synchrony everywhere to make things really fast. They automate everything, so the updates are very quick if they can be done. They try to remember if everything fails. They try to remember what happened, and they embrace inconsistency, even to the extent that, if they make a mistake, what they would do is to go and tell a customer that, okay, we made a mistake, you can have something for free, or you can have so much off the next product. They make allowances for their inconsistency, and therefore have a great sort of sales model and service system. Amazon, Werner Vogels is CTO at Amazon, and he built their shopping cart service. The old one, the original one built for Amazon, had strong consistency for replicated data. Dynamo was built, it uses a distributed hash table, has a very weak consistency. It eventually converges so that if you leave it long enough, the data in the database will actually reflect what's in Amazon's inventory. But if you go to it at any particular time, it might be a little bit out of date. Weakens consistency, but it has allowed Amazon to make a huge amount of money. Speed matters more than correctness. That's the Werner sort of philosophy of the way that Amazon works. And to a large extent, commercial systems can accommodate a little bit of incorrectness. Inconsistency does bring risks, as we said. Some of those are negligible. Some of those can be accommodated by giving the clients a benefit of a free service or whatever. Others cause real difficulties. So inconsistencies can cause bugs, and if you do it too often, and if the inconsistencies are too bad, your clients are going to lose faith in what the servers are telling them. So there is going to be a trade-off. So you have a notion of what is the weak or best effort consistency, and that depends really on, well, what are the things that could go wrong? What are the risks involved with getting an inconsistent model? What you see often enough is that if you have a strong security in your system, like you're moving gold bars or something and you want your gold bars not to get lost, then you're going to guarantee consistency. And an example of that would be if you have a medical electronic health record system or a bank that uses weak consistency for better scalability, it might have clients that start getting upset with those accounts. If, for example, you get charged for an overdraft when there wasn't an overdraft, that would be a real sort of failure of the bank to provide its service. The properties we might want, that updates occur in the agreed order. So, if somebody wants to sell something, somebody wants to buy something, that all that follows in a logical order. The durability, that once you've bid for something, it won't be forgotten. That you've actually, once PayPal has told you you've bought this thing, it's not going to then turn around and sell it to somebody who's got more money. That it's real-time responsive, that it's very fast, that you don't have to wait too long, that the security permits authorized actions by authenticated parties and doesn't allow arbitrary people to go in and make a mess of the system, that it doesn't disclose personal data, that you have some fault tolerance, so if systems fail, they can recover, and that you have coordination. Actions don't interfere, the actual actions don't interfere with one another. So those are the sort of properties we might want in building it, and then we can perhaps survive with some sort of eventual consistency. So here what you see is we're challenging the notion. You have a state machine or a Turing machine or whatever you want to think of as a computer. What we're arguing is it doesn't have to be exactly consistent after a computation. As all that, it can have some sort of delays, as long as it eventually gets to what everybody would believe is a consistent state that they all be happy with. We have a decent system upon which we can build services. But you have to know what is it being used for and why it's being used in order to employ that idea of eventual consistency. The CAP theorem is a warning that strong properties can easily lead to slow services. Weak properties are often all we need to have a successful strategy that both give us a good solution, require less effort, and can increase availability. What we see with cloud services is different uses of consistency. And there's some listed here because of the variety of ways they tackle consistency. One of the very popular approaches to providing distributed computing is to provide a cache and to make that memory-based so that it's very fast, and that's called memcached. But it doesn't have any special guarantees from the point of view of consistency. It's what you guess what you actually sees. Google's file system, on the other hand, uses something called locking to guarantee consistency. So whenever you do an update, everything's locked until the update occurs, and then the locks are released and you can see the updated value. Google's Big Table has shared key values, and it has consistency problems with the keys and the values when you have it spread across multiple machines. Dynamo, Amazon shopping cart, uses eventual consistency, and that's a topic we're going to be exploring in a little while. But essentially what eventual consistency doing is saying that you cache everything, and the updates to it don't really matter as long as you have that interval, you're working within a window of time when you know the updates will be made and you can look at the real values. Databases, very often they're snapshot based. They have mirroring in a fancy form of ACID guarantee, that ACID being atomic transactions, you update it and everybody sees the update. MapReduce, which you've been learning about, uses a functional style of computing model, and that offers a very strong guarantee of consistency. Basically, you can't see intermediate values. What you get is the results from the map phase, the results from the reduce phase, and you can't see in between values. So you either see the results or you don't. MapReduce that's very effective and easy way to program. Doesn't allow you to do everything that you would like to do though. Zookeeper is a particular form of device that actually provides consistency across a distributed system. It's an implementation of an algorithm that we will learn about in a second. The Yahoo file system actually uses Zookeeper to maintain its properties and make sure it's consistent. Peanuts is a Yahoo system, distributed database with sharded data, spectrum of consistency options. So you can say, well, I want it consistent up to such an amount. And Chubby is a locking service. Again, that's where you would lock the value, lock the database, change values, unlock the database. Chubby itself is a system, and that's providing very strong guarantees. So what you see here is cloud services introduce a whole spectrum of different ways to provide consistency, and hence justifies us looking at this topic for a bit. So let's assume we do need consistency. Let's assume that we can work so long, but then what we need is actually to know all the values so that we can compute what we're needing to do. If we want consistent computation, we use consistent transactions. There's a very easy way, which is to use ACID. There's also a very, you might say, back of the envelope convenient way of using base. Base is not a sort of guaranteed approach, it's a programming methodology, and it's introduced to overcome some of the overheads of building an ACID system. So ACID, we can build transactions with locking. We can use locking with various different mechanisms, but one of them we talked about earlier was Zookeeper. Zookeeper is based off this Paxos algorithm. We can also use straightforward two-phase locking that's been quite popular in small distributed database systems. Another approach is to use timestamps. We can have a clock. The clock can increase, as we saw, and there are various implementations of that. One of them is Lampport's logical clock algorithm. So this will give you a way to know when things are changing and what approximate times are, and you can use that to try and judge whether you've got a consistent transaction or not. And another approach is just to take a snapshot of all of the system itself and use that as, if you like, the truth of what is the state of the system. You can have distributed transactions. You stop everything, you take a snapshot, you start everything up again. That snapshot would encapsulate all the values, and you could say, well, it's the ground truth. Right now, it's got to be consistent because it's got all of the data that has been changed or not changed, all in that snapshot, in that dump of the system. So ACID is an approach, it's a model for the correct behavior of, well, pretty much any sort of computation. It really constrains us to operating like a state machine. It's the correct behavior for databases. The name was coined in the 60s for databases. Its name corresponds to different properties. A for atomicity. Even if transactions have multiple operations, it will do the operations to completion, or if it can't do them for some reason, say there's conflicting updates, it will roll back so that there's no impact of having tried it, and then it will try some other way to do the updates. So atomicity is you either do it or you don't do it, and if you don't do it, the state's what it was before you ever tried to do it, and if you actually finish it, then the state is updated and everyone sees that view. The consistency, after you've finished the transaction, all those values are going to be consistent. So if you have, say, a distributed system with a variable on two different parts of the distributed system, what you will see is that variable will have the correct consistent value in it as part of the consistent state. Isolation. It looks almost as if the transaction ran by itself, even though there could be multiple transactions running in the system. Basically, what it does is to say, well, we'll constrain everything so that all the updates look like they occur in sequence, even if there's some possibility of concurrency. And we saw that earlier on. When you're reading a database, you can be reading it. If your cache values don't interfere with anybody writing, you can be reading it and have a consistent view of what's going on. But as soon as you go and write to a database, then you introduce difficulties. And durability. Doing the ACID transactions, making sure everything is consistent. What you don't want to have happen is that the updates get lost. You don't want, once an update is being used by a client, you don't want it to be rolled back so the database no longer represents what the client's been using. So durability is that the state really is there for good. Transactions are based on this ACID properties. The applications are coded in a stylized way, and typically they sort of say, well, begin transaction, then they'll do some reads and update operations, and they'll terminate by saying, well, either commit or abort. The commit will occur if the system believes and the programming believes that all the changes were made to the databases and all the values are now consistent all the way across, so there is no question that we haven't followed the atomicity rules. The abort will occur if, in doing this, there are more than one process, say, writing, and there are now a variable with more than one value, then you would abort and you would begin again to do that computation. So here's an example. If you have a employee with an employee record, and there's an account rep for him, and Tony, and account rep Sally. What we can do is update all of that data at the same time. If we like it, we can say commit, and then it's in the database, it's durable. Next time you go back to that, you would see it. If, on the other hand, as you were doing this, some other process interfered and changed one of those values, perhaps it changed the status to re-employed, what would happen is that this particular transaction would abort, and you would go back to the state of the system before this actually occurred. So why is ACID helpful? Well, you don't need to worry about the transaction leaving some sort of partial state. You don't need to write sort of, well, if this got updated, then do this. If this got updated, then do this. Even trying to test whether something's updated may be a problem. If you have, say, a variable that consists of multiple words in the memory of the system, as that update occurs, it may change those words. You don't know how far it got through all those words. So none of that needs to worry you. You can just use the transaction to do the operations. Similarly, a transaction can't glimpse a partially completed state of some concurrent transaction. You don't have to worry if the transaction's going to crash or not and leave a partial value. It's either going to finish or it's not. So this is like if you're sort of got a linked list and you're trying to put something in the middle of the linked list, you worry if you don't actually update everything and your machine dies in the middle of updating the linked list, you could leave it a mess. Well, if it's a transaction, it wouldn't be. It would either work, the linked list is preserved and updated, or it's hasn't updated and it's what it was before. So that's ACID for us. Clearly, as you're doing the transaction, one of the systems holding all of this could fail. If we go to a very large system and we're updating data, we might want to replicate a lot, and that replication might occur on multiple different machines, and the likelihood that one of them fails could be very large. So what one does is to provide sharding and different code transactions to actually implement such complicated schemes. You could have hierarchical or whatever type of transactions to deal with it. But all of that introduces overhead, and you're going to be passing messages to actually coordinate all of these systems as they do their operations. And so what you can show is that that order of overhead increases in a power of 2 manner because of the nature of the duplication. You can make it much worse by having some sort of naive implementation, but you can't get much better than the types of things, order power of 2, in trying to make this efficient. And to some, that's not just giving availability for everything that you would like the cloud to do. So the idea is to look at building conventional sort of ways of programming to build up in this sort of conventional view of how you proceed and have everyone write to that convention. It was proposed by eBay researchers. The idea is everybody's used to transactional thinking, transactional programming, but that has its overhead. On the other hand, there's this case where you don't actually need to do the transaction. You could cache, you could allow a slight outdated piece of data to be used. Base will allow you to do that without actually incurring any costs, and it provides a sort of flexible way to handle that situation, and it's all encompassed in a coding style. So in a sense, it's sort of opposite of ACID. It's living dangerously, but it's making that danger usable in the cloud by making it follow a set of standard protocols about the way that systems are built. So what one does is to take a step-by-step transformation of a transactional application into one that is more concurrent and less rigid. It doesn't guarantee ACID properties. It does provide parallelism. It sort of is a parallel to CAP. It doesn't do everything. It doesn't solve the CAP problem at all. What it does instead is to, well, effectively live on this spectrum going from a rigidly ACID system to something that's actually serving your purpose, but can sometimes mislead the clients because the values be out of date. So base, well, its name is basically available soft state services with eventual consistency. It basically describes what it's trying to do. It's trying to make it eventually consistent with stale cached values that are not too harmful for the programmer, and it's trying to model transactions in a sense and provide you an easy way to go from transactions into this style of programming, thereby benefiting from the high speed and the availability. So terminology, basically available, the fast responses, even if some replicas are slow or crashed. So the base paper says that in data centers, partitioning faults are very rare. So when they do occur, well, you can afford to have the thing crash and to sort of reconstruct everything, reboot, and continue. And if you can make do with cache values while you do that, all to the good. The soft state service, that there's no necessarily durable memory. You can't store any permanent data, but if you do restart, then at least the data is clean and there's sort of consistency amongst the data. If you want to remember data, you either replicate it in memory in enough copies to never lose any in a crash, or you pass it on to a service that keeps some sort of hard state and can help you get back that state. So the soft state service is kind of one of the other types of approaches. It doesn't consist, say, of doing a snapshot that's completely correct onto disk. You can use all sorts of different schemes for the different parts of your system, but essentially, as you're doing the particular computation you want, you can employ this soft state service to provide that application all by itself, this property, albeit it's all programmed. And then eventual consistency, that it's okay to send out optimistic answers to the external client where those answers don't conflict with what the client wants to get done. So if you're using cached data, you could send that cached data out. You don't need to check for staleness if it's not going to really affect the results of what that client is requesting. So if he, for example, wants to know how to get from Champaign-Urbana up to Chicago, it's unlikely that sort of changes in the map are going to change that fast that his cached data won't be a reasonable, valid way for him to drive that distance. That cached data, you could guess what the outcome of the update will be. So if you have something that's increasing, you can expect it to keep increasing. As in, for example, if you have a clock and the clock crashes, when you start a clock, you would expect it to be increasing still, and so you could still use its value. That you might skip locks, hoping that no conflicts will occur. Well, very often locking is unnecessary because people don't update the variables held between the locks very frequently. So if the chances of this occurring are 1 in a million, why would you need to worry about it too much? And typically, one of the things they would expect with base technology is that if any of these things aren't quite right, that lead to inconsistencies in the values, that at some point you can actually correct the inconsistencies by sort of doing a cleanup of everything that's there. So if you notice, say, 2 clocks have different values, then eventually you can bump them up to the highest values, say, of both clocks. Or if you're advertising a price and the price is increasing and you have 2 slightly out of adjustment prices, eventually what you can do is to get those 2 prices to be the same. So, ACID code. The claims are it's much too slow and it scales poorly and end users wait a long time for responses. Clearly there's lots of research trying to make it work faster, but in general the notion is very difficult to overcome that if you take an ACID system, you scale it to say 10,000 nodes, that the overheads won't actually slow down the whole of the cloud. With base, it's much more concurrent, much faster. It eliminates responses. It gives you a better user experience. There's going to be some oddities. You're going to notice some, say, price inconsistencies sometimes. If you're bidding on buying something, you might see little differences in the bidding prices. If you want to upload a YouTube video, you search for it, you may not see it immediately. There's some sort of disturbing little inconsistencies, but overall it doesn't lead to a major problem. So we've motivated both ACID and base, and we've talked about eventual consistency right at the beginning. Now what we want to do is to see how you would take eventual consistency and actually build a system to provide it in a cloud. So we're going to do a centralized service. It's going to coordinate, it's a coordination kernel, you might say. It's going to coordinate everything inside the system so that all of the system, whenever it wants to get to eventual consistency, can use this particular algorithm to achieve that. We're going to look at Paxos. Paxos acts in a very distributed manner. Lamport created it. It's based off a quite interesting discussion of a Greek island state operating in a parliamentary style, but we won't address that. We'll just look at the way that the algorithm works. In general, it gets implemented as something called Zookeeper in many of the Apache projects, and Zookeeper is a simplified version of Paxos and operates perhaps not quite to such scale as Paxos could, but it operates sufficiently well that to all intents and purposes, Zookeeper is the module you use. So we want a centralized service, coordination. It's going to maintain configuration information. It'll allow you to do naming, get the consistency for naming right. It'll allow you to do distributed synchronization. It allows you to build group services, any sort of function inside a cloud where you need consistency. It avoids synchronization. It avoids races so that if you have a race, you don't know who's going to win. You may have to keep repeating the race. It's going to avoid all that and make sure that you have eventually a result you can use. The file system based API allows you to manipulate small data nodes, and The state is a hierarchy of nodes. The system uses that sort of file system-based API to keep track of everything, so it remembers what the state of everything is. And we will now look at the actual algorithm employed. So, if you were to describe this Paxos to people, what you would say is, well, let's suppose there's somebody wanting to make a change to the system, a proposer. The proposer is going to request that the Paxos system accepts some sort of command that will change its state, and Paxos is going to act like a postal system. It's going to make sure that the state changes. It's going to think about the whole state of the system, look at the letter, what the letter needs to be done, or what needs to be done in the letter. It'll replicate data, making sure that there's enough copies of things to guarantee, as far as it can see, that it will all occur. And then once all this is decided, that whole process of how to do things is decided, it then goes ahead and executes the proposer's command using its algorithm to make sure that there's lots of redundancy and you're going to achieve eventual consistency. In the diagram, you see the proposer sending mail to an acceptor. The job of the acceptor is to keep track that the proposer has asked for this computation to be done. They're replicated. The acceptors are all going to sort of work out how to operate and how to conduct the command. And then when they've all sort of sufficiently learnt how to do that, they will let the learners know what that command was. Now, we have enough acceptors, and each one of them is responsible for trying to do this command, that the acceptors can actually form a quorum, and the learners will learn from the quorum of acceptors what was successful. So here you've got a system where you know that you're going to get an answer because of the quorum mechanism. You know that what you're going to achieve is a sort of eventual consistency because of eventually some quorum of those acceptors are going to decide on some value. That is how the mechanism is going to work. So, more detail. The client issues a request to the distributed system, waits for a response, and for instance, might request a write on a file on some sort of distributed file server. The acceptors act as a fault-tolerant memory, a reliable, durable memory, that this is what's going on. And some of these acceptors can die in the meantime, but it's still going to grind forward and actually produce a consistent result. Acceptors, there's enough of them that if one or two of them die, it doesn't matter. In fact, we have a lot of acceptors. They can even have faulty operation. What we're going to do is to assume that the majority of the acceptors will come to a decision that's, or a way of writing to the file that is acceptable, and that quorum, once it's formed, will let the learners know they've achieved their goal. Any message sent to an acceptor is duplicated to that quorum, and any message received from an acceptor is ignored unless you get enough of the acceptors sending the same copy of the message. Paxos is based on very sort of weak assumptions. The processors can operate at different arbitrary speeds. The processors can all fail. The processors with stable storage can rejoin the protocol after failures, and it doesn't hurt what's going on. Remember, the quorums, you can have people leave the quorum and join the quorum, and it's still, as long as there's a quorum reporting to a learner, it's okay. you can use crash recovery fault tolerance techniques in the middle of this, and it doesn't affect any of the computations. There are some assumptions that the processes don't collude or lie or otherwise attempt to subvert the protocol. So this isn't a sort of mechanism for Byzantine failures, malicious code in there sort of trying to cause trouble. This is that everybody's trying to do their best, and this protocol is trying to ensure that if they do their best, you're going to get an eventually consistent result. The network itself, well, processes will have to send messages over the network to other processes. Messages can be sent asynchronously. They can take arbitrarily long to deliver. And this is the key nuts and bolts of things, that because they can take arbitrarily long, but you need to have some decisions made, you're going to the arbitrary, well, this set of acceptors in the middle are going to make sure that there is a reasonable confidence that the messages have been sent and received enough that you can move forward, even if some of the messages have got lost. So messages are delivered without corruption. You can obviously put checksums and other things in the messages, and that avoids some types of Byzantine failures and makes things a little bit more reliable. In general, how many processes do you need to actually do this? Well, there are consensus algorithms that show that there are actually limitations on how well you can proceed in an asynchronous system. In general, this particular consensus algorithm can make progress if it has 2f+1 processes, despite the simultaneous failure of any f processes. So you do need a lot of machines, but what it will do is to guarantee from 1 up to f that those failures can occur and it will still provide consensus. And this is why you're using the quorum. The quorum is going to guarantee that you vote amongst all of those duplicate processes in order to establish the results. If you're using reconfiguration, a protocol must be used, and it makes survival of any number of total failures okay, as long as you don't have more than f fail at the same time. So you could have, f fail and have or f-1 fail, and then restart, and that will be okay. But what you can't do is the total number. So Paxos has proposers, it has acceptors, and it has learners, and they communicate. And the proposer is going to send to a bunch of acceptors, and if it's going to try and convince that collection of acceptors to agree. And if it can get a quorum of acceptors to agree, then it moves forward. The acceptors tell the proposer that they've accepted it, and they notify learners, and the learners then sort of link round and actually do the implementation. So the proposer, clearly advocating a client request, has to make a good job of it. And what he has to convince the acceptors is that his request is the one for them to act on. And therefore, he's got to show that it is the latest, most up-to-date request and doesn't conflict with anything else. And you'll see how the agreement protocol works to do this. Once a client request has been agreed on by the acceptors, the learners may take action. They may execute the request, they may send a response to the client. To improve availability of processing, additional learners can be added so that if one of them fails, you don't have a problem. Paxos requires a distinguished proposer, and that's called the leader. Now, it's not clear who the leader is, it will emerge. There is a mechanism to make sure that one of the proposers becomes the leader. Many processes may believe they're leaders. The protocol only guarantees progress if one of them is eventually chosen. So this is a sort of leader election algorithm. We won't go into the details because we don't have time, but if you imagine if the processes that are the proposers number their requests, then the person who's got the highest number believes he's the leader, and if the acceptors agree with that number, then he is indeed the leader. If two processes believe they're leaders, they may stall the computation. They could actually sort of keep leapfrogging each other, but the safety properties that what is decided is consistent are still preserved, and eventually one of those two processes will head along and eventually cause the consistent update so that we've got everything agreed. The proposal number and agreed value. Each attempt to define an agreed value for the decision that's being made by the acceptors is proposed, and it may or may not be accepted by the acceptors. So what we need is a mechanism to decide how that happens. Well, we label each proposal uniquely with a number, and that's given to it by a particular proposal, and that particular number is unique to the proposer. So these numbers issued by the proposer identify in a unique way every attempt to try and get agreement from the acceptors. Well, basic Paxos, what it does, it decides on a single output value given all these proposals that are coming through. A successful round has multiple rounds, and a successful round has two phases. One is that there is a prepare promise made with a number of the proposal number on it, and when it gets accepted by all the acceptors, there's an accept request that's accepted by all these acceptors. And you would like the quorum of acceptors to then act. And what they would do is to notify the learners that everything's gone through. So let's be a client. What we want to do is to make a request, make some statement be so, like could be a semaphore value, it could be updating a database, whatever. So the client makes that request, and a proposer picks up the request on behalf of the client, and now he is going to try and get it through the Paxos mechanism. And remember, the acceptors are dual duty. One is they're resolving any race conditions and other things so that there aren't race conditions effectively. And they're also providing a memory so that if one of the acceptors dies, there will be lots more acceptors to actually take on the burden of making the choice. So we make a request, that goes to the proposer. The proposer prepares a promise, and that promise creates an identifier, say n, and this number must be greater than any previous proposal number used by the proposer. And then it sends a prepare message containing this proposal to a quorum of acceptors. Now, it could send it to all of the acceptors, and it probably would. All that's required is that it sends it to a quorum because it needs a quorum to actually agree so that it can move, that proposal can move forward. So there's plenty of room for failures. There's plenty of room for lost messages because of this notion of quorum and the memory entailed by having multiple acceptors. Once that prepare promise is being created, it's sent forward, and you can see it there in the diagram. Prepare n, which is the number of the proposal, and it's got a value Vx, and that has been sent to all the different acceptors. You can use all sorts of different mechanisms to actually give it to the acceptors. That's a sort of implementation detail. Well, the promise, if the proposal's number n is higher than any previous proposal number received from any proposer by an acceptor, so the acceptors are acting as a filter, then the acceptor must return a promise to ignore all future proposals having a number less than n. So this is a way of sort of increasing the height of the gate or whatever. It's making it more and more selective, moving forward into the future, if you like, by increasing n by the actual numbers the acceptors are receiving. So if the acceptor accepted a proposal at some point in the past, it must include the previous proposal number and previous value. And what it's going to do is to reply to the proposer that gave it the largest n with the details of what its past proposal number and value was. So there's a record going on being kept in the messages of just how you're moving forward in time, and the acceptors are implementing that by replying back to the proposer. Well, if the proposer's number isn't higher, the acceptor can just ignore the received proposal. It doesn't matter because the next proposer is going to propose a higher n, and the whole thing takes place in a forward-looking way. It doesn't have to answer. For optimization's sake, it's better if it sends a denial, a knack, saying, oh, that's a too low number, I've got one already. But it doesn't affect consensus at all. So the acceptor, what it does is to respond back to the proposer, and you can see it in this diagram, the promise. It sends any previous value it's got. It sends back the number of the proposer that it's actually said is the largest, plus the values. And then this list is any other proposals that it's received. If a proposer receives enough promises from a quorum of acceptors, so it can count them and see, oh, I got back from all these acceptors enough to be a quorum, then what it's going to do is to set its value to what it actually got back, such that its number is the largest of all of the things that it got back, and its value is the one that it decided. If any acceptors have previously accepted any proposal, they'll have sent their values to the proposer, so it doesn't really matter which proposer actually is receiving some of these things, because what the proposer is going to do is to choose the max. They're going to set the value of its proposal to the value associated with the highest proposal number reported by the acceptors. If none of the acceptors had accepted a proposal up to this point, then the proposer may choose any value for its proposal, because basically the acceptors could have all died and they are all being rebooted and you're starting all over again. So you want it to continue no matter what happens. Then last, the proposal sends an accept request message to the quorum of acceptors with the chosen value that it made, and it sends it back. Now, you note the proposer, after it sends the initial request, could have died. It doesn't really matter in this protocol, because the acceptors, the quorum of acceptors are going to send the stuff back to the proposers. One of the proposers is going to act on these decisions, and if it has a majority, if it has that quorum count, it's going to propose what to do. So the proposer accepts acceptors' proposal number, and you can see that here. I'm accepting, and it's going to take the maximum number of all of these proposals that have been made and the value that was actually proposed with that particular proposal. So here you've got a lock-in. Now the acceptors know what's happened. They've recorded all the information. The proposer comes back and says, I hear you. Here's what I've decided. And that quorum has now got locked in a proposal number. If an acceptor receives an accept request message for proposal N, it must accept it. If and only if it's not already promised to consider proposals having an identifier greater than N. Remember, the proposer might be lazy. He might be asleep, or he might be slow at least. So another proposer could have leapt in and made a decision. So the acceptors need to have that sensitivity. They need to pick the most appropriate proposal N. In this case, what will happen is the acceptor will register the value N, send an accepted message back to the proposer, and it will tell the learners that it's accepted it. Now, otherwise, if there's any other problems, it can just ignore the accept request. But that's what's occurring. So the learners are seeing messages coming in from this quorum of acceptors saying they've accepted a proposer's proposal and the number and the value, and the proposers are learning about it, and you have a sort of memory system remembering all this. You have the decisions over what's actually going to occur based off the quorum, which is always going to break races, and so you have a mechanism that satisfies many of the constraints that we've been putting on this protocol. Rounds fail when multiple proposers send conflicting prepare messages, or when the proposer does not receive a quorum of responses, promise or accepted. In these cases, you just go and do it again. Notice that when acceptors accept a request, they also acknowledge the leadership of the proposer. Hence, Paxos can actually be used to select a leader in a cluster of nodes. You don't need to have a leader election algorithm. It's doing it for you already. So here's what's happening. We've got an accepted, and that's being sent back to a learner and back to the proposer, and it's got the maximum proposal number and the value for that proposal. It's got a list of what's been decided before, but now you have a complete record in that message, so everybody knows what's happening inside this Paxos system. And then the learner, once it sees that there's a quorum of acceptors that agree to this, all of this data, what they do is to say, oh, okay, quorum decided, and it notifies the client that we have indeed sort of got a quorum decided, and it is going to do the action requested. And so thereafter, the state changes. The state is now VM, and you have consensus. So, as you can see, Paxos is quite complicated. Now, I didn't do all the corner cases. If I had done all the corner cases and described all the protocols, that would take a long time, and I would refer you to Indy Gupta's presentations and lectures to see the intricacy of Paxos. But what I wanted to do here was just to reiterate, Paxos is this cornerstone of consensus in systems. And you can build Paxoses for almost every occasion. If you want to have a multi-Paxos system with multiple Paxoses occurring, you can do that. If you want to have a cheap Paxos system, which only tolerates F failures with F+1 processes and F auxiliary processes, you can do that. If you want a fast Paxos, well, you can reduce the end-to-end messages, piggybacking and other things. If you want to generalize the Paxos, that exploits commutativity to actually make it a much more flexible system. And there's Byzantine Paxos. What you've seen here is that there are certain constraints on failures of the Paxos system, and the Paxos system doesn't lie. The pieces inside Paxos don't lie. But you could have a Byzantine Paxos where the elements, the acceptors, the proposers, and so on, could actually lie about what's going on, and you can still sort it out. In that case, you need many more different instances of the pieces of the acceptors and the proposers and the learners. Well, there's a bunch of references about Paxos. You can spend a lot of time. If you want a lot of fun, what I would do is to read Paxos Made Simple, which describes Paxos as it applied to a Greek parliament. But Fred Schneider gives a good sort of description in terms of state machines. So we were discussing Paxos, and from that we found an algorithm that works on a distributed machine that would actually give us eventual consistency. That was quite a remarkable step by Lamport. The next step is to find something that would work on a large cloud but wouldn't have quite so much overhead as Paxos. A lot of these commercial systems that we're building, they want something nice, efficient, fast, and effective, and all the bells and whistles that Paxos offers are not necessarily what the cloud people really need. So Zookeeper, it's a highly available, scalable distributed configuration, consensus making, group membership, leader election, naming and coordination service. It's fast and efficient, lean and mean. And there may be, or there will continue to be, improvements, I'm sure, on Zookeeper. But what it establishes is something you can put into a component and you can build clouds from very easily. And that is exactly what you're finding underlying Hadoop, underlying the databases that we're using, and all of the consensus seeking algorithms that we deploy. So it's difficult to implement all these different services. We want redundancy. It's got to be, you've got to avoid brittleness. You want to make it easy to manage. You want to make the implementations simple to do. And that's really the essence of the Zookeeper effort. It's a file API. You're going to keep consistency amongst lots of different things. Those things are identified as data objects. The data objects are organized as a hierarchy. And then what Zookeeper does is to manage all these different objects kept in those files so they're consistent for everybody looking at them. Hence the Zookeeper name. So there's per client guarantee of FIFO execution on the requests, and all the requests that come in from all the different clients are linearized so that they change the state in a linear fashion. There's no racing or anything else going on. Everything's moving from state to state in a nice organized way. The whole mechanism of Zookeeper is built using a protocol called ZAB. It's a totally ordered broadcast protocol. It's based on Paxos. You might say it's a degenerate version of Paxos. It's not as complicated as Paxos. It can run very efficiently. It's using broadcast to eliminate some of the overhead that you get in Paxos and sending lots of messages backwards and forwards. Because it's broadcast, everyone can observe what's going on, and that kind of eliminates the need to have groups agreeing about what's happening in the system. Again, with the recovery, the fault tolerance, if you have two F+1 servers that can tolerate F crash failures. So you get a good reserve of system in event of failures. So what are the guarantees? Are there any guarantees? Well, the clients never get to see old data. The data will be refreshed. If it's in the Zookeeper system, then anybody observing the Zookeeper, the variables being kept by Zookeeper, will see fresh data all the time. They will never see old data. The clients will get notified of changes to data they're watching within a bounded period of time, which is really the eventual consistency requirement. All the requests from a client will be processed in order. All the results received by a client will be consistent with the results received by other clients. So in this mechanism, there isn't stale data. You don't see that stale data. What you do is have your requests delayed until such time as all the data is actually updated. So the basic Zookeeper has servers, and you can have quite a few servers. They're all on different machines. All the servers store a copy of the data on a disk. A leader is elected at startup. Followers service clients so that you can have parallelism going on from the clients to the servers. All the updates goes through the leader. The update responses are set when a majority of servers have actually taken the updates and stored them on their file system. So you have this notion that what's on the individual file servers of the servers, once there's enough of those, once the majority of servers have stored on their file systems the value, then that is the value that Zookeeper is going to return as the consistent value in this distributed algorithm. So here's the leader, note flagged with red. All the servers store a copy of the data, the logs, snapshots on disk, and they use a in-memory database to make it all run faster. The leader is elected at startup. The followers service clients. All the updates go through the leader, so the leader actually knows all of the consistency problems and can resolve them. The update responses are sent when a majority of the servers have recorded the change. So if the leader dies, you can elect a new leader, and there is a majority of servers out there that actually know what the state of the system should be. So the redundancy is caused because those servers are recording the data on their disks, and this overcomes any problems with the leader crashing. You can just switch in another leader, and it can just resume from where everything left off using the majority value that's stored on all those servers. Protocol guarantees. Well, what you're going to achieve with this is sequential consistency, that all the updates will be sequentialized as they go through the leader. The updates from a client will be applied in the order they're sent by the leader, so you have a sequential version of consistency, which is good. The atomicity, updates either will succeed or they'll fail. There are no partial results, and the leader again is going to choose what happens. The single system image, a client will see the same view of the service regardless of which server it connects to, because they all have similar copies since they've fed that from the leader. Reliability, well, once an update has been applied, it will persist from that time forward until a client overwrites the update with another write. And so you have the dependability there built in. Timeliness, the client's view of the system is guaranteed to be updated within a certain bound. And we'll see how that's done. Either system changes will be seen by the client within this bound, or the client will detect a service outage, and so it will know something's gone wrong and it can take appropriate action. So the basis this is the ZAB algorithm. I've given you the HTTP for the ZAB algorithm. Zookeeper is based on ZAB. ZAB's a degenerate form of Paxos. It's an atomic broadcast. It consists of two modes. One, recovery, when the service starts or after a leader failure ends. When a leader emerges and a quorum of servers have synchronized their state with the leader, then you get this recovery. Then there's the broadcast. Leader is the server, and what it does is broadcast to the other servers using the broadcast protocol. And once a leader is synchronized with a quorum of followers, it begins to broadcast its messages, and they all record out onto the disks. So the leader broadcasts a proposal for a message to be delivered. It sends it out to all the servers. Before proposing a message, the leader assigns an ID to it, so things can't get confused between the leader and the other servers. And if a server dies and then comes back up, it can use these numbers to sort out what things it's missed and what it should be doing. Because ZAB preserves causal ordering, the delivered messages will always be ordered by these ZXIDs, these unique IDs on the messages. The broadcasting consists of putting the proposal with the message attached onto the outgoing queue for each of the followers of the other servers. And so that's a protocol we're going to see is implemented with TCP. So it's actually a fairly straightforward way of doing the updates to everything. Remember that number, the ZXID can be used to order in case there's problems with the servers going up or down. When a follower receives a proposal, it writes to the disk and sends an acknowledgement back to the leader as soon as the proposal is on the disk media. So in this way, the leader knows that all of the servers have actually, or a majority of the servers have actually recorded what it said. So once it's confident about that, it knows that the new value is established. When a leader receives the ACKs from a quorum of servers, then what the leader would do is broadcast a commit, and it delivers the message locally to the client that asks for that consistency service. So the followers deliver the message when they receive the commit from the leader, and then you will have everything updated. So here's how the ZAB leader election works. The Zookeeper service, it's got all its servers. What you do is to use UDP in this case for the leader election. The server with the highest log transaction gets nominated as the leader, and if the election doesn't have to be absolutely correct, it just has to be very likely to be corrected, because everybody's going to see who got elected, and they can and they're going to be a vote from the majority of them on what that is. So here you've got the servers. They are sending out their own messages saying they're voting for who. Each server initially nominates itself, and then the servers poll each other to get their votes using the UDP protocol, and eventually when all of them are happy, when enough of them are happy, having got the votes from everybody else and they all agree, then the leader election is complete. After polling each other to get their votes, they will vote for the one with the highest ZXID if there isn't a winner, and the one with the highest ZXID will be the one that takes over leadership. So, stepping back a second, why have two different mechanisms to do consistency in a system? Well, we've seen it's Paxos. It has very nice roots. It has a very good argument associated with it, and it's very general, and we've seen there's lots of different applications of it. And then we have ZAB, which is on a cloud, often used, and provides a sort of commercial type of version that's very fast and efficient. So what's the differences? Well, Paxos tolerates message losses and reordering. Zab is going to use TCP basically to get the messages across and to keep the messages in order, so it doesn't have all of the problems of Paxos. In Paxos, you need quorums. In Zab, you don't need quorums. What you're going to use is the majority of servers, but there doesn't have to be multiple quorums or decisions about whether the quorum is present. That's all going to be, I don't know whether I should actually say that. Let me go back to I'll restart from the quorums. Paxos has quorums. Zab doesn't have quorums. It's going to use a majority vote from the servers, as we described before. If in Paxos the proposer believes it's the leader, then it uses a higher number to take over leadership from another leader. It can always keep trying to do that. Eventually one of the proposers is going to come out ahead and is actually going to be able to do what the leadership behavior requires. In Zab and in Zookeeper, the leader is actually not that easy replaced. It's elected. It stays there until it dies, and so that part of the protocol is a lot simpler and easier, requires a lot less messages. So here you've seen the theory, Paxos, the practical, Zab, and Zookeeper. Zookeeper we're actually using day-to-day in this, in your exercises, in your MPs and so on. But Paxos does have its place, and it is used in very large distributed systems when scalability is a big issue and the whole system has become extremely complicated.
So in this lecture, we'll be looking at the design details of Apache Cassandra. So Apache Cassandra is a distributed key value store intended to run in a data center and also across multiple data centers. Originally, it was designed as Facebook, as an infrastructure for their messaging platform. However, later they decided to open source it, and today it's one of the most active Apache projects. A lot of companies use Apache Cassandra in their production clusters for a variety of different applications. These include blue chip companies such as IBM, Adobe, Hewlett-Packard, eBay, Ericsson, Symantec. Also newer companies such as Twitter and Spotify use Cassandra. Non-profits such as PBS Kids use it. And if you've ever used Netflix, you have actually indirectly used Cassandra. Essentially, Netflix uses Cassandra to keep track of positions in the video. So wherever you are in a particular video is kept track of in Cassandra, so that if you pause the video or if you stop it and then later resume, the Cassandra key value store is used to fetch your latest scene position. So let's go inside the design of Cassandra itself. So the first question that has to be addressed by the design is, given a key value pair, how do you map the key to a server? How do you know which server stores that particular key value pair? Well, it turns out that because key value stores are similar to distributed hash tables, Cassandra uses the ring that we saw in a distributed hash table. So you might remember this from when we discussed peer-to-peer systems. Essentially, Cassandra places servers in a virtual ring. Again, the ring here consists of 2 power m points, and m here is 7, so it's 128 points. And the server is placed at a point in the ring, and essentially then you map the keys onto points in the ring, and the server gets stored at the key gets stored at servers that are successors to its point on the ring. So for instance, key with an ID of 13, which maps to 13, would get stored at servers 16 and also 32 and also 45. One of these might be the primary replica, one of these, the others might be backup replicas. As far as Cassandra is concerned, it doesn't necessarily need to have primary or backup replicas or need to know the notion of primary or backup replicas. It just knows them as replicas. The client sends its queries to one of the servers in the system. It need not be one of the replicas. This server is called the coordinator. And again, the coordinator need not be on a per data center basis. It could be on a per client basis or on a per query basis. It doesn't really matter. There's also one ring present per data center. So if you have Cassandra running in two different data centers, each of those data centers would be using a separate ring with its own servers mapped to that ring. What is not present in Cassandra, which was present in a distributed hash table like CORD when we discussed it, is the notion of finger tables or routing tables. So there's no routing used in Cassandra here. Instead, when the client sends a query to the coordinator simply forwards a query to the appropriate replicas or just some of the replicas for that particular key. This means that every server, which could be the coordinator, needs to know about where the keys are stored on every other server in the system. We'll come back to this later on. We'll discuss later on how servers know about each other. But for now, let's focus on the key to server mapping. So the mapping from key to server is called the partitioner, and that is what is used by the coordinator here to find out which are the replica servers to forward a particular query for key 13 to. So there are different kinds of replication strategies. There are two main classes that are supported by Cassandra. They are the simple strategy and the network topology strategy. The simple strategy uses the partitioner, and there are two kinds of partitioners. The random partitioner uses hash-based partitioning just like CORD. So essentially this is the version of Cassandra that is the most similar to CORD, where essentially keys are hashed onto a point in the ring and then are stored at servers that are close to that point in the ring or are assigned to that segment in the ring itself. So for instance, if you assign to each server the segment in the ring that is between that server's point on the ring and its predecessor, then this becomes most similar to the CORD hash-based partitioning. There is also a byte order partitioner, which assigns ranges of keys to servers. You might want to maintain a table in Cassandra that preserves the ordering of the keys in there. For instance, the keys might be timestamps, and you might want to maintain the ordering of the timestamps. This does not hash the keys. Instead, it simply maps the key onto a point in the ring based on the value of the key itself, so that two keys that are in order in the real space are also in the same order in the ring space itself. This is useful for range queries. For instance, if you want to get all the Twitter users starting with A or B, then you can do a range query very easily if you're using a byte order partitioner by simply searching for the servers that would be storing that particular range of keys. If you were using the hash-based partitioning instead, you would essentially have to ask every single server in that particular ring to see if the server has any key value pairs that match this particular range. The network topology aware strategy is a different strategy which is used for multi-data center deployments. It supports a variety of different configurations. It supports one configuration where you can have two replicas of each key per data center. So if you have 3 data centers, then you essentially have 6 replicas, 2 in each data center for each key. There is also a different configuration which is 3 replicas per data center. Now, how do you select the replicas within each data center? So on a per data center basis, you first place the first replica according to the partitioner. Again, you can use a random partitioner or a byte order partitioner here. And then for the next replica, you want to make sure that you're storing that second replica on a different track. Why? Well, you don't want rack failure within a data center to lose all copies of a given key. So you place the second copy of a key on a different track. Essentially, you go around the ring clockwise until you encounter the first server that is in a different rack from the first replica that you placed. And you place your key at that first server. So this ensures that there is rack fault tolerance, and it also ensures that there are 2 replicas, in this particular case, for that key in that data center. So Cassandra uses a mechanism known as snitches to map IP addresses to racks and data centers. You can configure this in the cassandra.yaml configuration file. Cassandra offers a variety of snitch options. I'm going to discuss a few of those options here. And the first option is as simple as the simple snitch, which is unaware of the topology. In other words, your application really cannot know much about which IP addresses map to which racks and which data centers. In some cases, this works. For instance, if you're running only one VM, then you don't really want a snitch, and simple snitch is fine. The second snitch is the rack inferring snitch, which tries to guess from the IP address what the rack and the data center might be. Essentially, the IP address breaks up into 4 octets, and the first octet is ignored. The second octet is used to map to the data center. The third is used to map to the rack, and the fourth is used to map to the node. So for instance, if I have an IP address that goes 101.102.103.104, then essentially 102 is the data center octet. So any other node that, any other IP address that starts with 101.102 will belong to the same data center as this particular IP address given over here. The third octet is the rack octet. So any other IP address that starts with 101.102.103 will belong to the same data center and rack as this IP address given here. And finally, the last octet, 104, identifies the node. So any other IP address that has exactly the same 4 octets shown over here will be the same identical address, namely it refers to the same IP address and server or VM as this particular IP address shown over here. This of course is a best effort guess, because IP addresses may not map actually to racks and data centers as shown over here, but not knowing anything else, this is a pretty reasonable guess. You can also, if you want to be really accurate about which IP addresses map to which racks and data centers, if you actually know this information, you can create this in a property file, and this is called a property file snitch, and you write this into a configuration file. Finally, if you're running your Cassandra on EC2, EC2 of course uses regions, and within regions there are availability zones. So the EC2 snitch in Cassandra allows you to guess the rack and data center as the availability zone and the EC2 region respectively. And you can use this information then to do the Cassandra mapping, for instance replication, and also within a data center and across racks, as we discussed previously, and also across data centers. There are a variety of other snitch options available as well in Cassandra. If you're interested in this, please look at the Cassandra web pages. So how are writes and reads supported? So remember that when a client sends a write to a coordinator, the coordinator needs to forward the write to one or more replicas for that particular key that is present in the query, in the write itself. Writes need to be lock-free because we're dealing with write-heavy workloads here, and they need to be fast. Okay, so you want to incur few disk reads or seeks, preferably no disk accesses at all for the write in the critical write path. So the client sends a write to one coordinator node in the Cassandra cluster. The coordinator again may be per key, per client, or per query. If you have a per key coordinator, this ensures that all the writes to that particular key are serialized via that coordinator. But again, this is not a requirement for Cassandra. The coordinator, when it receives this write, uses the partitioner to find out which of the replicas that map to that particular key. It then sends the query to all the replica nodes responsible for that particular key. Then some of the replicas respond. When X replicas respond, the coordinator returns an acknowledgement to the client that the write is done. What is this value of X? We'll see that later. For now, let's just assume that X is some small number specified by the client that is smaller, less than or equal to the number of replicas for that particular key. So keys always need to be writable. So you want to make sure that even if you have failures, the writes succeed and return an acknowledgement to the client. So for this, Cassandra uses what is known as a hinted handoff mechanism. This works as follows. If any replica is down, the coordinator writes to all the other replicas, but it also keeps a copy of the write locally, and when that down replica comes back up, it is then sent a copy of that write. This ensures that replicas, when they fail and then recover, they receive from the coordinator some of the latest writes. However, all the replicas might be down. It's possible, right? It might be unlikely, but it's possible that you have 3 replicas for the key, and when a write comes along, all the 3 replicas happen to have failed. In this case, instead of rejecting the write, the coordinator stores the write locally at itself. It buffers the writes, and then when one or more of the replicas comes back up, it then relays the writes to the corresponding replicas. The coordinator, of course, has a timeout on how long it stores these writes. Otherwise, it may be storing writes forever. And this timeout is typically a few hours, which is good enough for replicas to recover and rejoin the system. Again, this mechanism is known as hinted handoff because the coordinator, based on the hints that it receives from the failure information, it might assume the ownership of that key for just a temporary duration of time. So if you have multiple data centers running Cassandra, you maintain one ring per data center, and you might also use a per data center coordinator. This coordinator is different from the coordinator used by client queries. The per data center coordinator coordinates with the other per data center coordinators to make sure that the data center to data center coordination is done in a correct manner. The election of the per data center coordinator is done via Zookeeper, which is a system, again an open source Apache system, which runs a variant of Paxos, and we'll see Paxos later and elsewhere in this course. So what does a replica server do when the coordinator forwards it a write? Well, the first thing it does is that it logs information about that write, just a little bit of information in a commit log that is present on disk. This is used for failure recovery, so that if the replica server fails at any point of time here on, it can know by looking at the disk log after it recovers that there was some write that it completed only partially, and then it can ask the coordinator for information about this write. After this, the replica server updates a mem table. A mem table is an in-memory representation of multiple key value pairs. Essentially, a mem table maintains some of the latest key value pairs that have been written at this particular replica server. It's a cache that can be searched by key, so you quickly search the particular key that you're trying to write. If it's present in the mem table, you update the corresponding value. If it's not present in the mem table, then you simply append to the mem table another key value pair. This mem table is called a write back cache, meaning that you're storing it temporarily and tentatively in a memory rather than writing it directly to disk. If you were writing it directly to disk, then it would be called a write through cache, and write through caches are much slower than write back caches. However, the mem table has a maximum size, and when this maximum size is reached, or when the mem table is very old, then it is flushed to disk. Essentially, you create an SS table or a sorted string table. Essentially, you take the mem table and you sort all the keys within them so that the keys are sorted and the values are present alongside the keys as well. And then you store it on disk as an SS table. Now, if you want to search for a particular key in the data file itself, in this data file that is the key value pairs, it might take a long time because it consists of both the keys and the values. So you maintain an index file as well, which stores an SS table of key, position and data SS table pairs, so that you can quickly look up the position of a particular key in the data SS table by looking at the index file SS table itself. However, in most of the cases, you might be checking for existence of a key in an SS table, and the key is just not there. In this case, doing a binary search through the index file to look for that key would just result in a very long, very large overhead. If you have a large number of SS tables, essentially each SS table containing m entries, then you're going to incur an ordered log m overhead per SS table in trying to look for a particular key. And so what you do is you add a Bloom filter, which is a quick way of looking for whether or not a particular key is present in an SS table. Okay, so a Bloom filter is a well-known data structure which Cassandra uses. So what is a Bloom filter and what does it look like? Well, here is a Bloom filter, an example. A Bloom filter is a compact way of representing a set of items so that the most common operation, which is checking for existence in that set, becomes very cheap and becomes very low overhead. The most common operation for a Bloom filter is you say, well, is this particular key present in this particular set or not? The other operation that the Bloom filter supports is inserting an item into the Bloom filter. The Bloom filter has some probability of false positives. An item not in the set may be returned as true, as being in the set, and for the Cassandra example, this just results in a little bit of extra overhead when you look through the index file and then subsequently do not find that item. But you never have false negatives, which means that if you've inserted an item in the set, you will always return true when that item is checked for the membership. So how does a Bloom filter work? Well, a Bloom filter is essentially a very large bitmap. Here's an example of a Bloom filter which has 128 bits, shown as numbers 0 through 127. The bits are all, each of them has a number, has an ID. Initially, all the bits are 0, so the entire Bloom filter is a 0. When you have a key, say k, you use a small set of hash functions, 1 through small k, to hash that key k. Each of these hashes returns a number between 0 to 127, both ends inclusive. So for instance, hash 1 applied on the key k returns the value 1. If you're trying to insert the key k, you're going to set that bit to be 1 over here. Again, hash 2 when applied to the key k returns a value of 69, and so if you're inserting the key k, you would set that bit number 69 to be a 1. Similarly, hash k returns a value of 111, and you set that bit to be a 1. So whenever you want to insert a particular key, you set all the corresponding small k hashed values to be 1s. If you insert a second key, you would go ahead and set those corresponding bits that that particular key maps to as 1. If any of those bits is already 1, you leave it as 1. So you can see that over time, as many keys are inserted into the system, a small set of bits in this particular Bloom filter are set to 1. Now, what happens when you want to check if a particular key is present in the Bloom filter or not? Well, once again, you do the same thing. You take the key, you hash it using the k-hash functions, and then you check if all of these hash2 bits are all 1s. If any of them is a 0, then you return false, saying this particular key is not present in the Bloom filter. Okay, and this is a correct answer because if that key had been inserted in the Bloom filter, all those bits would have been 1. If all those hash2 bits of this key k are set, then you return a true, saying that that key is present in the Bloom filter. This is guaranteed, well, this is not guaranteed to be correct. However, it is correct with a high probability. However, it's possible that this key was never inserted into the Bloom filter and that half of these bits were set by one other key and then the other half of the bits were set by a different key. And so you might end up returning an answer of true for membership even though that key was never inserted into the system. This is what is known as a false positive. However, the false positive rates can be tuned down to be very low. For instance, if you use 4 hash functions, 100 items inserted into a Bloom filter with 3200 bits, that's just 3.2 kilobits. The false positive rate is as low as 0.02%. Okay, so 0.02% or 0.0002 of the membership checks will return an answer of true when the real answer is false. Okay, and you can tune the false positive rate to be much lower by, for instance, increasing the number of bits that are present in the Bloom filter itself. So coming back to Cassandra, over time, a particular server might have a lot of SS tables that are written to disk, and a given key might be present in multiple SS tables. So whenever an SS table is written to disk, you don't check the other SS tables that are present on disk. So a given key might be present in multiple SS tables. So you want to look up for a particular key. For instance, a read comes in for a key. You want to look up. You may need to look up multiple SS tables, and this is potentially wasteful. So in order to avoid this waste, you do compaction. So over time, you take the multiple SS tables that are present on disk and you merge them. Essentially, you merge the updates for a given key. Okay, so if a key is present in 2 SS tables, you take the latest update for that key and you replace the older update with that latest update. The compaction process is run periodically by each server, and it is run locally on the SS tables at that server. Deletes. When you want to delete a particular key value pair, you don't delete the item right away. Instead, you write to the log or to the SS table what is known as a tombstone. A tombstone is essentially a marker that says, when you encounter this, please delete this particular key. Eventually, when the compaction algorithm runs, it encounters this tombstone, and when it does so, it will delete the particular key value pair from the table itself. Okay, now let's come back to reads. How do reads work? Well, reads are very similar to writes. Again, the client sends the read operation to the coordinator. The coordinator can contact a set of replicas. It doesn't necessarily contact all the replicas. It contacts only X replicas. X is a number, again, specified by the client. Typically, the coordinator might prefer replicas that have responded the quickest in the past. These are replicas, for instance, that might be in the same rack as the coordinator, or that might be on nearby racks in the underlying data center topology itself. When these X replicas respond, if they don't respond, then the coordinator might end up sending the read query to all the replicas of that particular key. In any case, when any of the X replicas respond, it doesn't need to be just the X closest replicas. Any of the X replicas, when they respond, the coordinator can then return the latest timestamp value from among those X. Well, the different replicas for a given key might return different values because we didn't say anything about consistency, which means that some of the replicas may have received the latest write to that key. Other replicas may still be working with a stale value of the value for that particular key. This means that when you get back answers from these X replicas for a read, some of them may be stale values, some of them may be newer values. So essentially, the coordinator looks at the timestamp of these values, and the highest timestamp or the latest timestamp value is returned to the client. Once again, what is the value of x here? We'll see again when we discuss the next lecture. The coordinator also fetches values from the other replicas for this particular key. Why does it do this? Once again, some of the values may be staler than others, and you want to make sure that these values are updated and repaired to the latest value. So if any of these values are older, then the coordinator initiates a read repair on these older values. Essentially, the read repair informs these older values, or rather the replica servers, that hey, here is the new and the latest value, the latest timestamp value that is associated with this particular key. Please update your corresponding mem table and eventually SS table. If this goes on for long enough, this mechanism will eventually bring all the replicas for a given key up to date, meaning that all of them will reflect the latest value that has been written to that particular key. For reads, however, if compaction doesn't run often enough, then a row may be split across multiple SS tables. Then reads need to touch multiple SS tables. This means that all the values or all the columns for a given row are not necessarily written in the same SS table, because you may have updated only one of the columns for a given row, for a given key, and only that particular column along with the key would be present in that SS table. So even apart from compaction, you might need to touch multiple SS tables if you're trying to read the entire row, because the row is split across multiple SS tables. This results in reads being slower than writes, but as we'll see soon, the overall system is still quite fast. Next, we come to membership. So remember that we said that the coordinator needs to know about all the other servers present in the cluster, and this is true of all the other servers as well. Every server needs to know what are all the other servers that are present in the cluster. So every server maintains a list of all the other servers present in the cluster, and this list needs to be updated automatically as servers join, leave, and fail. And this should be familiar to you from a previous lecture in the course. So essentially what Cassandra needs to do is it needs to maintain a membership list at each server. And Cassandra uses the gossip style membership list, which you have seen previously in the course. I won't discuss this in detail again. For details of this, please refer to the membership and the gossip style membership lectures earlier in the course. In addition to the gossip style membership, Cassandra uses suspicion mechanisms to make sure that when servers are being detected as failed, there is a low probability that this is a mistaken detection. So it tries to increase the accuracy of detections. For this, it uses suspicion mechanisms. This is different from the previous suspicion mechanisms we have discussed in the membership lectures. It uses what is known as an accrual detector. The failure detector outputs a value known as phi, which represents the suspicion. The app set an appropriate threshold. For instance, if you set a phi threshold of 5, this results in about a 10 to 15 second detection time. The way the phi calculation works is as follows. It takes into account the inter-arrival times for gossip messages. So if the inter-arrival times for gossip messages from a particular server have been long in the past, then it waits slightly longer for the next heartbeat before marking the server as having failed. Essentially, the phi looks at not just the inter-arrival times, but it also looks at their cumulative distribution, or the probability between when the last gossip was received and the time now, and based on that it outputs a value. When this value crosses the specified application threshold, that server is marked as having failed. Because essentially this is a fairly adaptive way of setting the thresholds for detection on a per server basis. So some servers that are responding slower than others will end up being given slightly more laxity in the sense of other servers waiting for slightly longer for heartbeats from that particular slow server. And other servers that are faster might have shorter timeouts. So essentially, the suspicion mechanisms are a way of setting timeouts adaptively on a server-by-server basis in the gossip style membership protocol. So how about speed? So how fast is Cassandra? So MySQL, which is one of the more popular relational database engines out there, on 50 gigabytes of data took on average 300 milliseconds for writes and on average 350 milliseconds for writes. In comparison, Cassandra took only 0.12 milliseconds on average and 15 milliseconds, that was for writes, and for reads, it took 15 milliseconds for reads. This is, of course, orders of magnitude faster, and this should lead you to think, well, what did we really lose? What's the catch over here? And that we'll discuss in the next lecture.
Hello everyone, in this video I will talk about a key value store called Redis. Now, Redis itself stands for Remote Dictionary Server. One question that you might ask is, why are we talking about Redis? What does Redis do? Redis is an in-memory key value store system, and it can be distributed. So what I mean by this is that the data model that it interacts with the user is you give it sets of key value pairs, and it just stores them in memory. Very fast, very quick. It's open source, written in the C language. It's very quick. Data model is basically a dictionary. It's kind of like, you can think of it as your classical hash data structure, which maps keys to values. Now, it supports strings, and it also supports numbers. It actually internally looks at numbers as strings. But it also supports some other abstract data types for values. You can have lists of strings. You can have sets of strings, which is just a collection of non-repeated, unsorted elements. You can have sets that are sorted. So in this case, the system guarantees that if you put different items that are repeated, it will just keep one of them. And in the case of a sorted set, it will also have a floating point number, which we call score, and we assign one score to each. Finally, you can have hashes, and this is actually very interesting. So Redis itself is you can think of it as a big distributed hash, in-memory hash, right? So you give it a key, it returns a value. Now that value itself can be a hash. So you can give it a key, returns a value, the value is a hash. Inside that, you can have key value pairs. So it's actually quite useful when you want to design or architect your systems. The thing about Redis is that it's really, really fast. It has the response time is really fast because everything is stored in memory. The system is written using non-blocking I/O, single-threaded, and it can have hundreds of thousands of read-writes per second. So rarely, if ever, you will have Redis be your bottleneck in your system. Now, there are, of course, downsides to it, and I'll get to that. But it's in memory, but it periodically checkpoints the in-memory values to disks every few seconds. I think the default is every 2 seconds. You can change that. If there's a failure, as you can imagine, only the very last 2 seconds or whatever amount that you define for checkpointing period, only that amount of data might be lost. Everything before that are checkpoints on disk. Potential uses for Redis is where, for example, you want to have a session store. A user comes in, interacts with your website, you start a session, you're pretty sure that this session will finish in the next 10 minutes or so. You might as well keep everything in memory, especially if you have you want to, for example, create with a PHP script or whatever a web page for a user, and if you know that that web page can be accessed by many different users, you don't need to recreate that page every time. You can actually create that page, put it in Redis, and then where you have many reads and few writes, Redis would be very perfect use case for this. Or whenever, for example, you have data that you don't really care about, throwaway data, temporary data, or timeouts, you just put them in there. Similarly, if you want to do like very rapid, low latency logging of some events in your system, and latency is important, Redis would be actually a good use case. One important thing is that the amount of data that Redis can store is limited by how much memory you have in your machine, and in case you want to distribute Redis across your cluster, how much memory you have across all of your machines, right? Because the whole idea of Redis is that it's very good, it's very fast, while everything is in memory, right? So things have to fit in memory. If it doesn't, then Redis cannot handle that. So it's not a truly big data database. In general, data that you don't mind losing, records that can be accessed by a single primary key, and you always have to have a primary key to access your data in Redis when you have a schema that is either a single value or a serialized object, and you can have the serialized object as a string and then store it in Redis. So that's good. But again, it's not a general database. That's the reason people even don't call it database. It's called key value store. So the programming model is quite simple. There are libraries for a lot of different languages. You name it: Java, Scala, Python. Many different languages have simple programming model for it. You can get a key value, set a key value. It allows you to atomically increment, decrement without requiring to read a value and then increment it in your program and set it again. So you can just increment, decrement, check whether a key value exists. And then similar, so this is for just regular numbers, the first line. The second line, kind of similar access pattern, but now for hash sets. So you can get a hash set with hget, set it with hset, check for the set of keys that are in a hash set using keys. The third line, we're talking about lists, so set. So when you want to add an item to a set, you do sadd, set add, set removes an item from a set. And you can check the members, set of the members of a set by S members. And finally, Redis allows you to do publish subscribe. So basically, client can say, I want to subscribe to a certain key. And then when another client comes and publishes a value to a key value to Redis, Redis actually goes and notifies the client that, OK, there's a change. So without further ado, I'll let you move to a demo video that shows you how you can interact with Redis and see how easy it is to work with it. Hi, everyone. Let me show you how we can interact with Redis. Now, in my video, I talked about how great Redis is. It's a key value store. It's extremely fast. You kind of need to know what sort of a data model you're interacting with. But the whole idea is that if you know what keys you have set and what sort of a data structure you're returning from your keys, things should be very fast and efficient with Redis. Here I'm actually running the Redis server here in local mode, but it's fine. And now it's listening on port 6379. Now, any other client that I write that connects to this port, in this case, my local machine's IP address or whatever IP address that the server is running on, would be able to run commands. Let me show you how these commands kind of work. In this case, I'm going to show you the command line interface. There are, of course, programmatic interfaces that if you're writing your program in Python, in Java, in Scala, pretty much any language that you can think of, there are libraries that you can load, and then you can kind of use very similar commands to work with Redis. But let me bring up the Redis command line interface. For you old-timers, it kind of works, at least the command line interface kind of looks like Telnet used to be. So you give it commands, and it basically runs the commands. If you remember from my slides, Redis basically works with key value pairs, right? The keys are unique identifiers. Now, the values can be different data structures. They can be strings or numbers. And numbers are really stored as strings. And you'll see in a minute. Your values could be lists, could be sets, or could be hash tables. What is a list? List is a number of an ordered set of strings. Set is just a bunch of values. They're strings in Redis. You can have sorted sets, and we'll look at that in a minute. Or you can have hash tables. So you use a key to access a hash table, And once you get that, you can actually give another key and get a hash table and get your value out. Let's start actually by giving it some commands and see how it works. So the commands in Redis are kind of very are named very accordingly. So you have set and get and delete, right? So to be able to set a key value pair, and let me zoom in a little bit, I can just set something. So I can say set name to Bob, and I will just say OK. By the way, again, I want to emphasize that like a single Redis instance can handle hundreds of thousands of these commands a second. So you don't definitely need to always interact with it in command line interface. These can be commands that your program sends to it. Now, if I actually just want to access my key value, I can say, what was the name? Get name. And it says Bob, right? So I can now change it. I can say, hey, change the name to John. And now if I get name, it becomes John. Another command useful is delete. So I can say delete name. And then if I say get name, now the name, the key value pair whose key was name isn't there anymore. Same thing with numbers. You can actually set number to 1, 2, 3. And of course, I can get the number. See, now the number is stored as a string. But once you have numbers, numbers have some interesting commands that you can interact with, and they're increment and decrement. So you don't necessarily need to get a number and add it in your program and send it back. You can just say increment number. So I can say increment this number. Now, if I get the number, it's 124 now. Same with decrement number. If I get it, it's back to 123. Of course, I can get the length of a string. That's easy. So let's say set my key as quick brown fox. Get my key quick brown fox. Now I can say string length of my key. And it goes and counts and says, OK, this is 15 characters. One interesting thing is I can check to see if a certain key exists or not. So I can say exists. And let's give it like a bad key. So let's type your key. It says 0. That means no, it doesn't exist. But if I say exists my key, it will return 1. That means that yes, that key value pair exists in a database. Now, one interesting thing is the server, again, the server is running separate from this command line. Different instances of programs that are interacting with this server can come and connect to it. So if I actually exit my command line, and if I go back here, nothing should be reset. All my key value pairs should be running because, hey, my server is still running on this other tab, right? So if I check my key exists, it says yes. If I say get my key, the quick brown fox is still there. That's the whole point of a key value store. It's typically used in Lambda architectures, for example, in streaming systems for storing the data set. After working with individual key value pairs, now let's look at some more advanced usage. Let's talk about sets. So I can have a set, and you do that with set add. So let's say I have a set of tickers, for example, stock tickers. And let's say we have a whole bunch of stock tickers here. So now I'm adding Google, G-O-O-G, to my set. If I say set members, it says at the moment I have one item in my set. Now, what if I now add, say, IBM? Now I have 2 items in my set. And you can have a whole bunch of other things as well. I can have NASDAQ. And I can have Dow. And if I get the set of members, now it returns all of them. I can also remove something from the set. So I can say remove from the set of tickers IBM. Now IBM is not a member of that set anymore. So as you can see, Redis can have keys and key values. For values, it can be strings that we've seen so far. It can be a set. And now it could be a sorted set. So for a sorted set, instead of saying set add, I say z add. So let's call it another set. Let's say set z add sports. And let's give it a rank. So let's say football. And let's say z add sports to hockey. And then I can interact with my sorted set now, and I can say, give me a range from the set sports, say from 1 to 2 with scores. So now we can actually give it a range, and it can then go and give you back the results sorted 1 to football, hockey. Even more interesting use case is using a hash set as the value here. As you can see, having key values, actually the whole idea depends on hashing mechanism. So I can extend this very powerful idea to values itself. So a value itself can be a hash set. So now instead of getting just string back, I'll get a whole hash set back. So let's take a look at, let's see, if I have a hash get, and let's give it a users. So it doesn't have at the moment users. So let's actually start giving it some values. So let me clear. Now I can say hash set. Let's say I'm trying to create a key value database inside my Redis and call that database users. So what I'm doing here is I'm saying, hey, let's actually create a hash set, call the hash set users. Inside it, have a key value pair. The key is name, the value is Bob. And now I can actually now do another thing inside this hash set. So I can say, now inside this hash set, I'm going to put another key value pair. Let's say age. And let's say Bob is, let's say 30 years old, right? Now I can actually ask for it to give me the set of keys in that hash set. So I can say, hey, go find this hash set users and tell me what keys I have in there. Sorry, H keys. There we go. So now it says in the hash set that you define as users, you have two different keys, key name and key age. Now I can interact with that. So I can say, OK, hget for that user from that user's hash set. Now I need to give it a key inside the hash set. So let's say age, and it says age is 30. If I ask it to give me the value for key name, it goes and finds the value for that and returns me Bob. And of course, I can go and delete individual items. So I can go and say hdelete inside users the key value whose key is age. And it will say, fine. Now if I ask it to show me what keys I have in hash set, it just has name. So you can think of it as, for regular key value pairs, I use get or set. For sets, I can use for hash sets, I can use hget or hset, and similarly for sets, I use S. Of course, I don't use sset, and I use sadd and smembers. I think that this is good enough. There are some other interesting things in Redis. There's lists that you can push things on a list and get a range again. There's the whole idea of kind of publish subscribe, which kind of gets you to some sort of a similar functionality as another system that we introduced in a different video, Kafka does. So here you can say, hey, I want to subscribe to a certain key, and then if another user comes in and creates a key value pair with that key, the person who has subscribed will receive that. And then, so another interesting thing that I'm not again going to show is the idea of expire. So you can actually set a key value pair inside Redis and then give it a expiration time in seconds. And then after a certain value, that time is gone, the key value pair are removed. So, but I think you get the gist of it, and it's very easy to interact with Redis. Similar libraries exist for a lot of programming languages. In this video, we will talk about HBase, kind of introduce the idea, and introduce the API of how we can use HBase a little bit. Of course, we have a tutorial about this, so I would strongly suggest you take a good look at our tutorial as well. HBase is a distributed data store. Now, what makes it very interesting is that it is built on top of HDFS. Now, of course, we talked about HDFS. It's a distributed storage, distributed file system, provides very interesting capabilities. We can store terabytes, petabytes, exabytes of data on HDFS. We can just easily scale HDFS by adding nodes to our cluster. That's called horizontal scalability, which is very great because you just need to buy one more machine, get a little bit more performance. Buy more machine, get another bit of performance. So it's great. What HBase does is it builds on top of HDFS and provides a sort of a database system. So not only a file system, but a database. It's an Apache open source project. It tries to provide storage on top of Hadoop distributed computing. And you can store data logically organized into tables, rows, and columns. It's part of the Hadoop's ecosystem. So this is some sort of a Hadoop ecosystem we've seen before. On the bottom, you have the HDFS distributed file system. We talked about MapReduce in our second week of lessons. You have Hive, which we talked about. You have Pig for writing scripts on top of MapReduce. We talked about Zookeeper as a way, or we will talk about Zookeeper as a way to synchronize and coordinate between tasks or data storages, and it provides very strong consistency guarantees. HBase is also part of this whole ecosystem, built on top of HDFS, and as a result, the HBase files are internally stored on the HDFS file system. So the question becomes, what's the difference between HBase and HDFS? When would you like to use HDFS, and when would you like to use HBase? HDFS is good for batch processing tasks. When you want to basically scan, or your algorithm scans over the big files, right? So what you want to do is open a file, read from the first record all the way to the last record, do something with all of these single reads, and then close the file. It's not good for record lookup. You can't just randomly access a file. It's good for scans, not record lookup. It's not good for incremental additions in small batches. It really likes large files. The minimum chunk size in HDFS is 64 megabytes or 128 megabytes. So if you have a little bit of information in a record, personal record, for example, name, address, something, it's just a couple of bytes of data, HDFS is not a very good fit. And it's not good for updates. It does not support in-place updates of data. Now, HBase tries to address the above points. In the next video, we will see that how HBase does that. But let's keep it in a logical way, in a box for now in this video. It provides fast record lookup, supports for record level insertion. So you can say, hey, go find this record, and then between this and the next record, insert a new record. You can do that in HBase easily. And it allows for updates. So you can ask it to say, go find this record. This is a key. Go find the record corresponding to this key, change it, and then come back. HBase allows you to do that. HDFS does not. The data model in HBase is basically designed on top of designed based on the data model presented in a paper by Google called Bigtable. Basically, HBase is an open source implementation of Bigtable. So if you're interested in reading more about the Bigtable's, the HBase's origins, you can take a look at the Bigtable paper. Just search for it on any search engine, Bigtable paper, and you can see that. So a table in Bigtable or HDFS, or HBase, sorry for that. A table in Bigtable or HBase is a sparse, distributed, persistent, multidimensional sorted map. Now that's a mouthful of a description. But let's take a look at this and see what it means. Let's take the easy stuff first. Distributed, okay, your data is distributed across multiple nodes. It's persistent. So when you store something in HBase, you can be sure that the data remains there. If a node fails, the data is guaranteed to be there. It's sorted, so your tables, the data, is always kept in sorted order. It's sparse. That means that not all the records need to be completely filled. You basically just take what data that the user or you give it, and it just stores them. And it's multidimensional. And the reason I say it's multidimensional is because a record can have multiple versions. You can have version 1, version 2, version 3, and so on. And we will see that. You can think of it as a huge distributed map, like a hash map structure. It's a map, and it's indexed by keys. The key would be a row key, or you can use a column key. And more importantly, you always have a timestamp, right? So what you can this is how you access your data. You you give it the key for your row, the key for your column, and the timestamp that you require. And why do we have timestamps? Because when you make an update to HBase, it doesn't quite delete the previous version. It just creates a new version of the record and puts a new timestamp on top of it, so that you can actually always look back at the history of your record and see, okay, version 1 at this time had this contents, and then version 2 at another time came in and changed the contents to another thing. HBase supports lookups, so you can look up for a certain piece of data. You can insert a new piece of data. You can delete an existing record. So looking at the table schemas, what HBase does is each schema, that's a database schema of your database, it consists of several tables, right? So you can have table 1, table 2, table 3, and that's not something new. A lot of databases do that. Now, each table has a set of column families, right? So let's, for instance, take a look at these. In this example down below, roles here is a column family. Info is a column family. Inside this column family, you can have different columns. So for example, for info, you have column height, you have column state. Now, columns are not necessarily part of the schema. What do I mean? I mean, different records can have different columns, right? Column families remain the same, but not the columns. So that's why we call the columns in HBase to be dynamic columns. In other words, the column names are encoded inside the information, inside the cells. And different rows or different records or different cells, they can have different columns inside their column families. So in this case, for example, in my first record, the roles column family has 2 columns, ASF and Hadoop, while in the second record, the roles column family has a whole bunch of other columns. So it has column Hadoop, column another Hadoop, column Hive, so on and so forth. Now, well, of course, it had 2 columns, Hadoop and Hive. The interesting thing here is that, as I said, records in HBase can have timestamps, and I'll talk about it in my next slide, but you can see that different values can be present inside the column family with different timestamps, like timestamp 2010 and 2011. Now, talking about the timestamps, it's a version number. It can be user supplied. You have complete control on it. It doesn't even have to be inserted in increasing order. So you can say, first, in the example from the previous one, you can first insert this information and then insert this information. But version numbers are unique within each key. So inside this one key, right, you can only have one timestamp 2010 within this role. Tables in HBase can be very sparse. That means that a lot of cells or a lot of records can be empty, and there's no reason why we can do that. Keys are indexed as the primary key. So basically, okay, so let's take a look at this example. You have a row key here. In this case, we have one row key, we have multiple things. Why do we have multiple records? Because each one of them has a different timestamp. Timestamp 3, 5, 6, 8, 9, whatever. And then inside each record, we have certain column families. So one column family is content, another column family is anchor. But inside, we can actually have different columns for each of these, and it's totally up to the user to decide what column to use. As mentioned earlier, the rows in HBase are always stored in a sorted order, and therefore the applications that you write can use and exploit this property for efficient row scan. So you can always assume that when you want to scan a certain range of keys stored in HBase, you can always assume that they are sorted, and you can use this in your algorithm. And the row ranges are internally partitioned into multiple tablets, and in tablet it was what we call in Bigtable. In HBase we would call it an H region. But that's an internal thing to HBase. From your point of view, you have a range of rows. In reality, they're dynamically partitioned within different H regions and stored in different nodes in the cluster. As mentioned before, columns are actually grouped into column families. And the idea here is actually it provides locality hints. The column key would be written in this format. You can have family, colon, and then a certain qualifier. And as mentioned before, the qualifier can change between records. It's up to the user to use whatever column that they want. All right, so to summarize, HBase provides basically a database model of rows, records, column families, columns. You can put your database schema based on a bunch of tables, and inside each tables you can have column families and records of data. And it provides you with functionalities such as record lookup, record insertion, record deletion, and more importantly, record update. And all of this is running on top of HDFS. Therefore, you can process huge amounts of data. We're talking about terabytes, petabytes of data that you can access as a database system using HBase. So it's a very useful system used throughout the industry today. And we have prepared a tutorial for you to go and figure out how to work this database system in your own applications. We have, of course, machine problems for you to solve. And in our next video, we will talk about the internals of HBase, how it achieves the magic that it does, how it can do record lookup and updates and in-place updates and still write its data on top of HDFS. Hello everyone, in today's lesson we will be talking about HBase. Now HBase is designed to work on really large data sets. Of course we're talking about big data sort of schemes, so hundreds of gigabytes, terabytes of data that needs to be accessed, and it has certain requirements that necessitate the design of a database system such as HBase. Now, before I get into talking about the HBase itself, I should mention that HBase, as an Apache open source project, is built on top of ideas presented in a paper by Google. The paper talks about a system called Bigtable. It's Google's internal database system. And they presented the idea behind the Bigtable in a paper. People decided that, oh, this is actually an interesting system, therefore let's go and implement it in an open source system, resulted into HBase. So whatever I talk about today, you can, for more information about the design of the system, you can also go look at the Bigtable paper. That is actually a very interesting read. So let's take a look at this diagram about HBase. We have a master node, like a lot of other cluster designs that we've talked about in the course and we will talk about later in the course. We have a master node that synchronizes everything. We will talk about how it does its functionality. There is a Zookeeper instance, and the Zookeeper instance here is used to maintain synchronization between the different nodes, so that for limited amounts of synchronization data, different nodes have the same view. And of course, you have a client that can talk to your HBase cluster and get services from this huge data store. Now, of course, when you're talking about a big data distributed system, you have individual nodes doing things. In this case, each individual node is running an H region server, and we will talk about these as well. And inside each H region, you have a couple of store files. H files are stored in store files, and we will talk about those. There's a mem store for each, for each store that can basically cache an H file. We will talk about those. Now, another thing that I want to show in this diagram before moving on is that HBase is built on top of Hadoop Distributed File System, HDFS in other words. And that's basically how it does its big data magic. HDFS is capable of handling terabytes, petabytes of data, and HBase builds on top of HDFS. All of the stuff that we see here with H files and mem stores and H regions and these things, they are basically there to add a little bit of functionality on top of HDFS so that we can provide functionality that HDFS can't. Like for instance, HDFS, as we talked about in previous lessons, is very good for doing serial processing on large chunks of data, like 64 megabytes of data. What if you require to go and find one record of data? And that's the sort of functionality that these H regions and H files and everything else provide on top of HDFS to be able to handle those. Okay. So as I said, HBase is built on top of some building blocks. You have HDFS, you have Zookeeper, which uses the ZAB, the ZAB protocol, Zookeeper's Atomic Broadcast Protocol. And the next important building block, which we'll start talking about, is HFile. HFile is really the basic building block of HBase. What it is an on-disk file format, right? So it's a chunk of data that is stored on disk, on HDFS, and it represents a map of keys to values, a map of strings to strings, keys to values. It's persistent, which means the data is stored on hard drive. Therefore, if the whole cluster crashes, you can actually bring the data stored on it back upon recovery. The data is stored in an ordered format. So data is sorted and then stored. And the data in an H file is immutable. So once the data goes on HBase, on an H file, you don't change it, like in place. You can, what you can do is you can remove a whole H file and replace the whole H file. But you don't go and get into an H file and then change a couple of bytes in an H file. And as I said, an H file is stored in HDFS. So an H file looks like this. You have a file stored on disk. It has a couple of data chunks. Now, for instance, the data chunk can be 64 kilobytes of data. An H file typically has a lot of these blocks. Maybe, I don't know, about 1,000 of these blocks can be stored in one H file. So it has a sequence of blocks. Aside from that, it also has an index. And the reason it has an index is that if we want to look up a certain data, we can, instead of going and searching throughout the data, we can use the index to quickly figure out, OK, the data is stored here, the data that we want, and go grab it. Now, one interesting thing about H file is that it's stored on disk, but there is an equivalent data structure in HBase called memstore that looks pretty much similar, but is only stored in memory, right? And this is how basically HBase does its magic. What it does is that when we want to read like a certain data from an H file, it goes and finds the H file and then loads it up into memory by creating a memstore, filling it with information from the H file. Then it keeps it in memstore. the next time you say, hey, go and change this one record, it doesn't go to and change the record in the disk. It goes and changes the data in the mem store, in memory. Once it's done, it goes and replaces the H file with what you had in memory. So it copies the mem store back to H file. And that's how basically HBase does its magic, does both big data and can do record-based processing. OK, so back to H file. It supports a couple of different operations. As I said, you can look up values associated with a key. So you can ask an H file, hey, give me the value for this key 1 item. And it uses the index data structure to figure out which of these blocks has it and goes and finds the information and returns the key to you. Another thing that it can do is it can iterate on key value pairs. So what you can do, you can ask it, is saying that instead of finding key 1, you can give it a key 1 and key 2 range. And it will, and remember that the data stored in H file is ordered, so it's sorted. So it can go and find where key 1 is stored. It says key 1 is here. Where's key 2 stored? Key 2 happens to be here. OK, iterate on these values. So it goes and does a certain operation on all of the items in between these two keys. OK, so now we have defined an item called H file. Now, coincidentally, I should say H file, and H file is about 64 megabytes, 128 megabytes. It matches a chunk on HDFS. Remember from back in our previous weeks where we had our lecture on HDFS, we talked about the chunks on HDFS. And each chunk would be 64 megabytes or 128 megabytes, depending on the usage. So each H file typically corresponds to a chunk on HDFS, right? Now, the next thing I want to talk about is an H region. What it is, from a logical point of view, is that it contains a range of rows, a range of keys, and it's dynamically partitioned. So you can actually change the information from what key to what other key is stored in an H region, right? What it really is you take multiple H files, maybe 100 H files, I don't know, maybe 1,000 H files. You put them together on one machine in the cluster, one node in the cluster, and you call that an H region. If you were to look at Bigtable's paper, this would correspond to what Bigtable calls a tablet. So in a region, what you have is a couple of these H files. And they are all sorted. So now you can, for an H region, you can have a start and you can have an end key. And we'll see how this is used in a couple of slides from now. OK, so we have H regions, which correspond to different nodes in our cluster. What about the master? Of course, we have this thing called an HBase master. It's the master node in the cluster. What it does is it assigns H files to H region servers. It can detect an addition or expiration of H region servers, H region server being cluster nodes. So if a new node is added to the cluster, or if a node fails for whatever reason, it detects that and considers the added or removed node from its calculations, assignments, really. One important thing that HBase Master does is it tries to do load balancing for the different servers in your cluster, right? So what HBase can do is try to randomize the location of different H regions throughout the whole cluster. And therefore, it uses this randomization algorithm as a sort of load balancing scheme. Aside from that, it can also handle the garbage collection if a certain, say, H region or H file is removed. It can go and remove them from memory or from hard drives. And if there's a schema change in the database, it's the HBase master that decides, OK, now there's a new schema. I should tell my HBase servers that, OK, there's a new schema, make changes to your H regions, and so on and so forth. So, of course, we talked about H regions, HBase master. Now we have H region servers. This is the daemon program that runs on each node of the cluster and manages a set of regions on the machine, right? So you remember, so we said, just to clarify, you had H files that maybe was 64 megabytes, maybe. It had a whole bunch of 64 kilobyte chunks of data. This was an H file. Inside an H region, you could have a couple of H files. And then in one machine, which an H region server is managing, you can have multiple H regions. H regions. OK, so there's typically between 10 regions or maybe up to 1,000 regions per machine. So you can imagine that there's maybe up to maybe a terabyte, maybe 2 terabytes, couple terabytes of information stored in one machine, and it's distributed according to this scheme that we talked about. An HBase region server handles read and write requests to any of these regions, and if an HBase region, an H region, is grown too large, the H region server itself can decide that, OK, it's now time to split this H region into 2 files, and just then tells the HBase master that this file is split into 2. It can also decide to merge things. One question that you might have at this point is that, OK, we have this large cluster of H region servers, and there are large H region files stored throughout the cluster. OK, I'm a client. I come to the system and I ask it, find this certain key for me. How would I know which one of these machines I should go to? One very simple naive way is, hey, let's ask every node whether you have that or not. But that's just unnecessary load on all of the nodes in cluster just to find one record. The better way, and this is how it's implemented in HBase, is that within Zookeeper, we have a set of metadata. What happens is that when we want to find a certain key, we start by looking at a certain master index called root region, right? It's a region, therefore it's one of the typical region, H region files in HBase. So it's not something totally new. So we go into that, we say, hey, I want this certain key. It goes into this its own database and says, I don't know about your key, but I know about a couple of meta regions that was introduced to me. And looking at the key you have and knowing that everything is stored in HBase, I can go and figure out that your key is between such and such range, therefore it fits into my meta region. Then you go to the meta region and ask it, where is my key? It says, OK, I know all of everything about my user regions, and your key happens to be inside this user region. Then from this 3-layer scheme, you figure out, oh, it's in that user region. Then you go contact the H region server machine that has that user region and ask it to give your key, to find the value for your key. One major question that needs to be answered is, how do we assign an H region to one of the H region servers? What HBase master does, it keeps track of a set of live nodes in the cluster. So it knows a set of live H region servers. And when there's a new H region, it can assign it to one of these H region servers through some sort of a randomized scheme. It also knows and always keeps track of the set of unassigned H regions that need to be assigned in the next round of assignment. And you can imagine the HBase master continually does this. It continually keeps track of unassigned H regions and assigns it to somebody else, then sees, oh, there's a new unassigned H region, let me assign it to someone else. Each H region data file is assigned to only one H region server at a time. And as a result, the H region server that contains a certain H region maintains a lock, exclusive lock, in the Zookeeper system. And this is the way that an H region server says, hey, you know what? I have this H region, and please nobody else claim it or touch it or try to do anything with it. What the HBase master, on the other hand, monitors these H region servers, monitors the Zookeeper directories, and if it sees that, okay, there is an orphan H region, for example, or there is a new H region that is unassigned, then it tries to handle the assignment. If there is a change to an H region structure, like for example, you have table creation or deletion, or merging, these instances are handled by HBase master. So if, okay, the user says, I want to create a new table in my whole database. The request goes to the master then tells everyone all of the nodes, all of the HBase region servers. This is the same with merging. If you have two H regions that, for example, assume in the beginning each of them was 64 megabytes in size and everything is good. Now, user just started to remove records from each of these two H regions. At some time, the first H region is now down to 10 megabytes. The second H region is down to 12 megabytes. It's not very efficient to store 10 megabyte files on HDFS that wants to keep 64 megabyte chunks for each file. And as a result, the master can decide that these two H regions need to be merged together, and it tells the H region servers that contains those H regions to start a merging process. As I mentioned before, the splitting action happens the other way. The H region server decides that a certain H region has grown too large, and it tries to split them and then tells the master that this H region was split into. So the last thing I want to talk about in this video about HBase is the in-memory representation for H region. This is basically how HBase does its magic, right? It can read records, it can modify records, it can change records on really large databases. So what happens is that, as we talked about, H regions contain a whole number of H files, and each one is stored on HDFS, right? And if you remember from our lecture on HDFS back like last week, you know that in HDFS, you do not have random access to contents of HDFS. You cannot just say, read this location of the file stored in HDFS and change it to that. Just HDFS doesn't support that. But HBase does. So the way it does it is by using this in-memory structure called a memstore. When you want to write or read from an H file, it instantiates a memstore object in memory. And since it's in memory, you can have easy random access to it. Read a record, overwrite the record, again overwrite the record, or again overwrite. Doesn't matter. It's all in memory random access, right? So you have this write buffer that is in memory, and you also have an append-only log on HDFS. Now, both of these components are necessary. When there is a read operation comes, the first thing that we do is check to see if one of the current in-memory objects, one of the current in-memory memstores, contains the record that we want to read. If that's true, then we can actually just return it from memory. If not, if it's not in memory, then we revert the access all the way down to H file and then return it. Right? So what about when a write comes? The first thing that we do when a write comes is we write this write operation in an append-only log. So the log will contain a new entry saying write for key 1, new value 1. And then the next time another write comes, we just append another entry, write key 2, value 2, and so on and so forth. And then, and I'll tell you in a second why we do that. And then the next thing that does is that after doing the append-only log, we go and change the record in the memstore, right? So we change the record in memstore. The next time there is a read request coming in, the read comes in, it sees that there's this H file is now already changed into a memstore object, and it just reads the new contents of that record and then returns the value. So everything works fine. Question is, why do we do this append-only log? And the reason is that HBase tries to provide persistence storage. So if a node fails, it has to guarantee that the information stored are kept there, right? If information was already stored in an H file and a machine fails, fine, it's already on HDFS, it's on hard drives, it can reload it back. But what if information is stored in memory and the machine fails and it's not stored back in an H file? In that case, when we restart that region server, we load the log from HDFS and then replay this log. When we replay this log, all of the changes will take place again for this certain memstore. And then, therefore, we can actually provide persistence storage guarantees through HBase. All right, so HBase is a very interesting system. To sum it up, it works on a distributed cluster with HBase master, multiple nodes, H region servers, and it relies on Zookeeper and HDFS to do its big data storage system. Hello everyone. In this video, I will talk about Spark SQL or Spark SQL, as some people would like to pronounce SQL or SQL. So of course, we are talking about the domain of NoSQL databases. And remember that NoSQL doesn't mean that a database is not SQL. it stands for not only SQL, right? But in previous videos, we've talked about all the theoretical backgrounds of why you need consistency, relaxed consistency sort of things. And Spark SQL is also one of those database schemes that kind of fits into that big data NoSQL structure. What Spark SQL allows you to do is to do structured data processing in Apache Spark, right? Now, of course, throughout the course so far, we've talked about Spark a couple times. We started the course with talking about Spark, so you actually have experience seeing how RDDs are used to represent data, and you can take data, put in RDD, it gets distributed across the cluster. A lot of nice things are provided by the framework: resiliency, fault tolerance, distribution. All of those things are nicely added. So the idea here is that since we have that nice engine, can we make that engine work with databases, work as a database with data that is stored in sort of a other more traditional NoSQL database? Here I'm talking about, for example, data that is already in Hive tables or in Parquet files stored on HDFS. Parquet is a format for storing databases. Or data that is stored in JSON format, or vice versa. Basically, can we try to use Spark to access that sort of data and query data? And the answer is yes. Of course, you can do that. The trick and the key here is RDDs are just very general. The framework doesn't really know what you will put in an RDD. An RDD is just a blank data structure. So you need to provide more information about the columns of the data that you will have in your tables. This is what classically we refer to as schema, right? Database schema. If you have this information, the framework can try to optimize access patterns, try to run optimized code to do queries on your data. As we will see, Spark allows you to do that. You can get the data inside data sets and data frames, and I'll talk about those. But underneath data sets or data frames really is just plain old RDD, right? So you can, the nice thing here is that you can switch back and forth between SQL for, if you know how to write SQL queries, select statements, and we'll see how, we'll have examples. Or switch back and forth to regular programming languages, Python, Java, Scala, whatever. And this becomes a very powerful tool. You don't need to shoehorn everything into SQL select statements. When SQL select is going to work better, you can just use select. When you think you want to write a function, you might actually switch back to regular programming language like Python or Java. Select the SQL language, for example, has this notion of user-defined functions. And of course, it's supported here in Spark SQL. But once you get to that point, you might want to ask yourself, do I really want to go through the trouble of defining the SQL user-defined function UDF? Or do I want to now switch back to RDD and deal with the data set as an RDD, and then again, when required, switch back to, for example, select statement. So it's up to you, but it gives you this flexibility, and it's it's a very good implementation. It has a strong query engine. Most of the times, the query engine is so optimized that it's faster to write a select engine than try to write your own filtering, for example, logic in the programming language. So there are two main ideas here, two main data types. One is data set, and the other one is data frame. Data set is a distributed collection of data. It's really basically built on top of RDDs. So it provides all the benefits of RDDs, like the typing, the ability to use Lambda functions with, like, you say RDD.map or flat map, and then you give it a Lambda function, so you can just do that with a data set. or you can switch it back to the Spark SQL's execution engine. Data set can be constructed from JVM objects, so basically any hash set, list set, whatever that you have, you can then construct it, change it into a data set. And you can then use map, flat map, whatever. At the moment, at least, as of version 2.0 of Spark in 2016, the dataset API is only supported in Scala and Java. Python doesn't currently support it. But of course, due to Python's nature itself, a lot of the benefits of datasets are available in Python. So you can actually go and access fields in a dataset using Python's language, and Python can support that. But then the other data type for Spark SQL is data frame. A data frame is really built on top of dataset that I talked about in the previous slide. But it's organized into columns that have names, right? So now we have applied the schema to the data. We can think of it functionally as equivalent to a table in a regular database, or Python language or R language. They have data frames coming with them, so you can think of it as just basically a table. Data frames can easily be constructed from a lot of different sources. You can basically load them if they are already in structured data file or tables in Hive. You can connect to external databases, Oracle, MySQL, and through JDBC interface, read off them and get a data frame inside Spark environment. Or if you have an existing RDD, and that's very powerful, you can switch that RDD, change the RDD into a data frame. There are different ways of doing that. You can either ask the system to try to infer the schema itself, and it tries its best, or you can programmatically set the schema one by one, the columns yourself. The data frame API is available in most of the languages, Scala, Java, Python, and R. I would like to show you a demo on how data frames are easily accessible in Spark SQL and how easily you can query data, whether it's in RDD format or in select SQL format. Let's take a look at a demo of how you can use Spark SQL in Spark. Now, to run this simple example, I have a input file here. It's called people.json. Let's just take a quick look at people.json's content. You see it's in JSON format, so it has brackets here and there. Inside each record, you have a name and an age. One of my items doesn't have an age. So just taking a look at this. All right, so let's get out of here. Let's bring up PySpark, which is the interactive Python shell for Spark. One thing to notice before I start is that in version 2.0, which is the latest version of Spark, they've slightly changed some stuff, a whole bunch of stuff. There used to be like a Spark context and a Hive context before was available in the shell as SC and Hive context. In a previous video, which I didn't actually require to use any of those, I might have mentioned that Spark SC and Hive context. Now in the newest version of Spark, there is just one object Spark session that handles everything. So just pointing out. First thing I want to do is I want to read the JSON file inside the Spark environment as a data frame, and then try to interact with it. Let me see. I'll say data frame equals Spark, which is just this object that is a Spark session and is available. If you're writing a program, you have to initiate an object of this class type. But in the shell, they've already done that for us. So you can say from Spark, I want to read JSON file, and my file is people.json. Usually takes a bit of time to read the data because it has to read the stuff as an RDD, and then it needs to go and infer the schema and everything. Usually takes a bit of time, but now if I say the data frame show, it will show a first couple of elements in my data frame. Now in this case, as you see, it has nicely figured out that okay, I have two different columns, column age and column name. One of my items, as you remember, had a name but didn't have an age, so it's populated that with null. And then the other ones, it's figure out Andy is 30 years old and Justin is 19 years old. So you see how easy it is to get a JSON file into Spark. This is similar to if you had a Parquet file that's a compressed data file format that it's very common for storing data on HDFS. So you could do that. Or Hive, if there was Hive files and you had Hive processes, now you want to port your Hive database into Spark, you can just point it out to Hive. And same, again, it's very easy to load that stuff. All right, so now that I have my data here, I can try to interact with my data in two different formats, right? So one way is to just use programmatic interface. Data frame is a data type in Python in this case, and I can use Python functions that come with that object. So in this case, for example, I can say .select. This is a function that is implemented for this object, and I can say select field name. Now, this statement here returns another data frame. And as we saw, we can call function show on a data frame. So now I can say show this new data frame for me. So it will just select the name part and return everything back. As I said, this is the way to programmatically interact with the data frame, kind of like an RDD. There is another way, and this is a very nice way of interacting with stuff. You can basically create a window, create a temporary window, and register it as a table. And then once you do that, you are able then to interact with classical select statements. So let's see how that works. So I can say this data frame that I have, this whole data, I want to create or replace temp view, and I want to call this table people. And it goes and does that. One thing I want to mention is that this temporary table that you're registering with Spark, the lifetime of this object, is this table, is limited to the lifetime of the Spark context object that you've created. So in this case, since the Spark session is available for this session of interactive working with Spark, this table will remain available throughout this session. Okay, so now I have registered this data frame as a table. So now I can say spark.sql, and here's where the magic begins. Instead of doing select, I can just say, I'm going to give you a SQL query and go figure out what I mean. So from here, it becomes your standard SQL, right? So I can say select everything from people. People is now registered as a table, and this is a standard SQL query. This whole thing is going to return another data frame, so I can say show. So see now, it now goes and returns the whole thing again. This is actually quite nice, right? Because I can now start doing all the select statements that a lot of people from database background already know, right? So I can give it a filter where age, for example, is bigger than, let's say, who's eligible to vote, for example. In this case, only Andy is eligible to vote. Let's see if I can only get the name of people that are older than 21. It just returns the name. This is about as much as I want to show you for how you can interact with Spark SQL. As you can see, it can be very simple to interact with your data, and it's very powerful. You can connect to a Spark installation on a whole large cluster. You can interact with data sets that are petabytes large, and as long as you can get your data frame set up, I want to reemphasize, a data frame is really just an RDD with a schema applied to it. And if you have an RDD, you can just apply a schema and it becomes a data frame, and then you can just interact with it using select statements. And the SQL engine implemented in Spark is actually very well optimized. So chances are, if you write your query in this format instead of writing programmatically, you might even get better performance out of it. All right, that wraps out our demo.
So we're going to talk about Kafka, a way of distributing information from a set of producers to a set of consumers. Kafka is rather different from other protocols that do this. It's part of the Apache series that's associated with streaming data, and there's very good reasons for that. It can be used for all sorts of purposes within a cloud to provide data feeds for lots of different processing elements, typically applying that towards real-time systems. So let's have a look at Kafka. First of all, we'll take a view of what it does in an application, and then we'll go back and we'll look at some of the key concepts in Kafka, and then give some examples of how it's used and what the Kafka clients actually do. So at the top level, what is Kafka? And this slide illustrates all of the parts, but we will need to go and explore all of this in detail to understand it all. First of all, it's distributed, meaning that it's actually going to be a cluster of machines that provides the Kafka support. It's partitioned, and that means that it's actually using separate partitions to represent the data that it's transferring in the messages from producer to consumer. It's replicated, and that means that these streams are stored in separate systems in the cluster, so that if one of them dies, you're not going to lose anything. You're still going to be able to continue processing the stream. And this is important because it's really aimed for large data, for big data, where you might have so many streams, you need so many computers that the likelihood is that something might at some point fail. It says publish, subscribe, and that really refers to the fact that you have producers that put the information in there, consumers that remove it, and typically producers put things into the system in order, and the consumer will remove things in order. Now, in this particular system, in Kafka, what you find is you can actually mix inputs and you can mix outputs, and in particular, sometimes the applications use a pool of consumers to consume from a particular output stream from Kafka. If you like to think of these as messages, what you're doing is providing communication between a bunch of producers and a bunch of consumers, and there might be some indexing, some annotations, some control going on in the Kafka cluster. So we will now take a deep dive into what is actually happening, and then we'll look at some applications, as I said, later. So it maintains a feed of messages in categories. Those are called topics. So when you exchange information between a producer and consumer, a producer is going to produce something for a topic, A consumer is going to remove something from a topic and do computation with it. Processes that publish messages to a Kafka topic are called producers, and processes that subscribe to topics and process the feed of published messages, they're called consumers. So that's quite natural. It's the relationship of the producers to the Kafka system, to the partitions, and to the consumers that becomes interesting in any application. Kafka is run as a cluster on multiple machines so that if one breaks, others can take over, and so that if you have a large input feed of huge amount of data, you can actually compensate for that by having more machines process that data. That whole mechanism is called a broker, and what it's doing is making sure that the right data gets to the right data from the producer gets to the right consumer. The communication, it again follows the TCP paradigm that we're so familiar with in data clusters. Things are in stream, they're ordered, they're not lost, they're repeated if they're lost. TCP is the protocol that does that, and typically the clients will read these streams in order from the different devices, but we'll find some different cases as we go. Oftentimes, clients will be programmed in Java, but that's not necessary. Any sort of processing language system that will handle TCP will be fine. So what are its key contributions then to big data and streaming and the way that systems are organized? The answer is, well, it's very scalable. Kafka is backed by a file system, so you can get an enormous amount of data stored in this topics broker type of configuration. It can deal with hundreds of megabytes per second per server of throughput, and that's quite an accomplishment. It's not just that it can deal with it on a short-term basis, but because of the backing file system, it can deal with it over a long period of time, like days, months. The servers can have many terabytes of data in them, and so you have a window. Now, typically, as data moves through Kafka, it will get eventually replaced, deleted, maybe after 4 days or 5 days. But if you're looking at sort of very high throughput, then that can indeed be a huge amount of data residing on the Kafka servers. It's distributed so that we can do replication, and so we can use partitioning to make sure that there's no interference, that we can scale it, and so that if there's any particular failure, it's not going to affect the whole system. So here's a picture of producers, consumers, and what you can see is that there can be multiple producers going into multiple, actually we can have multiple topics inside a broker cluster. We are having producers feed into one topic and then consumers reading out of that topic, and there can be multiple consumers. The order in which the consumers take things out of the topic can be of interest to the way you build the applications. Now, each topic has partitions. Those partitions are going to be independent. They're going to be replicated so that as you're writing this stuff, the topics actually provide a very resilient, robust infrastructure for communication. And the partitions themselves are distributed across all the servers in the brokers, so that if a server dies, there'll be some other server that can take over and actually provide the information. So if we dig down a bit further, what you'll see is that messages about a particular topic will get stored in a partition, and that partition is an append-only log file. So what you're doing is to writing to the end of this file, so there's less reason for corruption, and that there is less need for synchronization. All of the additional messages from producers go at the end. The consumer is going to gobble up the front part of it, and so you shouldn't get any interference synchronization-wise between the producer and the consumer. Each partition is ordered so that you can keep the sequencing that you need for messaging, and that properties kept all the way through because the protocols are TCP/IP. It's numbered and it's immutable in the sense that once you've appended to it, it doesn't go away. So it's very, very much like a commit log of all the messages for a particular topic for that going through that particular partition. Well, let's move on to exactly what is the notions underlying how it works. Each partition can be replicated. You've got to find the right partitions if you're a consumer. If you're a producer, you've got to know which partitions to write to. It's replicated across a configurable number of servers, and if one of the servers goes down, that will change and the system will accommodate that change. Each partition has one leader server and 0 or more follows, and the leader handles the read and write requests and then copies the data out to the followers. A follower replicates the leader, acts as a backup, so this is what gives you your resiliency. Each server is a leader for some of its partitions, but other partitions that it actually holds on its file system will just be replications of other servers' leadership. So the whole load is spread uniformly between all the servers in the cluster. Now you can say, well, how do I keep track of all the information, the state information about which producer is writing to which cluster, which is the leader, where everything is? And the answer is we are going to use Zookeeper. Zookeeper is going to be used as a little sort of data store that records where everything is. Zookeeper has consistency built into it, and so it doesn't suffer from any race effects or from failure effects. It will keep everything consistent. All that the servers have to know is to where to go to get their information. So we've talked about Kafka as a system. What makes it interesting? And the answer, well, this is from LinkedIn. It's a demonstration of what Kafka is being used for. It's being used in this system as part of a big distributed data system, and it feeds online applications data into the system and will allow that information to be updated to distributed databases and to analysis to keep everything up to date. So you see the Kafka in the middle of the screen, and what it's doing is to receive data deployments, and it's receiving change logs from another system called Ambry. We'll get round to that later in the course probably. But it's receiving those updates, and what it's producing is streams of data out to another process called SAMSA that can be used for doing analysis on streams. Now later on we're going to be talking about stream processing, and we'll address the idea of SAMSA. But what you can see here is that Kafka is providing, if you like, the data throughput, the way that the messages, the information flows through the system when it's dynamic and when it's updating. And it is the sort of glue that goes between streaming and big databases. So let's now sort of go back, take a little bit more leisurely time through this system. What does the producer do? It sends messages to Kafka brokers. The messages are sent to a topic. The same key goes to, the producers produce messages with a key. That same key goes to the same partitions so that they're kept in order. Messages without a key, well, by convention, they actually go to a random partition. So you have a way of actually distributing data without a guaranteed order if you want to use that. If the number of partitions change, well, you would have problems keeping those keys consistent, and so you're better off if you can actually replicate and duplicate systems that fail with backup systems. Here you've got a diagram about consumers, and what it shows is that, well, a consumer can belong to a consumer group. There can be consumers in the same consumer group. They need to collaborate between them, coordinate with who consumes the actual messages. So for example, in this diagram, you have P1 and P2, the partitions P1 and P2 being read by consumer groups. How they organize who reads from P1 and P2, that's really up to consumer group A about how that's operating. Similarly with consumer group B, you have a much more complicated situation there. That group can read from P1, P0, and P2, so it needs to coordinate exactly how it's reading from those partitions. But as I say, it's very flexible because it's up to the consumers about what they do reading from these groups. From the broker's point of view, it doesn't need to know all the complexities of what the consumers are doing. Instead, there's an index into the log, and that message offset doesn't change. The consumer offset is that part related to what is the consumed. The message offset is that part which is related to where the producers are putting things. So the consumer offset, just removing, will increase the consumer's position as the items are consumed. And as I say, which consumer process actually increments that is up to consumer convention. The consumer offsets can represent topic, partition, and then within that, the consumer group itself. So these consumer offsets could have race conditions and other things if that's a problem. So consumer offsets can be committed as a checkpoint for consumption, so it can be used when, say, another consumer comes along, or if you want to resume consumption from later committed offsets, you can decide that, but that is at the consumer level. Here's an example of how you might actually program with those consumer offsets. Let's suppose you have consumers and they're absorbing or taking messages from, say, each of these partitions, P0 through P3, and in topic 2, partitions P0 and P1, then essentially you've got a queue per thread, and each consumer can absorb from multiple partitions. What you'd like is exactly one consumer in the entire group to actually sort of be taking the data and using it, and so you would need to decide. If there should be an imbalance, say some of the consumers are too busy, for example, consumer 1 and consumer 2 are absorbing both messages from topic 1 and topic 2, you may need to reorganize it. Or maybe you want to add load to consumer 3 or consumer 4. You need to rearrange the whole system, but again, that's done through the consumers and consumer programming. So here's a sort of change that might be made, adding a consumer 3 to take data from that partition 1 in topic 2, but that would have to be done through the consumer agreement. Okay, so in summary, what you have is what is effectively a publish-subscribe system, but it's actually publishing and subscribing to logs which are stored on disks, making them very reliable and resistant, and also very scalable because you can store huge amounts of data and you can replicate, have more files, have more brokers, more servers, and so you can actually increase the throughput for any particular system. So this is a unique sort of piece of the framework, and we're going to see it applied in many different applications later on. So we've been looking at big data and how data systems, data centers process those big data requests and sort of examples of the processing engines involved and the storage involved. Another form of big data that's really important in clouds is how they process streams of data, and that has become an enormous sort of business sort of driving multiple different organizations, think people like Facebook and so on, in how they actually manage their cloud computing and services. Stream processing has lots of important features which we'll deal with. Imagine you're browsing a web page. What you will probably end up doing is to click over an advert or whatever, click on a page that has an advert that pops up or is otherwise displayed. You can imagine the advantage to the service providers if they can count how many adverts you actually get to look at. The companies providing the advert will want to know just how many people were interested in that advert, whether they clicked through and whether they actually bought the product. So counting all of these things has become a big industry. If you see an advert on a page, just seeing it, the systems nowadays will actually try and record that you actually saw this and when you saw this. So the user, the advert, and the ad ID, and then the timestamp of when you actually saw it would go to the consumer base. So let's say you're clicking through LinkedIn, then you would see an advert as you were sort of browsing somebody's page. That would all be recorded and is useful because now the advertisers know that you're actually sort of observing their adverts that they've paid for LinkedIn to put on their website. If you, however, got interested in the ad for that new sort of Tesla car, then there'll be another ad click as you sort of click on it and go to the website. And that really is in response to, well, it was a good advert, the ad agency did well in placing it there, and you are sort of an interested potential customer. So again, a record will be taken of that and stored away. So you get these mouse clicks from everybody's browsing, and pretty much whenever you visit servers or whatever that have advertising, this is going to happen. And it's going to produce a huge amount of data streaming back to a variety of different companies. So you need to process this to actually find out how effective an ad is, how effective a campaign is, or whatever. What is the interest in this particular type of article? And the mechanism for doing that is in data traffic going back about those mouse clicks. How to process it? Well, it's continuous. It's mixed up between lots and lots of different users actually looking through the web and clicking on pages that might have adverts on them. And there's just a huge number of people, so it's 6 billion people or 7 billion people in the planet. A large number of them may be clicking through. And when you have sports events like the Olympics, you can potentially have huge fractions of those folks actually sort of observing an advert. So all of this data comes back. What you would like to do is to process it and in near real time actually decide, well, do you want to place more adverts? Do you want to spend more money on advertising? Or do you want to change the adverts? Do you want to identify other places to place adverts? All sorts of decisions that can be made off what's occurring. How are the advert companies going to do that? The answer is they would like to take that continuous stream, look at it, see who the people are that are looking at these adverts, look at the timestamps, look at the adverts themselves, sort them out, and then decide whatever they're going to decide. So they need to process all of this data. Typically, the output's going to be a sort of infinite sequence of changes to the derived data set. It's going to change how many people are interested in this product, how many people are interested in that product. It's going to generate out a sort of fan of information in a sort of consumer-producer way to a whole bunch of engines in the cloud. And the question for us is just how do you build such systems? So you have high input, lots of different events. They're sequenced. When you get them, of course, they're going over the network, so they may not be in their original sequence. You've got to sort them out. You've got to work out what they relate to, and you want to process them very quickly, and then you want to output data from them that can change the behavior of the advertising company or whatever in that sort of real-time way. So you get diagrams of these streaming processor systems that look a bit like this, that you have multiple streams coming in, you want to sort out between them what is common, what is different, what the times are, sort the times, join the streams together, work out what's a hit on a particular ad, and then send out data based off that, and it all has to keep up. If you have queues inside this system that increase because your processing isn't fast enough, then essentially you're going to increase the latency, you're going to slow everything down, it's not going to keep up with real time, so that's a problem. What you want to do is to keep it running as fast as you can. So you may want to add extra stream processing units to that, in which case you may need to do extra joins and all sorts of other things. You need to think about that architecture of stream processing. So that's the topic of the next sets of lectures. We're going to discuss different stream processing engines, different ways to construct Fritz streams, different frameworks, and some of the practicalities and problems about doing this stream processing. Essentially, what you're looking for is low latency. You want to be able to tolerate things that arrive out of order, even though they've got dates on them. You may even sort of late arrival. You still want to be able to process it and fit it back in somehow. It should be usually user-friendly. In particular, the person doing the stream may not be the person processing the actual ad request, so it has to be user-friendly so that it's easy to operate. And typically, people think about SQL for data queries. You would like SQL on streams to give you results about what's happening out there. You would like it to be scalable, so if you hit a big, Olympics event, you can accommodate all those clicks. You would like your data to arrive safely, so it's not duplicated or lost. You would like it to be highly available, so you can instantly see what's going on. And probably there's a whole suite of other requirements too. So these systems that we're talking about generally are built to allow you to do this and allow you to build systems that maintain this requirement throughout that system for processing all of those streams. As you sort of hone in on particular ideas in stream processing, what you'll find is there's some slight changes depending upon the applications, how you're going to process these applications. There's some issues about scalability. Are you looking at millions or billions or trillions of events a day? And how do you actually store all those? How do you get a state representation of what is occurring? And in particular, you may have multiple products. They may all be having clicks, and you may want aggregates across them, and you may need to accommodate all of that aggregate stream as well. So you have multiple parts of the back end. Why is it expensive? Well, you may need to keep the intermediate data sets to allow some further processing, perhaps at low latency. You might need to be actually moving large amounts of data across the network from one part of the country to another. Lots of sort of implications of the way that you've organized your outfit. All of that has to fit into the framework you're going to build for this stream processing. So the next time, what we'll be looking at is the individual components of how we do stream processing on data centers. Thank you.
In this module, we will be talking about real-time streaming systems, cloud-based real-time streaming systems. We are talking about a new breed of streaming real-time data processing systems that have become very common as of a few years ago, maybe 2 or 3 years ago. And there's a lot of work going into these systems at the moment. The research is very hot. A lot of enthusiasm in the industry on using these systems as well. So why would be interested in real-time data processing anyway? Real-time big data stream processing. It has become really a requirement for modern businesses. Of course, we've talked about big data and cloud computing and how cloud computing has changed the face of modern IT services and infrastructure, and how processing big data has become really mandatory for businesses to survive. The nature of big data is starting to evolve little by little in the industry. Of course, we still have huge amounts of data, log files, static data files that we need to do batch processing on them. That hasn't changed. There is definitely a place for Hadoop for batch-based systems, as we talked about in our module 2, Pig, Hive. Those are definitely valid use cases. But now we have a new breed of big data, real-time information streaming in. Think about real-time search. As a search provider, a company would have millions of requests to address each hour. Tens or hundreds of thousands per hour, per minute, really. Or think about high-frequency trading, where machines are deciding in milliseconds, nanoseconds, really, whether they should do a buy order or a sell order on a certain stock. Social networks, think about social networks. You go to your favorite social network, Facebook, Twitter, whatever, and you see your friends or people you're following, new events come for them or about them every second. So, for example, again, in the case of social network, you really don't want, as a user, you wouldn't want the provider to only have a batch processing system. Every hour, we update the status of everyone, and within the hour, you just keep reading what was there about an hour ago. That's not what you want. You want to see if some of your friends post something on Facebook, you want to see it within a few seconds, right? So any system that have a stream of events that flow into the system for a given rate of data rate, we consider it sort of a real-time streaming system. Another example is advertisement clicks. A lot of large website providers, they put advertisement on their websites. And within each minute, within each second, there are hundreds of people clicking them, seeing the ads. And you really want to see how the users are reacting to a certain advertisement or not within at most a couple of seconds. And as they say, time is money in this industry. You really don't want to show an ad more than it's being paid for, but you also want to maximize the utilization of your advertisements. So these systems are huge. The processing system that wants to handle this set of data must also keep up with the event rate. If it cannot keep up with the event rate, say suddenly there's just so much demand and the number of machines that you have set aside for processing this streaming data set is not enough, we want the system to degrade gracefully, for example, by eliminating events. We don't want the whole system to go belly up and crash. We want the system to keep continuing, maybe drop some of the events. And well, we call this feature load shedding. You want your real-time big data streaming system to have load shedding and gracefully handle load. And as I mentioned, batch processing systems like Hadoop and MapReduce, they store and process data in batches at scale, which is good for some use cases, but it's not useful for real-time systems. In a previous video, I was talking about how Hadoop system was hacked by researchers and then some industry participants into doing some things that it was not designed for. For example, iterative computations. Okay, there was some hacks, but for some instances, and some of them were successful, some not. But for real-time streaming systems, there was no hack. Hadoop itself was just so different, so fundamentally different set of requirements was used in designing Hadoop as a batch processing system, that there was really no hack to get Hadoop to do real-time processing. And lack of a Hadoop of real-time, as we can call it, because Hadoop has become very, very popular. Many million man-hours of work was spent on developing Hadoop and finding bug fixes and making sure it's scalable and everything. So it was very popular. We needed something like that system for real-time processing, streaming systems. And it was, at least up until like a year or two ago, it was really the biggest hole in data processing ecosystems. So what we had and what now we have in the last couple of years, and I really am talking about starting in 2011, 2012, and really exploding into a large number of systems now that people are very interested in working on. And as I'm talking to you right now, people are working on it, fixing bugs, trying to make sure these systems scale. The area is very hot. There's a handful of systems, a couple that I want to mention. Number one is Apache Storm. It was kind of earlier than the other systems to the game. And in this course, in the upcoming videos, actually this whole module, we talk about Apache Storm in detail, how to write applications for it, how it goes and manages to run your streaming big data application on a very large cluster of machines, and more examples. There are other examples as well. Twitter Heron is a system recently announced by Twitter. Twitter was originally working on Storm, as we will talk about in our next video. And then at some point they decided that they will want to adapt it more to their needs. So they actually forked it off and wrote a new system called Heron. And that's one of the competitors. Apache Flink is another one of these big data streaming systems that has its own set of proponents. Now, of course, there was a set of older non-cloud, non-big data systems that nevertheless were trying to address real-time streaming. IBM System S is a prominent commercial example, still very validly used in the industry. Borealis had its roots in academia, really. It's a descendant of another academic system, Aurora, that came out of the Brown University originally. There's not much work on these systems anymore. A lot of work is going on Storm and then some of the other open source systems.
Welcome, my name is Matt Arns. I'm an engineering manager at Yahoo Champaign, where we're solving a lot of interesting big data problems. And one thing that's happened in the last few years is there's been a rise of demand to have data in more real time. And so as a data team, we've been looking at what technologies to use and how to migrate our architecture to support more real-time use cases. One of the big technologies that came to the forefront as the rise of real-time began is Storm. So now Hadoop offered a lot of large-scale capabilities when you talk about batch data in terms of processing data in chunks of data every 5 minutes, every hour. But there was a growing need to provide data in real time for analytics use cases and also to get instant feedback for some of our large-scale data problems that we were facing. An example would be if Yahoo has on its front page some trending now module that shows users what are some trending search terms or what are some trending news articles, that we wanted to provide users with feedback in the order of seconds or minutes to tell them, okay, what are the top things that are relevant right now? And so we needed a technology that could get us data back in a matter of seconds. So Storm is a technology that Twitter created and then open sourced, and it became stable for production scale, or the scale that we use at Yahoo when you talk about billions of transactions a day and terabytes of data a day, in 2012. So that's when we started looking at that and trying to apply some of our problems on top of Storm. Now what Storm is, it supports a fire hose of data, and it has the notion of topologies that are graphs of spouts and bolts that are connected with stream groupings. And they run indefinitely, that these processes are always running in memory and can process new tuples whenever they come in. There's also streams of data, which is an unbounded sequence of tuples that are processed and can be passed downstream to other operations in the topology. Now the concept of a spout is where the data input comes from, and Yahoo has various points of spouts that we would use in terms of advertising data, audience data, other analytics data that we have internally. And then we have bolts, which process different types of data, and we can do transformations, filters, aggregations, or joins. And then we have sinks, which is a special type of bolt, which allows us to output data to some sort of data mart or other stream that can handle data for a use case. So how did we get here? Why was 2012 around the time when we were ready for something like real-time? When you think about doing a real-time technology, the big thing is you need to do processing in memory to be able to be fast enough. And we finally had hardware costs down when you talk about the cost of memory at a place where it was cost-effective to process billions of events per day through a streaming technology. You can see here on the graph that the cost has gone significantly down in the last 30 years alone in terms of how much it costs per gigabyte of RAM. So it became viable for us to try to justify building these large-scale streaming platforms for our data pipeline use cases. One thing that came about, and this came about from the Twitter world as well as they created Storm, is they created an architecture called Lambda, which actually allowed a system to blend batch data that was processed on Hadoop with streaming data which was processed on Storm. So you can see here in this picture that you have the same data stream coming right here. But it will actually get sent in two different ways, one to a Hadoop system, which is the batch layer, and then also to a speed system, which would be on Storm. And as data gets processed through both means, the Storm layer would obviously be faster. So if someone is running a query at, let's say, minute 5 of an hour, they might only get data that is coming for that hour from the speed layer. So they would only get this data. But let's say they processed at 30 minutes after the hour. By then, there might be some data coming from Hadoop. So it actually gets some data that had come from Hadoop, and then also a mix of data coming from Storm. So that was the benefit, is you actually could get some data in real time, but it could be blended with data coming in from Hadoop. And that matched a lot of our analytics use cases at Yahoo, is that our customers wanted their data as soon as possible, but we also wanted to take advantage of these Hadoop systems that we had built, which had a little bit more guarantee and higher data quality in terms of passing data through Hadoop. So you can see the present architecture, which we followed that Lambda model, and that we have systems on Hadoop and Storm that are processing the same types of inputs and doing data pipelining through the independent paths, and then storing it into a common data mart to allow for that Lambda access for our data users. So the technology that we've been using the last couple of years is a technology called Druid. And Druid supports batch ingestion as well as real-time ingestion. So that means that data can be sent from Storm in real time to send events as they happen, and the latency is on the order of a few seconds. And then later, an hour or two later, we might have an hourly set of data coming from Hadoop, and the Druid data mart will then replace what came from the real-time instance with the batch data and make that the source of truth. But the nice thing is that our data users and customers, they don't know what's going on behind the scenes, right? You can draw a line there that they only know that they're getting their data really fast, and they don't even know that behind the scenes that batch data is replacing the real-time data. So it's a big benefit to be able to have the real-time analytics as well as the guarantee of the data coming from Hadoop. So now that we've gotten to the Lambda architecture, we're now starting to think about what would be next. What is the next generation of data architecture for processing billions of transactions and terabytes of data per day? And then there's been some talk in the industry of this notion of having real time as source of truth. Some people in the industry are calling this a Kappa architecture, where instead of having two independent systems, you have one system built on Storm, which becomes a reliable platform to process data with a latency of a few seconds that becomes the source of truth for all downstream users. So you can see here, there's no, at the front end of the data system, there's no Hadoop. There's just Storm that processes data that would go then to downstreamers such as Druid and HDFS. Now, one thing is we still would have Hadoop in play because there's some things that, especially right now, Storm isn't as cost-effective for doing large-scale, daily, monthly aggregations of data, and we would still use Hadoop for that. But we still would get the benefit of having Storm be the front end of our data system because it would be able to give us data in the order of seconds. So we'd get all of our data now in the order of seconds to process to our downstream users. So this is something we're working out and we're exploring and trying to move to, and it's something that's happening in the industry as well. So we'll see what problems and challenges we face, but it's something that we are hoping will provide a lot of value for our customers and users.
In this video, we start talking about some of the concepts in Storm and how you would want to program a simple word count problem in Storm. In upcoming videos, we will talk about the details of Storm as well as more involved examples, more advanced examples. So let's start by talking about what is Storm. So Storm was developed as a real-time streaming system with a set of goals. Some of the goals that the designers of Storm had originally are as I've put here on the slide. The first thing was, if there is a need, they wanted the system to guarantee data processing. What I mean here is that they want to make sure the system does not drop an event in case of a failure, right? So an event is an important thing. If there is a need for it and it's configured by the user, they want to make sure every single event is eventually processed by the system. They want to have horizontal scalability. What we mean here is that if the system isn't enough for the streaming load coming in, we can just add machines of similar type to the cluster, scale the cluster horizontally by adding similar machines to the whole set, and the system can then scale and answer the load. They want to provide fault tolerance so that if one of the machines or some of the machines fail, or if there's a network failure, the system can, regardless, tolerate that issue. For example, kill those nodes, launch new instances somewhere else, and continue processing. They wanted to make sure the system doesn't have a single point of failure or hotspot to make the scaling issue. Therefore, they wanted to make sure there's no intermediate message brokers. All the nodes can talk to each other if need be. And really what they wanted to achieve was a higher level of abstraction than message passing. Yes, you can write a streaming big data event processing system by just using MPI on a cluster, but they wanted to give the users a higher level of abstraction than just saying, hey, this machine sends a message to that other machine. It becomes very tedious to write programs that way. And they wanted to really have a system that basically just works, kind of like a Hadoop of real-time streaming jobs. What I mean is that they wanted to allow the user to just start thinking about the logic that they wanted to program and let the system, the framework, handle all the nitty-gritty details of how to send the messages from one machine to another, how to queue the messages, how to handle failures, scalability issues, so on and so forth. Storm was originally built by a startup called Backtype. Twitter bought Backtype at some point, and eventually the whole project became an Apache open source project. And this is where it is at, thriving in the open source community. The Storm cluster has multiple players, multiple components. There is a single master node, it's called Nimbus, that oversees the flow of information in the system and basically manages the other components in the system. Each individual node in the cluster has what is called a supervisor daemon that talks to Nimbus, figures out what processing tasks to run and where to get its input data for its tasks, from what network port, from which machine to, and send its results to which other machines. And the communication typically happens through a small Zookeeper cluster. Now, we haven't talked about Zookeeper much. It's out of the scope of this our short Coursera course. Having said that, Zookeeper provides really a service to allow coordination. Therefore, if any component in the network, any supervisor or Nimbus, writes something to the Zookeeper cluster, it is guaranteed that any other actor would see exactly the same thing in the correct order. Storm cluster has multiple players playing in the system. The master node here, which is called Nimbus, oversees the general flow of program execution across the cluster and makes sure the resources are handled correctly. It schedules different user jobs on the different nodes of the cluster. Each of the cluster nodes has a supervisor daemon running on it, which basically gets its assignments from Nimbus and starts running a user task, and can send the result, and by result I mean the job progress or the status of the job, back to Nimbus. Supervisors talk to Nimbus through a Zookeeper cluster, which we will talk about later in our course. It's just a simple mechanism to make sure cluster coordination can happen correctly with certain guarantees. Now, each supervisor, when the Nimbus tells it, will go and launch certain user tasks. So let's talk about how a Storm program is written so that then we can figure out what tasks are. To write a program in Storm, we need to know about a couple of concepts in Storm, which are, to be honest, these are also common across other streaming systems as well. Now, the terminology here is really only limited to Storm, but the concepts are common across streaming systems. First concept we want to talk about is streams. Streams are a sequence of tuples. Now, what do I mean by tuple? Tuple is a bit of information going around the network from one player to another, from one node to another. A tuple typically can have a key and a value, like many of the other big data or cloud systems that we talk about throughout the course. We always talk about key value pairs, right? So a tuple also usually has a key and a value. Now, a stream is a sequence of these tuples going from somewhere to another. Second concept here is a spout. Spout is a source. So you can get a stream coming out of the spout and going to other components of your program. An example of a spout could be a component that reads data off of Twitter over internet and reads them and then passes it on to the other components of your program. Or you can think of another spout that can read data off of HDFS stored files and feed them into your program. Other spouts as well. There's for example, a common system used in big data is Kafka. You can have spouts that read data off of Kafka and again pass it into your topology, which I haven't talked about. I'll talk about it in a second. The third component are the bolts. Now, bolts are arguably the most important part of your Storm program. A bolt is a component that gets a certain amount of input and produces output. As input, it gets an input stream or more than one input stream. It could get multiple input streams. And as a result, it produces output stream of tuples. Here in bolts, you can program your functions, filters, joins, aggregations, database lookups. Basically anything that you want to do with your program, you write them as bolts. And finally, now that we have introduced these three concepts, we put them next to each other and we call the result a topology. A topology is a network of spouts and bolts, as you can see in this diagram, that they're connected to each other with a certain idea that, for example, my spout 1 could be a database, spout 2 could be coming from Twitter. I can do some sorting here, and then I can write them somewhere. In this meanwhile, I can also do a grouping. The database inputs can come and become like a table, and I can do a join on these and do something with them. So topology is really your program that is built out of bolts, spouts, and processes streams. So remember that when I say a sort bolt, or for example, a word count bolt or whatever, I'm not saying that we need one bolt for each machine, right? That's not what happens. The programmer wants to write a program in a logical sense. So we want to say, my program first gets its data from Twitter and then sorts it. The programmer shouldn't need to know how many machines are required to sort it to think about the program. That comes next. That comes in the context of tasks. So each spout or each bolt can execute as many tasks across the cluster. So you can have one bolt that is really running on 1,000 different machines. When a tuple is emitted, now the question becomes, what task does it go to, right? So for example, look at this diagram. You have your spout that is connected to this bolt. Okay, a tuple is coming out of here. This bolt could be running on 1,000 machines. The question is, when a tuple is coming out of the spout, which of these 1,000 machines does it go to? Now the answer to this question is, it's up to the programmer. There are multiple predefined strategies in Storm that a user can decide to use. I have put a bunch of important ones here, common ones. First one is shuffle grouping. Shuffle grouping says that I really don't care which of these tasks my tuple goes to. Whichever it goes to, it's fine. It just needs to be processed. So shuffle grouping picks a random task and just sends it to that machine. And it's typically used for load balancing across machines. So if you have a certain amount of load that you just need to divide between a certain number of machines, you just pick shuffle grouping, and the system does the load balancing using a random algorithm for you. The next method is fields grouping. What fields grouping does is that it takes a consistent hashing function that could be provided by the user as well, and there are default ones. So it takes a consistent hashing function and runs the tuple through that function. The output of that hashing function decides which task machine that tuple goes to. It's consistent, so if a tuple with the same contents comes again, it's guaranteed that it goes to the very same task. Next strategy is all grouping, which means when a tuple comes here and I specify all grouping, it goes to all of the machines that are running that bolt. And there are some other ones as well, like for example, global grouping, where you can pick a task with the very lowest ID. Let's look at an example of an application that we want to write with Storm. And let's go through the code a little bit to see how you would really write a real-world streaming example with Storm. Looking at the diagram, we can see what we want to implement here is a streaming word count. We can assume the input contains a set of sentences, a set of quotes that come in real time, and they just keep coming. And what we want to do is we want to know at each moment what was the last top K words that was seen and observed before in a certain time window. To write this program, we can write something like the following diagram. In the first bolt that you have, you can consider to have a sentence splitting bolt functionality that what it does is just get an input sentence, and as output will emit individual words that are seen inside that sentence. The results of that could go to another bolt called word count bolt. Word count, what it does is keeps the total count for each of the words across all of the quotes or all of the sentences. And anytime it sees a certain word, any word, it emits a new tuple with the count that it has seen so far updated. The results of these bolts go to the next set, which would be, for example, sort bolts. A sort bolt would continuously sort partial lists and emit the list as the output periodically. And then the next and final bolt would be a merge bolt that combines partial lists together and output one final merged top K words list. OK, let's look at how we would write these bolts in a Storm program. Let's first look at how we would write a bolt. Writing a bolt in Storm is quite simple. Majority of the functionality of the bolt is already implemented by the framework, and it's provided to you via certain interfaces and parent classes. In this case, like the interface rich bolt and the parent class shell bolt. So all I need to do really is define a new class. Let's call it split sentence as my first bolt in the diagram that I showed you, that just extends the required parent classes and implements the required interfaces. And inside this, you just write simple Java code. Like as input, you can just say have a sentence, and outputs are just words. So let me show you in another example more detailed. Let's look at our next bolt, for example, the word count bolt. This time I'm implementing a different interface, basic bolt. In our next lesson, where we get to talk about the more advanced parts of Storm, we talk about the differences between the rich bolt and the basic bolt and how they change the functionality of Storm. But for now, let's just assume that there is a parent sort of interface that you just decide to pick one or the other and just implement it. So here I'm creating a new class called word count, implementing the interface basic bolt. And inside I want to write code to count words. What you have to do here, and I just didn't show you in the previous example just to keep the slide a little bit clear, is you have to overwrite a function that is defined as an abstract function in the interface. Now you have to overwrite it to make it a usable class. The function that you have to overwrite is the execute function, which the framework gets to call every time there is a new tuple arriving. What it does is that it gets that tuple, calls your execute function, gives you the tuple. And aside from that, it also hands you a collector, which is of the type basic output collector in this case. This is your mechanism to use to emit output tuples. So now, from here on, it becomes very simple, right? You have one input value, and you can do your processing, any sort of processing, and use collector to just emit outputs. Once you've written your bolts, for example, the sentence splitting, the word count bolt, and so on and so forth, sorting, merging, you need to connect these bolts together to make a topology. And topology is really the combination of these bolts and their connections that achieves your goal and runs your program. To build a topology, what you do is you use this class provided by Storm called Topology Builder. Once you make a new object of this type, and as we will see, provide correct parameters, it builds a topology that then you can pass to Storm, to a running instance of Storm, and say, hey, this is my topology, please start executing it. The first thing that you need to do in a topology is give it a set of spouts and bolts. So let's see how this works. I start with a spout. I just give it the designation 1. For the class that it needs to go and find the code for spout, I'm telling it to go and create the spout from this class, kernel spout. This is one of the classes, Storm classes that can read data off of Twitter. As parameters to this kernel spout, I'm telling it this I'm giving it a URL to read information off of Twitter, and possibly a port number, some parameters required for reading information about Twitter. And one important thing that I'll talk about in a second is this number 5. I'll talk about that in just a second. So once you've identified the spout that you want to use in your topology, you continue by giving the topology builder object set of bolts. So the next thing I say is that use a split sentence bolt. I just introduced the class myself to the system. This is the class I implemented myself and showed you in the previous slide. I give it a designation 2. And what I do here next is I say the input to this bolt comes from component number 1. And component number 1 was defined here. This is the spout, and it's component number 1. And not only that, I also specify how I want to get the tuples. In this case, I say shuffle grouping. That means that any of the tasks in this bolt can receive randomly a tuple created by the spout. So how do I specify the number of tasks that each of the spouts or bolts have? This is what I was talking about. Number 5 here, or number 8 here, or number 12 in the next bolt. This is what is called the parallelism degree. And it's really the number of tasks for each spout or bolt that the programmer specifies. Once the storm system sees this topology, it tries to launch 8 tasks for this certain bolt, our split sentence bolt, across the cluster, 12 word count tasks across the cluster, 5 spout tasks as well. So now you can imagine there are 5 input streams of Twitter information coming into the system, into the topology, right afterwards. So there are 5 input, and then there are 8 split sentence tasks, and each spout, each tuple coming out of a spout can randomly go to any of these. Let's finish up this example. The next, the third bolt, and I give it the designation number 3. I say to use this class, word count class, that we saw how to implement in the previous slide. Run 12 tasks for it. Get the input from component number 2, which is the previous bolt, and use field grouping, which, as you remember, uses some sort of consistent hashing function. And since it requires the consistent hashing, I'm actually giving it the class that does the hashing. Finally, we need to, now that we have created a topology, we need to submit it to a storm running cluster, a cluster that's running storm. And we are really talking about Nimbus. So what we really need to do is to tell Nimbus that, hey, this is my topology. It's in a jar file. I mean, the topology builder puts it in a jar file and then hands it to Nimbus. But we eventually want to tell Nimbus that, hey, this is my topology. I want to give it a name. Let me call it word count. And how do I get the topology? I ask the builder object to now go create the topology. Before this, I told the builder how the topology is going to be built. Eventually, I asked the topology to build the topology and then pass it to the Storm Nimbus through a class called Storm Submitter. This way, after all of these steps, Nimbus gets the topology and then starts scheduling it on the running supervisors on the cluster. As many tasks as the user requested, 8 tasks for some of the bolts, 12 for the other bolt, and so on and so forth. Of course, in this example, I didn't show you all of the bolts in the diagram in the beginning of the video, I showed you 4 bolts. Here I'm just showing you the code for 2. The other 2 bolts are quite similar.
I'm sitting here with Matt Arns again, and I'm going to ask him some questions about how Yahoo is using Storm. Matt, why did Yahoo choose to move to real time?
Well, I think we were keeping up with the demands of our customers in the industry. If you think about large-scale data, the first dimension that was solved was the dimension of scale, right, with Hadoop coming along. And then the next thing people asked for is now that we gave them lots of data, they wanted it as quickly as possible. So we needed to provide some sort of platform to give them data, really in the order of seconds or minutes at most.
So this is industry-wide?
Yeah, this is something that started, really a few years ago, where there's a trend of once, memory costs got reduced, people said, okay, we can do this. We can do billions of transactions per day processing in streams through memory. And so a lot of the, the big data companies are providing these platforms.
Okay. And why didn't the batch model work anymore? I mean,
so the batch model still works, for the batch use
Okay.
cases, but what it couldn't solve in terms of real time is providing really that second latency. And the main reason is because Hadoop, in terms of its batch use case, was built with the overhead of starting up jobs and processing large data sets. It was built to mine terabytes of data at a time. It wasn't built to necessarily process a kilobyte event at a time. So it's just the nature of what Hadoop is good at, and then now what these real-time technologies are good at as well.
good. And how did Yahoo handle real-time systems before Storm?
So that's a great question, because we actually did have some of our own solutions for solving real-time systems. So we used our own custom messaging frameworks to just pass messages between systems and do very lightweight aggregations, but it wasn't at a large scale that we're seeing today. It maybe handled millions of transactions a day at most.
And so what has Storm brought to Yahoo, and it's sort of now in the current day?
Yeah, so a few things that Storm's brought. One is it's brought us just a large scale of data. We have clusters of hundreds of nodes that are in a multi-tenant cluster that we can have many projects using the same Storm cluster to process their own millions or billions of transactions a day. And it's also given us a common API that we can use, right? So anyone that wants to do real-time data can use the Storm API, both on the the front end and the Spout side to input data, or on the back end to process data downstream to various data marts or other data streams.
So we talked last time about students wanting to get into this, to actually sort of go and try, look at some data sets, play with it, sort of try and extract. What would they do for Storm? What sort of data sets could they look at with Storm?
Yeah, so one of the best things, and I've played with this myself, is just connect to the Twitter firehose. So Twitter makes their, some of their public data available through a firehose that you can connect to it and get a bunch of tweets just sent to you, and you can try to process them through Storm and solve different types of problems, like what are some trending things happening. You could try to just search for keywords in your topology. So you could build your own system which says, okay, anytime this certain celebrity gets named, I'm going to count it up and see how many times they're getting tweeted about in a given time period. So I think the best application, I mean, I think there's other options, but just connect to the Twitter firehose and you could build a Storm solution for that.
Okay, thank you.
In our last video, we saw how one user can write a Storm program by writing his programming logic inside bolts and possibly spouts and connecting together and creating a topology that he can submit to the Storm framework running on a cluster to run his application. Now in this video, we'll look at how Storm really works. And different styles of programming in Storm and in general in stream processing systems all depend on what you want to do about guaranteeing message processing. Different streaming systems make different decisions on how they want to handle the message processing guarantees, and there are basically three main flavors that we are concerned here. the easiest way of handling message processing guarantees is to not give any guarantees. This is like, for example, the old S4 streaming system was working, basically, and it's open source. Basically, any event or packet that is dropped by a failure of a hardware component, software issues, drop packet, network traffic, any event that is dropped, the system doesn't do anything about it. Okay, that's one way of doing things. The other way that we are concerned in this video mostly is at least once processing guarantees. That means that when a tuple comes into the system, goes out of a spout, the framework guarantees you that this tuple will not be missed. It will be processed at least once. Now, to be able to do that, the system might play some tricks that might end up running the processing logic on the tuple more than once. And we will see examples in this video. Storm handles this style of message processing guarantees by using tuple trees, anchoring, and spout replay. And I will talk about these in my upcoming slides in this video. But the third one that is interesting is when you want to provide exactly once guarantees. So you want the system to process every event that comes into the system once at least, and exactly once, no more than once. This is, for example, like Hadoop processes things, right? It's batch, yes, but when you say I want to do this logic on my input data, it guarantees that every input data set or record is only processed once. This is the focus of our next video, where we will talk about Trident. But for now, let's get into the at least once processing provided by Storm. The main mechanism that Storm uses to provide at least once processing is tuple trees. So what is a tuple tree? A tuple tree talks about a data structure handled by the framework, so the user doesn't necessarily see the tuple tree or do any interaction with it. Of course, the user has to tell the system some things, and we will see in the next slide. But the idea of a tuple tree is that, say you have a tuple coming out of a certain component of your system, say Spout. Every tuple that comes out of a Spout becomes the main node or the root of a new tree. So for this example, let's think back about the word count streaming example we were looking at in the last video. We had a Spout that was creating sentences from Twitter API, for example. We had one bolt after that that was splitting the sentences, and we had another bolt that was counting, right? So in this case, the first tuple that goes out of a Spout becomes the root of the tree. The first bolt creates a set of tuples based on its input. Each of these tuples becomes nodes in this tree. And as each of these tuples are again processed by other bolts and create tuples, again, these tuples are added to the tree. Now, the main idea then is that a Spout tuple is not considered fully processed until all of the tuples in the tree have been completed down the road. So the tuple coming out of the Spout becomes the root of the tree, and it kind of keeps track of this tuple by relying on this tree that the framework is taking care of. And it doesn't consider the life cycle of this tuple done until everything down this tree are all guaranteed to have been processed. we can then give it a specified timeout. And if within that timeout period, this whole tree is not completely processed, the system considers some of these tuples lost, and the Spout tuple is replayed. We will see an example in the next slide. The way this whole mechanism works is relying on certain special tasks in the system called anchor tasks that keep track of these tuple progresses. And this is what we call basically the anchoring mechanism. Let's look at a programming API for the user to see how the user can tag into this reliability API. Let's assume this is an execute function. We saw that to write a bolt or spout, the user has to overwrite the execute function of the parent class. So let's look at this execute function. As an input, we have a tuple. Basically, what you need to do, and let's say this is our splitter tuple, splitter bolt. So what it does, it gets a sentence as its input and creates or emits a tuple for each of the words in a sentence. Okay. What the user has to do to tap into this reliability API is to, first of all, ask the system to keep track of this whole tuple tree. Anytime that the user does an emit of a new tuple, we call it an anchoring event happening. Anytime the system sees an emit, it creates a new edge and a new node in the tuple tree. So if you remember from the previous slide, if this first tuple was the top of the tree and was representing the sentence coming in as tuple, when we are creating multiple words for each of these, when we say collector.emit, the system will create a new node in the tree. The next part of the API, and let me wipe this off. The next part of the API is now up to the user. When the user's code assumes that the processing of a certain tuple has finished completely and successfully, then the user's code can basically send an acknowledgement. So it can say, collector, I'm sending you an acknowledgement, and I'm telling you that I am done processing the input tuple. So now that we have made a tuple tree that keeps track of the tuples emitted and marks them as finished when the user says ACK, what happens if there's a failure? If there's a failure happening somewhere in the cluster that Storm is running on, what happens is that double processing can occur. And in my next slide, I will show you how. It depends on the use case. For some use cases, this might be all you need. Sometimes you don't have very critical tasks, and just guaranteeing once processing is all you want. This is, for example, user clicking on advertisements. You want to make sure every click is counted. Now, let's say one click is double counted, that's fine. Or for example, if you're looking at statistical trends for some, say, your input is coming from Twitter and you want to figure out statistical trends of what is raising and what is not that interesting. Okay, double counting some tweets once in a while is not going to make much difference. Now, one thing I want to make sure is that your Spout itself has to support this idea of replay. So when the infrastructure sees a timeout for a tuple tree, what it does, it tells the Spout, okay, I figured out there's something wrong in the processing, go replay. It's now the job of the Spout to replay and recreate that tuple so that the whole stream of events can take place again. Not all of the Spouts coming with Storm have that, and not all of the messaging infrastructure supports replay. So if you want to have your Spout provide this reliability measure, you must make sure that the Spout itself can do replay. Now let's look at an example, how this whole scheme works in action. Again, we're talking about our word count example. You have your Spout that creates sentences. You have a split bolt that gets a sentence, splits it into words, and then you have a count bolt that counts the number of words. Now, we also have a new component. We have an ACR task that creates a tuple tree and keeps track of things. Okay, let's see how it works. A new tuple is created by the Spout. It tells the ACR, it says, so the Spout code, you can imagine, says emit this new tuple. You know, the cow jumped, so on and so forth. And then once it says emit, the ACR task is notified, and it will create a new node for it in the tuple tree. Then the tuple comes over to the split bolt. And as a result, the split bolt, as we saw the code for it, will say emit word 1, word 2, word 3. Each time it does an emit, the ACR task is also notified and will create and add node to his tuple tree. Once creation of new tuples is done, the sentence is done. So the split bolt will say collector.ack for this tuple. Now we can mark that tuple as done, but still its children aren't finished. So we still have to make sure all the nodes as the children of that tuple are finished. So the job is still not done. Okay, things move up to the next bolt. We are using consistent hashing, field grouping. So as you saw, we have two tuples that have the same contents. So they will then move to the same bolt, the same task of the bolt to be processed. Again, the word count bolt here does some processing. It emits something else. By the act of emitting, it will create tuples in the tuple tree by letting the ACR know. What happens right after is that the count bolt, once it emits the new tuples, it then sends an ACK for the input tuple. And then the ACR will be notified that these tuples are done, and it will remove them from the tuple tree. Well, we still have some. So it keeps track of things and waits until all of them are acknowledged. What happens if there's a failure? Let's say this certain tuple was not correctly processed. So we don't have it in the output. What happens is that when it was emitted, the ACR was notified, but then it somehow doesn't make it all the way to the final count bolt. And when these things are done, we are still waiting for that missing tuple to finish. After the timeout is finished, the ACR will decide that, you know what, the tree isn't finished in the amount of time allocated to it. So it will then, ACR we'll call the Spout again, and we'll say, remember that tuple that you started this whole process from? It was not completely processed. Please replay that tuple again. The whole processing will continue again. It's the same series of events happening, and hopefully this time it gets processed and it gets and the whole tuple tree gets acknowledged. Now, of course, it has a certain amount of overhead. Different research papers have showed that the overhead could be large. So it depends on the use case that you want to use. Just know that this mechanism has a certain amount of overhead, and sometimes the overhead could be considerably large. So you have to find a good reason to enable this mechanism. Otherwise, Storm's performance might not be satisfactory. In our previous videos, we looked at Storm, how we can write an application using Storm, how Storm runs on a cluster with Nimbus and supervisors and whatnot, and how you would write your program using bolts and spouts. And we also looked at how Storm can utilize a tuple tree mechanism using anchoring and spout replay to provide at least once processing guarantees, so that the tuple comes into the network, the topology, the framework guarantees that this tuple is going to be at least once processed, maybe more. But what if you really want exactly once processing? And that is what Trident tries to do. That's what we talk about in this video. That question has another side of the coin. If you want to guarantee exactly once processing of your tuples, that's also similar to asking, how can I store state in my streaming system? And the reason that is that if you want to guarantee exactly once, you want to provide for cases when one machine processes the data, and then after it processes a certain tuple, it dies. Well, it has processed it once, so you don't want to process it again. But the system has died, so if when it boots back up and restarts, its memory is refreshed and it doesn't have any notion of what it has done before. So here is a case where you have to store the state of your topology somewhere in a persistent storage like a hard drive. Now remember that Storm itself does not provide that functionality. Storm is designed as a streaming system. Tuples come into the system from one machine, hop into another machine, being processed, hop into another machine, and then they're done, right? So that's the simple model Storm provides. And if you want to add storage on top of that, Storm doesn't do that. This is why we have a this could be a problem. If your bolt goes down after 3 weeks of aggregating data and processing on them, and if you haven't stored it anywhere, well, too bad, right? Your 3 weeks of computational work has gone down, and you don't have anything to show for it. This is what Trident tries to do. Trident tries to provide exactly once semantics and guarantees. So what happens is that in Trident, state itself is treated as a first-class citizen. It's added definitely on top of Storm, and it's everywhere. Now, the exact implementation of how you want to store the state is up to the user, up to you. There are many pre-built connectors to various NoSQL stores. We will have a video actually in our next module talking about some of these NoSQL stores, such as HBase or other databases. And you can use those to store the state of a running topology. What Trident does is allows you as a programmer a high-level API that you can use for storing your state. So let's look at that example. Again, let's continue with our running example of word count. And here I'm just showing, say, the split bolt of it. So the first slide here is the easy part. Then the next slide, I'll show you how the magic happens. So here you're creating a new class, again, split, like we did before. But this time, I'm extending a different parent class. This comes as part of Trident. But if you look at it, it's pretty similar to what we had in Storm. So you overwrite the execute function. Instead of getting a Storm tuple, now you get a Trident tuple. And instead of having a collector to collect your things, you just have a Trident collector. And basically, you do the very exact same code here. OK, so this part doesn't do the magic. I mean, the framework handles things, but your code doesn't need to change in the bolts itself. So what you do is you get the sentence from the tuple extracted, and then for each word in the sentence string, you split using the space character, for example, and then say collector emit new values. Remember that unlike Storm's anchor functionality with tuple trees and anchoring and spout replay, you do not need to do hacking here. So you don't need to say once this processing is done for the sentence, you don't need to say ack sentence. This you do not need to do that in Storm, in Trident anymore. The system takes care of that. How? Now the magic happens here. Here we create a topology, but now we subclass from Trident topology instead of just the regular Storm topology. From here on, the structure that you will see here is using a certain programming pattern called the builder pattern, which is quite prevalent in industry. So you'll see in many systems. And the idea here is that each method call returns the very same object, just remembers what you've done in the previous method call. So it ends up in writing like a neat syntax that you can, kind of looks unfamiliar from Java because you keep calling dot, 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 dot on one object, and it's kind of strange. But with builder pattern, actually, you can do that. And I'll refer you to look into builder pattern out of this class. But anyway, so back here, what you do is that now we create a new Trident state, right? And then we can use the split class that we just wrote that uses the Trident pattern class. And just write our functionality here. So we can say, hey, I have a new stream, a new tuple stream. Let's connect it to some spout. So then what happens here is that now we just create a Trident state object, and we tell it how the state is created so that it can store it. We just call it word count. Let's say we start from the topology object that we created. We use it here. We just say, OK, let's create a new stream. The stream starts from the spout. And then for each tuple coming out of the spout, use the split class to split the sentence into words, group the words by the word, and eventually, this is where it becomes interesting, do a persistent aggregate. That means aggregate the word counts. And here's how I'm telling it to use the count class. So it's aggregating what? It's aggregating the word counts. But it's also doing a persistent aggregate. So it's storing it inside whatever mechanism you decide. How do you decide what class, which classes or which data store are used? It's using this structure here. that you're telling it, hey, out of the memory map state, so in this case, let's say I want to store them in the memory, but you could have other classes. But this class tells you that, hey, I want to use memory map state, use the factory class to get an object of that class, use it to store the state. And finally, you can give it a parallelism hint so that it knows how many tasks you want to have for this certain Trident bolt. So as you can see, it can be quite concise. Using the builder pattern, the designers of Trident have managed to make a very concise and readable syntax. And by using certain persistent storage classes, that some of them come with Trident and some of them you can overwrite or write your own, store the state of your topology running Trident topology in a persistent storage state. In this lesson, we will talk about the insides of Apache Storm a little bit. We designed this lecture hoping that some of you might be interested in looking inside the Apache Storm and trying to figure out how the whole system works, maybe try to contribute to the open source project a little bit. And to be able to do that, you need to see how things are connected. Now, Storm is written mostly in Clojure and then some in Java. So it's a little bit not easy to get into it. So that's why we designed this lecture, to let you start fiddling with the Apache Storm itself and hopefully start contributing to the open source community. So in the first video here, I will talk a little bit about the environments that we kind of need to play around with Storm, and some of the things around it, Thrift compiler. And then in the coming videos of this lesson, we will talk about some of the individual modules. Of course, I don't want to cover everything in Storm. It's almost impossible to do, even in like a whole 1 week video. We might actually need like a whole course for that. But I will just try to show you how to start tackling things like the main modules, the main daemons. You have Nimbus, you have Supervisor, how to look for some of the things and how the code is organized. So without further ado, let's start looking at things here. So the first thing that I want to show you is the IntelliJ IDE. This is a very good free to open source users IDE, optimized to work with Maven-based projects. And a lot of these open source projects that we talk about, Apache Storm, Apache Yarn, a lot of other important projects, all of them based on Maven these days. So I personally like IntelliJ IDE, and to get it, you just need to go to IntelliJ. You can just directly go to the download link, and you'll see that there's a community edition there for free. You just can get the community edition. That's what I use. It's great. OK, so once you say you download and start the IDE, to import Storm, you need to first have Storm in your computer, which I will show you in a second. But once you have that, all you need to do is say go to File, New, Project from existing sources. And then in your directory structure, scroll to where you have stored Storm and just say OK. And from there on, just click Next, Continue, Continue. It will figure everything out and import the project like it is done for me here. So that's the first half. The other part that I want to show you is how to get the Storm code itself. You've installed an IDE. Now let's go get the code. One thing I should mention here is that I use the IDE just for navigating in the code personally. navigating the code, looking at the code, making edits and everything, but I don't personally run things from the IDE. It's usually much easier to run things from terminal. If you have Linux or Mac machine, it's easy. You have a terminal always built in. If you have Windows, there are software applications that you can install. So let's see how to get the Apache source code. What you need to do is go to github.com/apache/storm, and it brings you a page like this. And you can, first of all, take a look at the code structure right here in your web browser. So for example, in Storm, a lot of the major code of Storm is stored under the Storm core directory here. So I can click on Storm core and navigate right here through source, maybe JVM, backtype Storm, and I can take a look at some of my code right here. For example, some Java code declaring the constants. Okay, so this is pretty cool. You can actually do a lot of browsing through the code right here in your browser. One really neat shortcut in the GitHub page that I really like is pressing the T button, T as in tango. You can press the T button and just type the file name, any part of the file name. For example, I'm looking for the Nimbus code. Let's say I'll just type Nimbus, and see even without typing the last S, it goes and finds all the files that has Nimbus in it. Okay, let's say I want to look at nimbus.closure. I can continue with saying, hey, Nimbus CL. Okay, it says, do you want to look at Nimbus closure? And now I'm looking at the Nimbus closure code. Okay, so these are pretty cool. Now let's see how we would download this code from the website, which, by the way, is interesting to note that this is a cloud service, right? There are some servers at the GitHub Foundation, and when you want to download code or browse the code, you are really connected to their web services or cloud services, as you wish. All right, so let's see how you would download the code. Of course, there are lots of tutorials. I don't want to go through that. Just to quickly mention it, you need to set up your private public keys. So what you need to do is first of all, you need to sign up. If you haven't signed up, make an account, sign up, and then go from your profile here, go to settings, and you see that there's a SSH keys. You need to go get your public key and upload it here so that when you want to download the code, the GitHub server can identify you as who you are and who you signed up in the website. Okay, let's go back to my Apache Storm project. Assuming that you've already set that up, uploaded your public key into the machine, and there are lots of tutorials to show you on the internet how to do so. You can get the SSH. There are different ways of downloading the code. You can get HTTP subversion. What I like personally is the SSH. So you need to click on SSH and then copy this link that it gives you here. You can just press this button and copy it to your clipboard. And go to a terminal. Let's see. I'm already in the Storm directory. Let me mkdir, say Storm new, just to show you how it's done. Cd Storm new, and I can say git clone that, and it goes, and you see it doesn't even try to authenticate me or ask me a password because I have already uploaded my public key, so it knows who I am. One thing I should mention is that this is good for if you just want to try something on your machine. If you at some point decide to contribute to the open source project, what you need to do is to first fork the Apache open source project, Apache Storm, and then when you have forked it, you will have, instead of, say, Apache Storm written here, you will have your username /storm. Then you can make changes in your local computer, push your changes to your forked repo, and then submit a pull request. And then the project organizers will look at your code, will do code reviews, comments, and eventually will pull those changes back in. But for now, I don't want to fork. I can just use this because I don't want to submit code back to the project, at least for now. All right, so in the last video, we saw how to get the Storm code and how to set up the IntelliJ. Now let's look at the source code of Storm and figure out a couple of things. First thing I wanted to show you before going through the code is I want to tell you that the Apache Storm project is written in a couple of languages. You have a lot of the code written in a language called Clojure. Now, Clojure is a very interesting language. It's a functional language, functional programming language. So functions are, the main theme of the whole concept. And it's also a dialect of Lisp. Lisp was an kind of an old invention. It's been there for quite a while. A very powerful way of thinking about programming. Completely functional and based on sets and maps. And it's an interesting way of thinking about programming. So I would encourage you to work on Clojure. And the reason is that it's a modern language. Lisp itself, well, it's been there for a while. But Clojure, it's a recent development, I think a couple of years, 4 or 5 years probably. And it's designed, first of all, to run on top of JVM. So anywhere you can run a JVM, which is basically everywhere, you can run Clojure. So that's one thing going for it. But aside from that, since it's written on top of a JVM, you have complete Java interoperability. You can bring up Clojure, write a Clojure code. In your Clojure code, you can load Java objects, load Java libraries, create new objects of Java types, call the Java objects methods and functions. Basically, it's any Java code that you have, you can just directly deal with it. You don't need to do anything extra. So that's actually a great thing. The other thing that Clojure has going for it is speed. It is basically compiles things into Java and kind of like a just-in-time compilation. Java itself does a JIT. So Java is pretty fast these days. There used to be a time way back when Java was kind of slower, but nowadays Java is actually pretty fast. Maybe not as fast as the C language, but not much far behind. And it's way faster than other interpretive languages like Python and Ruby and those things. So, and Clojure is just as fast because it just compiles things to Java and runs. So, it's great. And the other thing, one last thing I want to mention about Clojure is that it has this thing called REPL, R-E-P-L, that allows you to interact with your program like an interpreter. So you can just bring something and you can just type and say, hey, make a new object of this class. It will say, OK, I made. Here's your object. And then you can interact with it, say, OK, call this method of that function. And it'll just do that. So it's a very, very powerful tool to do debugging and to do development even. So I'd encourage you to look into Clojure as well. Now, a lot of Storm is written on Clojure. The other half of Storm is written in Java. And I said they have complete interoperability, so there's no problem there. There's lots of code in Java. For example, a lot of scheduler code, which is one of the main important parts of the Nimbus, the master node in the cluster, is written in Java as well. Okay, now that we talked about the structure of code in Apache Storm, that is half of it is written in Clojure, the other half is written in Java. And by the way, there's a little bit of native code, as in C code, that gets compiled to native code in there. Not too much, just a little when you want to launch workers, for instance. So worker launcher is written in C. Now, one other major component of Storm is its use of Thrift. Now, of course, we had a whole lecture back in week 1 about Thrift. Here, we'll see how Thrift is being used in the Storm open source project and how it can actually help us write a distributed system without getting into the gory details of all the deadlocks and live locks and hangs and all of those things that writing distributed systems involve. So without further ado, let's look at some code. The first thing I want to show here is that you need to have Thrift installed on your computer. Now let me go to the Thrift webpage. Apache Thrift, another Apache project, open source. It's great, and you can download the Thrift code from here, and you can install it. There's lots of tutorials on internet showing you how to install Thrift on your machine. Now, I have a Mac, and I'm pretty sure Linux has similar things. So in Mac, I just install Homebrew. Homebrew is a very nice package manager for installing Linux-based packages. So for example, in your Linux, you usually have, for example, let's say Ubuntu. You have apt-get install Thrift. Here in Mac, after I've installed Homebrew, I can say brew install Thrift. I will go and try to install it. Of course, in this case, it didn't because I already have Thrift 0.9.2 already installed. But if I didn't have it, it would just go download everything required for Thrift and find the latest version in the repositories, which at the moment is 0.9.2, and go and fetch it and install it. Nothing else I would have done. The same command would go and install it. OK, so I have Thrift installed on my machine, right? Let's look at how Thrift is being used. In the Storm core, so I go to I've already set up my IntelliJ. I've already imported the project. Let's go to Storm core/source. And if you don't have it, if you go to the web page, you see that under Storm, there's a Storm core and source directory. This is where we want to look at. I can click on storm.thrift, or I can look at that in my browser, in my IntelliJ. Now, I haven't installed a plugin to make it like, syntax coloring, so let me switch to the browser and let's look at the Thrift code a little bit here. So opening this up. So as we talked about in our Thrift lecture, when you want to use Thrift, you can define in a file name .thrift file what sort of communications you want to happen between your nodes in a distributed system, right? And you can actually define a lot of those. You can see that a lot of those are defined here. Let me just go out a little bit. So for example, just let's take a look at this. I have a struct here, topology info. The topology info tells you that, hey, if I want to get the information about a topology, what I need to provide in a network call that goes from, say, supervisor to Nimbus, what you need to pack into this network packet is a string called ID, a string called name, an integer 32-bit integer called uptime seconds. You need to provide a list, so that's a Java list object transferred into a serializable object called executors, status, so on and so forth, right? So that's just one example. And then the other thing that is kind of interesting here is we can define services, right? So we have a service called Nimbus. This is how Nimbus will act as a daemon running on a single machine, but it can provide such and such services to other nodes running on other machines in the network, right? So in my service Nimbus, I can submit a topology, I can kill a topology, I can activate, deactivate, rebalance, so on and so forth. And here in Storm.Thrift, I define how these should look like. For example, let's take a look at this one, activate. Here I'm telling it that you should provide a function called activate. Someone from some other part of the network should be able to call this, provide you with a string that is really a name for the topology that you want to activate. And that's all the parameters that you give. Your function can throw a not alive exception or authorization exception, right? And we will see how these are implemented. But Storm.Thrift is just a text file, right? It's just a text file that you write and you define what I want to happen. What happens after this is that the Thrift compiler will look at this file and will go generate a lot of other Java files based on what you have here. So let me switch to terminal and clear it. OK. So I'm in my Storm new directory that I just got from GitHub. Let me show you where things are. So you can go to Storm core and go to source. This is the file that we just talked about, Storm.Thrift. It's here. And the compiler, the commands to compile it is also already in a file here called genthrift. So I can cat genthrift. And you see that basically it removes some files, makes some files, and then it calls the Thrift compiler to generate the code. So all I need to do is just say gen thrift and just run it. It doesn't say anything, nothing shows up, but what happened in reality is that it went and recreated a lot of my files, a lot of my generated files. And to show you, I can say git status, and you'll see that as a result of calling the compiler, a lot of these files in the JVM backtype storm generated directory are now created again. So let's go and take a look at one of these files. And I'm going to open here and try to open the nimbus.java file that we just looked at the service, right? This is a file in source JVM backtype storm generated. And it shows the service that is created as a result of having that service Nimbus portion in the Storm.Thrift. Okay, so far I've talked about the daemons, right? I've talked about the Nimbus, supervisors, workers, executors, and tasks. Now let's take one last look at another part of the Storm project. This time I want to take a quick look at the scheduler part of it. There are two main files that I want to show you. One is an interface designed to make the scheduling framework for Storm kind of pluggable so that new developers, you for instance, can come and create new schedulers without requiring to go and touch everything in the Storm source code. So whenever you want to, for example, create a new scheduler, all you need to do is instantiate a new object, write a new class, overwrite whatever iScheduler requires to be overridden, and just create a new scheduler. In this video, I'll also quickly look at the multi-tenant scheduler, which is the current default scheduler in Storm. It's a pretty simple scheduler, and we can see how it works. OK, so to do that, let's take a quick look at this. You have two parts in the Storm directory for schedulers. One is under Storm core source closure backtype Storm scheduler. And then there's a counterpart to this. Let me close closure and go to JVM. JVM backtype Storm scheduler. You'll see that in this case, there's more code for the scheduler in the Java side of things compared to the closure side of things. A lot of this code is used here for figuring out how to do scheduling in general. And then there is the multi-tenant directory that is one of the schedulers in Storm. There's a couple others, and there's a couple other open source projects underway that are about to be committed to Storm. So by the time you see this video, or maybe a month or two after this video, there will be even more schedulers in this directory. So I want to show a couple of things. One is the iScheduler interface. This is basically the primary way that Storm allows new contributors, like yourself, hopefully, write a new scheduler. Basically, what you need to do is implement this interface, iScheduler, and just what you need to do is implement two functions, the prepare function and the schedule function. Schedule function, what it does is it gets two things, an object of type of class topologies and another object of type cluster. Let's quickly look at topologies and cluster and then look at one instance of scheduler. So what topologies does is basically a wrapper around a lot of topology details objects, right? So Storm at each instance is running a number of topologies for different users. This topologies object kind of keeps track of information about all of these topologies. Information about a specific topology is in topology details, which is a class right here, same directory. In topology details, basically what you have is topology ID, the configuration for that topology. It's a map that stores a whole bunch of key value pairs that store the configurations. You have a map showing the executor to component mapping. So remember that an executor runs different tasks. So you kind of need to know the set of executors across the cluster that are running different tasks for this specific topology. You keep that information here in executor to components. So you see that most of these functions here are just simple accessor functions. There is also one function here, select executor to component, which given a set of executors will go and find out which one of these executors are really running tasks for this specific topology. All right, so all of these information are then gathered in the topologies class. So it has a map of topology details. So topologies knows all of the topologies running in the system. And then in the scheduler, when we pass this topologies object to it, we kind of give it a snapshot of all of the topologies running on cluster. Now, the other object here is, of course, cluster. Taking a look at the cluster object right here, we see that cluster Java is kind of a snapshot of what is happening in the cluster at each moment. The cluster mechanism is how Storm keeps its state. Nimbus itself doesn't keep state, right? So it can crash and it can restart without going through any catastrophic failure because itself doesn't store its state. What it does is that it stores its state in Zookeeper. Now, it does that through a class called cluster closure. This is how we talk to the Zookeeper. You can see that the first thing that we do in the cluster closure is making connections to the Zookeeper. We have making a client to Zookeeper and then talk to Zookeeper to set or get state into Zookeeper. So cluster closure is our main method of accessing the state of the system. Now, every time that Nimbus decides to run a make assignment phase, every 10 seconds or every 30 seconds that decides, OK, a new round of scheduling should happen, it creates a new object of cluster.java type, populates it basically from cluster.closure, and then passes it to your schedule function. So that now not only you know what topologies you're running, you also know what the state of the cluster is at this moment. OK, so now that we talked about these, let's look at one implementation of the iScheduler interface. There is, of course, in the same Java directory, there is a multi-tenant implementation that if you look at it, you will see that it is implementing the iScheduler interface. But I want to show you something else. If I back out of the JVM directory and again into the closure directory, closure backspace backtype storm scheduler, you'll see that there are some scheduler implementations here. Let's take a look at the, let's say, the default scheduler. Default scheduler is, you see it's like just 2-3 functions returning closure. As you remember, I said closure is very concise, so you can write a lot of functionality in a few lines. And you see it's completely has interoperability with Java. Why? Because you can see that my closure class right here says that, hey, I want to implement backtype storm scheduler iScheduler. That was a Java interface, and now I'm in my closure code, I'm implementing that Java interface. What the default scheduler does is that when the default schedule function is called, it goes and prepares some of the required variables. It reads the topology ID, gets the number of available slots, gets the available all of the executors, and then from there it finds the alive executors, the ones that are assigned to it. And eventually what it does, it goes and calls the proper function in the event scheduler. So the default scheduler uses the event scheduler. Let's take a quick look at the event scheduler. Well, let me quickly go back. the functions that I need to implement here are two functions, schedule and prepare. Everything else is local functions. And you see that to implement, and this is basically to implement the interface. When calling the schedule, it calls a default schedule function, and default schedule function goes on and calls the event scheduler schedule topology. So like taking a look at the event scheduler, you'll see that the schedule topology function basically does some similar things, gets the executors, available slots, and then eventually does a very simple idea of basically round robin, finds new assignments by putting into an empty map, a map of vectors, and just does round robin here. Okay, so this basically wraps up our discussion into looking inside the storm and seeing how basically the interplay between Clojure and Java. Clojure at first might look a little bit intimidating, but once you get to play with it, it's actually a very nice language. Fast, concise, could be very expressive, and quick to write scripts. And if you get to play with the REPL, you'll see it has a lot of power to help you implement a lot of these things. So for example, when debugging these, we can basically bring up REPL and create a new instance of the whole Apache Storm project running in your REPL, and you can interact with it while it's running. So it's a very powerful tool to do debugging.
Hello and welcome. I'm Bobby Evans. I'm an architect at Yahoo, responsible primarily for a few big data open source projects, Storm, Spark, Kafka, things that are kind of the next generation big data projects. So I want to talk a little bit about what we do at Yahoo and what I do in particular. So Matt Aarons, I think he gave a talk a while back. He provides a lot of the value to Yahoo. I mean, he produces the pipelines that count all the pennies when you click on an ad that helps pay my salary and his salary. What we provide, what my group provides, is a platform for his group to be able to run on. And so it kind of fits with the building. One of my colleagues, Reza, pointed out that the platform guys all sit on the bottom floor, and the pipelines people all sit on the top floor. So I kind of showed it here. So we provide a hosted platform for not just the pipelines, but all of Yahoo to run on. So some of the groups that use our stuff is not just the pipelines, but Flickr, news, sports, search, everything that Yahoo does flows through these platforms, whether it's Hadoop or it's Storm or whatever else. A lot of them actually are on both to be able to get both low latency and massive scale processing. So what is it that we do? We primarily are concerned with making sure that these tools that we provide, in addition to the normal software engineering things of providing new functionality for people, fixing bugs and pain points that they have, but a lot of what we do is making sure that they will scale to a scale that Yahoo runs at, making sure that they're secure, and then making sure that they're easy to use. So scale, what is Yahoo scale? Well, here's kind of a slide for this year, 2015, of some of the things that we were doing at the beginning of the year, both with Hadoop and Storm. So the largest Hadoop cluster we have is about 5,000, is over 5,000 nodes. The largest Storm cluster is still only about 300 nodes, but if you compare that to other people and their stream processing, that's still pretty big. And the total number of nodes that we have for Hadoop is over 40,000 nodes. And for Storm, we're only at 2,000 nodes. But if you add all of that up, we're talking about hundreds of terabytes of memory and hundreds of petabytes of disk space. Many of these people, many of these groups that we work with are processing hundreds of terabytes of data every single day. And so this is a massive scale beyond what a lot of people deal with. And it produces lots of interesting problems. So one of the problems that we're working on right now with Storm, which is a stream processing system, is how do we schedule to be able to take advantage of this? That if you look at a network topography, how the different machines are fit together, it's not homogeneous. Every node they can talk to every other node, but the speed that it goes at and how many points that it has to go through are completely different. What I'm showing here is a fairly typical network called a fat tree. But there are lots of other network topographies too, where some of them are even just random, where they try to connect as many random ways as possible to hopefully get a route that's short from one place to another. And so the software that we write has to be able to deal with these different pieces. That if we just place things randomly, place the tasks randomly on these different computers, we're going to, as the network increases, as the size of the cluster increases, we're going to get statistically much, much more flowing through smaller pipes as we go. And that becomes very problematic. Now, this may seem simple, but it's been proven that this isn't just the knapsack problem, but this is a multi-bin knapsack problem, which you can go up to Wikipedia, read all about it. It's some very interesting things. At the scale we're working at, we can't just brute force it. It's NP complete. So we have to look at heuristics. We have to try and do balancing acts to be able to deal with this. But what's more, this is not a static system, that once this thing comes up and it starts running, people can interact with it. Somebody can say, oh, I want to start doing something new over here, and I want to shut down this old thing. So now, actually, it's the halting problem. You can't predict the future. We can't figure out what people are going to do. We can play some games with that and see if people do things regularly, like with Hadoop. But for Storm, we can't really do that. And so we have to come up with these really interesting heuristics to get the best fit possible, and then decide what happens when failures happen. Because in the real world, nodes go down, network switches go a bit crazy and start sending random data. Things happen, and we have to be able to detect these things, adjust, shift around. So it's very interesting and hard problems that show up when we're at scale. Some of these other things that we deal with is with the massive amounts of metadata that we have. So I recently gave a talk at Hadoop Summit on how we've scaled Storm to the level we're at now. A lot of it is around the metadata that we're collecting and processing for all these different systems. And to be able to work around these issues, you have to understand in pretty decent detail what the hardware is doing, what the software is doing, and how they interact with each other. So in this one case, we had an issue with Zookeeper where it couldn't process as much data as we needed. Typical spinning hard disk runs at about 80 megabytes a second. Zookeeper, it is an in-memory database, but it writes all of the data out to disk to be able to have persistence. And so that is the limiting factor in Zookeeper. As we go through and we looked at the different things we were writing into Zookeeper, there was scheduling information from the supervisor heartbeats saying what they're up to, and then we have heartbeats from each of the different topologies. And those tended to dominate. And so when we looked at that, we were getting massive amounts of data being written from that. And we looked at a number of things we did. We compressed the data. We switched the data over to a new format that was more compressible, all kinds of different things to be able to get it smaller, but each of those were incremental changes. And so from that, we could see that the theoretical limit, the maximum limit we could run at was just over 1,000 nodes. And typically in engineering, you don't want to run at the theoretical maximum. You want to probably run about 50% of that. So that kind of set our limit of what a cluster could handle to about 600 nodes, and that wasn't anywhere near where we wanted to be. And so with that, we have to be able to then work around bottlenecks, understand what those bottlenecks are in this big, massive system, and to be able to go in different directions. And so because disk was the bottleneck in this case, we decided to move to a complete in-memory system. That these heartbeats that we were writing in, if we lose some of them, it's not the end of the world. That they're there mostly for liveness and a little bit about making sure that we get the right statistics. And so some of these hard problems that we look at with scale is how do we remove these bottlenecks and what the impact is going to be. So it's very much like performance tuning, but kind of harder because you have 100 nodes, 200 nodes, 1,000 nodes, and you probably don't even have all of that hardware available to you to be able to test things on. That you're doing simulations and trying to guess as to what this is going to do in the best case scenario and the worst case scenario. And so with that, we saw that we had removed disk as the bottleneck, and now it had become network that was the bottleneck in certain situations, depending on the hardware that you're running at. And so then you have gigabit network, which can do about 125 megabytes a second, best case. And so if we set the arbitrary limit of we want to download all of this data from this state store in 10 seconds, which seemed reasonable, that was the frequency that we do rescheduling in Storm, then that came up with a theoretical limit of about 6,000 nodes, which is great, but again, that's the theoretical limit. We probably want to do about 3,000 nodes at that point. But these aren't the only bottlenecks. We start running into other issues, like the scheduling issue, that if we're scheduling things badly, having a 3,000 node cluster, now we'll have hundreds of racks of nodes. So if you look at a data center, there'll be a single cabinet, a rack, filled with different computers with a switch at the top that is connecting all the computers together. And there'll be multiple of these racks in a data center if we have 3,000 nodes. And the more of these we put in, the more important it is we get our scheduling algorithms right. The other thing we look at is making sure that everything we do is secure, that your data is important to you. We want to make sure that somebody doesn't break in and steal it. And that's why it's very important to us. You look at these data breaches that show up all the time. We definitely don't want to be in the news as the recipient of one of those. And so every time we produce a new product or we want to go release an open source product, we need to make sure that we've gone through and secured it. This is a bit of a time-consuming effort because it really just involves understanding how all the different pieces communicate with each other, and then making sure that there's a way to authenticate anyone that is communicating and then have an authorization mechanism to make sure. A lot of times we try to use off-the-shelf components because I consider myself a smart guy, but I don't want to be the one writing the encryption algorithm, that I'm not the mathematical genius to be able to really come up with these things. And so in most of these cases, we tend to default to using Kerberos and off-the-shelf encryption systems. But again, we need to make sure that as we go through, that we've secured every single connection that exists, and ideally encrypted many of the connections as well. The final thing we want to do is we want to make sure that it's easy to use. And this is actually probably the hardest thing that we do, because we want to make it very simple for our end users to do. So that's a simple API. We want to make it simple for them to debug. But that's our end users. We also have people who run these clusters for us. So we want to make sure that it's very simple for these people to set up the clusters and to upgrade the clusters. Ideally, we don't shut down the whole cluster, all 1,000 nodes, because then people get angry at us. We want to be able to do it in a rolling fashion. And there are very difficult problems with some of these things too. That when you have one machine, failures will happen. But usually when a failure happens, the whole machine stops. We want to be able to have hundreds, thousands of these different machines together. And if one of them fails in a weird way, the whole system doesn't stop. So when I was working on Hadoop and we were creating the MapReduce version 2, we ran into a very interesting problem where you could have a split brain issue. And you can look that up on Wikipedia too. Essentially, it's a network partition. You have two different processes that think they're the one that's in charge, but they're not. One of them isn't. And if both of them are trying to do things, you can get situations where you have data corruption or other problems. And so these very difficult problems, we have to come up with solutions as a platform. We don't want to force our end users to think about these things. Oh, is this going to cause a split brain problem? Oh, if I write this out at this really bad time, is that going to bring down the cluster? Can I do a denial of service accidentally on the entire system, which is very easy to do at 1,000 nodes. So we want to make sure that everything that we have is going to be easy to use, that they don't have to concentrate on making it scale or on making it on these really difficult problems. We want to make sure that all they think about is, what is my algorithm? So if somebody's designing an algorithm for deep learning, they don't want to have to worry about all the 1,000 nodes and how do I get the GPUs and everything else that I'm using. We just want them to be able to ask, can you give me 1,000 nodes with GPUs, and I will handle the rest. So that is really what we do at Yahoo and the platform side, is trying to provide a scalable, a massive scale distributed cloud system that is easy to use and easy to debug.
Hello everyone. Today I have Bobby Evans from Yahoo with us, and he's kindly accepted to come here and talk to us about stuff that Yahoo does. So Bobby, why don't you introduce yourself to our audience?
Sure. So I'm Bobby Evans. I'm an architect at Yahoo. I work primarily on big data projects and kind of the next gen big data projects. So Spark, Kafka, Storm. We do a lot of streaming and iterative processing. We provide them as a platform, as a service at Yahoo.
Well, you mentioned an architect. What does an architect do?
Well, that varies from company to company, but at Yahoo, it's a little bit like a technical lead. I still write code, thankfully, but a lot of what we do is kind of setting the direction that we want to go in. So understanding how the different components in the system work together and how they talk to each other, and putting all those big pieces together.
Right. So you mentioned you oversee Spark, Kafka, Storm. Well, let's talk about Storm a little bit. Well, let's talk about Storm at Yahoo. What does Yahoo do with Storm?
So Storm is a stream processing system. So if you're familiar with Hadoop, I assume you've talked about Hadoop, that it really is batch. And so you'll get a large amount of data, you'll process that massive amount of data in one big job or multiple jobs to be able to come up with an answer. The idea behind Storm is that a lot of times the time from when the data shows up till the time that you actually get an answer, that you can react to that data, is critical. So like in cases of, say, think of a thermostat. If it took an hour for your thermostat to update, that would be really bad. Your house would be either too cold or too hot all the time. You want to keep that feedback loop very, very small. And there are similar use cases within Yahoo where we're trying to be able to deal with budgeting for ads and making sure that we show the right number of ads without showing free ads or not using up all of the advertisers' money. Things like that, where we want to have a nice tight feedback loop. And Storm provides that. And so as an event shows up, we can process and come up and update the result in near real time.
So Yahoo uses Storm not only for ad budgeting, but a whole bunch of other things.
Yeah, so like every time you upload an image to Flickr, Flickr will automatically tag it. It will use some deep learning algorithms to be able to say whether this is a picture of a puppy or a baby or whatever else. And all of that is done through Storm.
Well, Storm is a nice open source platform, but I assume Yahoo is a big enterprise, right? So what does Yahoo do on top of what we get from open source?
Well, so Yahoo tries very hard with open source to give back as much as possible to open source. So on top of is probably not necessarily the right words, is more of what contributions have we been putting in. And so some of the contributions we really try to do is we want to make sure that any project we use, any tool we use, is going to have security, is going to be fairly easy to use as far as being enterprise ready, and it can run at Yahoo scale. Even some of these projects that talk about big data, well, Yahoo is quite a bit bigger than a lot of other companies. There's only a small handful of groups that really run at the same scale we do. So there's obviously Google, which has their own proprietary set of things. But like Twitter and Facebook and LinkedIn, this is kind of a small group of people that really do the same massive amount of processing that we do.
Yes. So before we started talking today, you mentioned multi-tenancy. What do we mean by multi-tenancy?
Okay, yeah, thanks. One of the other things that we want to do is we want to provide these things as a hosted service that we don't...
Like a cloud computing.
Like cloud computing, so think like Amazon. That if you're at Yahoo, you don't want to have to spend the time figuring out how much hardware you're going to need, what you're going to do, what processes you install on that hardware. You just want to concentrate on what is the algorithm that I want to implement. What's the final result? And so with that, we want to make sure that we provide all of this as simple as possible. And so one of the easiest ways to do that is to have one large cluster that everybody can share. And that's essentially multi-tenancy. So it's multiple tenants all at the same time. Think of a big apartment.
So multiple programs, multiple Storm programs running on the same set of hardware under the control of the same Nimbus node. Well, I can say it because I had it in my lectures. But
yeah, so it's multiple different use cases all running at the same time and sharing the same hardware. So right now for Storm, because of the latency issues, we don't have multi-tenancy with Hadoop in the batch side. Technically that's possible, but because of resource constraints and things, batch doesn't really care as much about making sure that they're as strict with resources as Storm needs to be able to give those same guarantees. And so you have Flickr running on the exact same node and using massive amounts of CPU and even potentially GPU to be able to process images. All the advertising people that are using massive amounts of memory to be able to cache lookups for the different advertisers and other things.
All right. So let's go back in history a little bit. There is definitely a kind of a revolution in the way people do computing, especially big data computing, right? Before 2010, nobody had heard about clouds or big data, and enterprises typically did their own thing. And then you had this thing called Hadoop coming in. How did Yahoo, as a big enterprise company, respond to this change?
So Yahoo is, as most people know, is not number one in absolutely everything. We do have a lot of really great number one websites, but as far as in the back-end processing of things, Google was really leading the way at that time. And so they published a number of papers on, say, MapReduce and some of the other things that they were doing. And Yahoo, we saw these things, we saw how great they were, and then we decided that this is something that we needed to implement. But we also understand the power of open source, that if it's just us doing something, we can build something, it can be great, it can be fabulous, but if we can get other groups, other people involved as well, then it's not just us building it. And that can build on top of what we've done, and we can end up with a much better product overall. And so we decided as part of this, as we were implementing an implementation of the MapReduce algorithm that Google had published, to release it as open source. And so we hired some people like Doug Cutting, who had a lot of experience in open source, and we started working with him and with another group of people I wasn't on at the time to be able to build an implementation of Hadoop, of MapReduce, in the Nutch project. So Nutch is an open source kind of search engine, and Yahoo wanted to be able to use some of that technology to be able to do our own search indexing. And eventually Hadoop split off from Nutch as it became more general purpose, and it grew and it grew and it grew through all kinds of different things at Yahoo, and then we started looking into other pieces. So there were other things built on top of it, so SQL engines on top of Hadoop, all these other things. And at this point in time, Google actually has a term for being Hadooped, where they don't publish things nearly as much as they used to because they realize that open source does have this power, that groups of people can combine together to be able to follow very quickly behind them, but also catch up. And so Google now actually runs several Hadoop clusters, or so I've heard, because they've bought companies, and those companies use Hadoop. And it's more painful for them at this point to be able to force all of them onto their proprietary system than it is just to run a Hadoop cluster.
Interesting.
And that's the power of open source, and that's why we really do like open source at Yahoo.
Interesting. What about Storm? What about the streaming platform?
So the streaming platform, we've known for quite a while streaming is important. Yahoo initially wrote a streaming platform called S4, and we released it as open source. There were some architectural issues with S4 that made it difficult for adoption. That was really written for an enterprise system, and it had a few assumptions in mind that didn't make things very easy, so it was lossy. That when you're writing a program and some of your data can disappear at any point in time, people get nervous. Now that, for the most part, when you're doing analytics and you're trying to figure out how many people saw your website, statistically, you lose a tiny bit of data, it really doesn't matter. But it still makes people very nervous to be able to write it, especially for other use cases, say counting pennies for financials or things. And so S4 never really got the adoption that we were hoping for. At the same time, Nathan Mars, at a startup called Backtype, he wrote his own stream processing system called Storm. And Twitter bought Backtype. He convinced Twitter that they should let him release it as open source. They did, we saw it, and we adopted it. At the same time, lots of people have great ideas at the same time. There were a number of different groups that were also exploring stream processing. And so we have other things like Spark streaming that showed up. We have a commercial one called DataTorrent that recently announced that they're going to be releasing their core as open source. And then LinkedIn came up with Samza, and some really smart guys out in Europe came up with Flink. And so lots of different people all had the same idea. And it's really kind of nice to be able to see all these different groups all fighting each other to be able to come up with the best streaming platform out there.
Yeah, it's actually very interesting. Like maybe 5, 6, 7, 8 years, I don't know, maybe 10 years ago, there was a similar sort of a battle going on in the batch processing world, and then Hadoop won. And right now we have the same sort of battle in the streaming world.
But I think some of the difference, and this goes back to open source too, is that there were lots of different batch processing engines, but a lot of those big batch engines were closed source. And so they were done by these big enterprise data warehouse companies. And we say that it won, but there's still lots of big companies with lots of big data warehouses out there. It's just all of them are now trying to integrate with Hadoop because it can do things that others can't do. And it is open source, which gives a lot of people confidence in that if they go with one vendor, that vendor closes shop, there'll be another vendor, and even if all of them close up shop, well, at least you can hire somebody to still run the software that you're running.
Right, right. Actually, I want to get into detail a little bit. So we're talking about Storm and, of course, a lot of its competitors. One particular thing that I've read over internet and get feedback from some people is that Storm is written in Clojure. And tell us about that decision. What do you think about it?
Okay, so a lot of big data processing tools are written in Java. If you go back and you talk to Doug Cutting, he wanted to learn Java when he started writing Hadoop for Nutch, so he picked Java. And then all the other tools started interoperating with each other based off of Java. Java is a great tool, but there are a lot of other things that are kind of lacking with it in some areas with languages. And so a number of people have written higher level languages. So you get things like Scala, which is very popular. A lot of big data tools are now written in Scala, and they interoperate quite well with the rest of Java. Clojure is a Lisp language that runs on the JVM, so it can interoperate with the rest of Java. So Some people find it difficult to look at Lisp and really grok functional programming. I understand that.
I was like that at the beginning. When I started looking at Clojure, I was like, wow, this is hard. But then it grows on you.
Yeah, and so Storm, when Storm was first being created, they wanted to pick a language that would be very functional, very easy to write for people who knew what they were doing. And there has been some pushback. We don't get as many new developers as we'd like, and so a significant amount of the code base is written in Java, and I think more of it is going to be moving towards Java. But Clojure itself, we don't really have too many complaints. Few small bugs, but I mean, at our scale, we find bugs in Java too. We've gone back to Java and had them fix a number of things for us.
Yes. And that's actually the beauty of open source projects. Like, you know, you find you're doing something, you find a problem in Zookeeper. You can file a bug against Zookeeper, and you know, some other people go fix it.
Or you fix it yourself if you don't
fix it yourself, and you know, contribute your changes back to the project. So while we're on the topic of languages, some people say that why the choice of Java for a lot of these big data platforms? Wouldn't it be faster, more efficient to use something like C or C++?
Yes and no. I mean, so if you look at the micro benchmark numbers for things between Java and C, you're going to get maybe an order of magnitude speed up going from Java to C, which, you know, that's fine, that's great. If you're really trying to push the boundaries of what you do, so you look at things like Impala, which is a SQL engine on top of Hadoop, it's written in C, because they really truly wanted to push the boundaries of what they could do and get every little bit possible. But architecturally, the best you're going to do is a 2x speed up. That if you really want to make a huge difference in things, you need a much higher speed up than that. So one of the big trends recently has been moving from disk-based computing to in-memory computing. And you know, that's much more than one order of magnitude speed up if you can keep all your data in memory. And then you have other games that people really try to play where you want to make sure that the data you're processing is as close to the processor as possible. So you want to do almost micro batches that fit within the cache. And these are games that all SQL databases have been playing for years and years, and people who really know what they're doing with software engineering have been doing that for years. It's a little harder in Java because of the garbage collection and the pointers and things, but it's not impossible.
Yes.
But then again, Java has a C interface too. And so if you really want to,
you can always write native
code. You can always write native code, and Hadoop even has some assembly code. So like talking about the power of open source, Intel really wants everybody to run on their processors. So they have a group of people who go out to help open source projects make sure that they run really well on Intel processors. So in some of the Hadoop code, Intel has been happy to give us Intel optimized instruction sets, well, not instruction sets, but code, assembly code even, to be able to run those things really well.
Yes, and then again, in the land of big data, we are bound by data bandwidths, right, here or there. So
a lot of times it is the bandwidth, whether the data is coming from disk or the data is coming from memory, that can actually be a bandwidth limitation. It's more of where the data is that you can process it. So like talking about Impala. Both Impala and with Hive, they've been putting in features into the core of Hadoop so that you can be positive all of your data is cached in memory. And that's closer to 100x speed up instead of the 2x speed up of Java versus C. And so from a developer productivity perspective, if I don't have to worry as much about seg faults, and I know that the developer doesn't have to worry about cleaning up their code afterward, I mean not the code, but the objects afterwards, the garbage collection will handle that for them.
So let's talk about that stuff a little bit. Yes, Java might be a little bit slower. We are anyway bound by data bandwidths here or there. But what does Java bring to the table?
So Java makes life easier for developers for the most part. I'm not going to say that it's 100% better because Java is very C-like in its syntax, but a few things like garbage collection make life a little bit easier, especially if you're writing a big multi-threaded program. being able to keep track of all the pointers and everything else that you've allocated and not get memory leaks, it's definitely not impossible. You look at all the big operating systems and so much code that's written in C. It's just if that can be freed up from you, then you can do other things. But at the same time, we start getting other issues. So like with HDFS. HDFS keeps all of the metadata about all the files in memory in one single big JVM process. And garbage collection is a constant problem. That if you have 64 gigabytes of heap on your JVM and it decides to do a stop the world garbage collection, where it stops all the threads within that process until it can find space. That just scanning through that much memory can be on the order of a few minutes. And if
For a few minutes, no thread is nothing is running.
For a few minutes, it looks like all of HDFS has stopped and paused. And that's something that we really want to avoid at all costs. And so we put in a lot of time being able to tune the garbage collector to make sure that we're not going to get these huge pauses. Google knows this, not Google, Oracle knows this too. They've been working on their own next-gen garbage collectors like G1 and other things to be able to avoid a lot of these pauses and these other things, be able to support much larger heap sizes. But any tool you pick, there are going to be advantages and disadvantages, and it's important just to understand what those are so that you can deal with them.
Like speaking of advantages and disadvantages, some people, of course, as we just talked about, say Clojure is hard to learn and do. On the other hand, Clojure gives you this nice software transactional memory. So yes, it might be harder to pick it up, but once you pick it up, it's so much easier to write parallel software with it.
Yeah, and I've run tests too that we've had performance bottlenecks, and so I'll take the same piece of code, rewrite it in Java, and in some cases the Clojure code actually runs faster because of the way the locking semantics work. Most of the time, they're essentially neck and neck with each other. So at least from my perspective, Clojure has never really been that much of a performance issue, so long as you know what you're doing. There are certain things where Clojure is trying to be smart and make life easier for the programmer and falls back to doing reflection into Java classes, which is very, very slow. But as long as you know what you're looking for, it's not that bad.
So let me talk about a little bit about the competitors, right? You did mention Spark streaming. At some point, you mentioned this thing called microbatch. Some of the competitors of Storm take the microbatch style. So what is this thing about?
Okay, so in stream processing, the idea is so let me step back a little bit. There's stream processing and then there's low latency processing. And Spark streaming says that there's stream processing, but by the definition of stream processing, I'm not sure I'd group them into that. What they do is very, very low latency batch processing. And so as events come in, they will take a batch, by default about 1 second of data, put that in memory, and then run a very, very fast batch job all in memory to be able to aggregate whatever it is you're looking at, process it, and then commit those results to wherever you're writing the result to. And so unless you're sending one event every second at most, you're not processing event by event, you're processing small batches of events. And so it has very high throughput, but the latency is at minimum however long that batch size is. And in a lot of use cases, in fact, most use cases, that really doesn't matter. A lot of times if you're moving data from one colo to another, one data center to another data center, then you're going to be on the order of a second or two anyways just to move the data there. So adding another second to batch it up really doesn't matter. But in other use cases, then having sub-second processing can be a huge differentiator. So true stream processing is event by event. So as an event comes in, it gets processed, state gets updated, and the result gets written out wherever it is.
It's kind of well known that Storm and a lot of these other streaming systems have scaling issues. And you, in your talk, you also talk about scaling Storm. So what scale can Storm run now? And then how can we see, because you're also a Apache committer, right? You're also part of the Apache open source, core of people working on Storm. So where do we see the scaling go? Like, where is Hadoop now? Where's Storm now? When do you see things progressing?
So right now, Storm tops out at a little over 1,000 nodes. If you tune things correctly, there are certain limitations in some places where we store state, and I'll talk about that or in the other slides. But we really do have plans to be able to scale much, much higher, and I'll talk about details of some of the things that we're doing to be able to deal with that. I was talking with some guys from CERN, who are the Large Hadron Collider. Mm-hmm. They have this problem where they will generate 4 terabytes of data a second from the collider.
4 terabytes of data
per second.
A whole hard drive full of data every second.
Yeah, and they don't have enough spindles to be able to write all that data out. So you look at a typical hard drive, a spinning hard drive, about 80 megabytes a second is what it can handle, best case. So that's on the order of 60,000 hard drives to handle 4 terabytes a second.
Okay.
That's
big data.
That's very big data. They don't want to store all of that. So they've developed all kinds of very special, fancy algorithms to be able to filter out what does make sense and what doesn't make sense so that they only write the pieces that matter. And we were talking with them about whether they'd be, well, they were interested in whether Storm could handle some of this and some of the newer things that they want to be able to do, especially with GPUs and other things to speed that up. And so that is one of my goals, is to be able to get to the point that Storm truly can handle 4 terabytes a second. That this is going to be several thousand nodes. You just look at the networking involved, even with InfiniBand. It's going to be a significant number of nodes to be able to process all this data. Yeah. The CPU involved, all of that. It all has to be in memory. You're never going to be able to touch a disk until the very end. And so it's a very interesting problem. Okay. Internal to Yahoo, we have a goal to be able to have a 4,000 node cluster. And so put it very much on the same scale of what Hadoop can support. Mm-hmm. Mm-hmm.
So one other question I have. You are a Apache Storm PMC member, mm-hmm. right? So tell us about the open source process of development of Storm. Say somebody, one of our students, wants to start contributing. What is the process? How does it work?
Okay, so open source in general is kind of a free-for-all in that there are lots of different groups, lots of different projects. You can go to GitHub and who knows what's there. Then you might not even have a license associated with it. So a lot of the big data projects have found a home in Apache. Mm-hmm. When people hear Apache, they think of the web server, and it's still there, but it is an entire software foundation devoted to open source, and all of their projects are under an Apache open source license. One of the Apache concepts is is community over code. That having a strong, vibrant community for a project is much more important than having the best code possible, because a vibrant community will be able to fix the issues that are in the code. And so that's kind of the Apache way. That's the idea behind Apache, is to be able to do that. And so Apache provides a number of different things. So if you go to apache.org, they'll have a big list of all the projects. One of them is Storm, so there's storm.apache.org, or hadoop.apache.org, or flink.apache.org, or spark.apache.org. All of them have found a home there. And so you'll go to there, they'll have a list of some of the mailing lists that you can sign up for, that you can ask questions on. There usually is a Jira, which is a bug tracking tool, or there's Bugzilla or other things that are associated with the project, and you can go look at that. Most of them are also reflected on GitHub. So if you go to github.com/Apache, should list the vast majority of the projects in their repository with a nice README in there to be able to explain a little bit about how to contribute. For Storm in particular, you'll sign up for the mailing lists, and you can ask people questions about whether there are projects or things that you want to be able to help out with. One of the other things you can do is just go directly to the bug tracking tool in Jira and go looking through for something that's there. But one of the things I really find to be most critical is that you start using the tool. That whatever it is that you want to contribute to, you want to start using. And then you find something that bugs you, something that doesn't work quite right. It could just be the first thing might just be they misspelled something in the documentation, or this documentation missed a quote, or it doesn't do exactly what I expected. And so you can contribute back some of the documentation. And then you start looking at it and you say, oh, I wish the Storm could do this. I got an exception. I want to be able to get that exception back programmatically, not from the command line through a shell script type thing, rather than having to go through Thrift or looking at the UI. There's somebody that we worked with that decided, those guys, the people working on Storm just weren't listening to me enough. They didn't put it in, so they spent all of 15 minutes, wrote this small function, and contributed that back, and now Storm can do that as well. And so it's kind of those things that you find a pain point, something that you want to be able to do, and you start working with that. And then, like any other project, you're going to have to work your way up. It's complex, and it will take a while to be able to understand what's going on. But as you contribute more, and as you answer more questions of people who have questions, and you ask questions to learn more, slowly you get more of a reputation in the community. Apache is supposed to be a meritocracy. I'm not sure how well that works in practice for everything, but it works fairly well for open source, at least, in these big distributed groups. And so as you contribute more, and as other members of the community get more confidence in you, eventually you can become a committer, which is somebody who actually has commit rights to the repository. So when somebody says, hey, I have this lovely new feature, or I have this bug fix, committers can take a look at it, understand that yes, this is good, or give feedback, and then check it in. Now, other people in the community are encouraged to take a look at those patches, give feedback also, but it's that last step of checking it into the repository that is what the committers can do. And for most projects, a while after that, then you can become a project management committee member. And that's mostly there for voting on things like how the project should be run and who other committers should be. So PMC members, project management committee members, there's kind of this aura or whatever about it, but it really is just they vote on whether these other people seem to be at the level technically that they need to be committers. And it doesn't have to be just code contributions. One of the things that we really like to encourage is other people who are just from the community. We have one member, Michael Knowles, in Storm, who is an amazing person. He's done all kinds of blog posts about Storm and how to get Storm up and running. He has done a couple code contributions, but not a whole lot. But it's mostly the documentation and the whole community aspect of what he's done that we decided that he would be a perfect person to be a part of the PMC for Storm and to really help the project along.
And then contributing to open source projects helps our students' job prospects later.
Yes. You put Hadoop on your LinkedIn profile, and it's hard not to get people asking you for, to come work for them.
Yes. Well, thank you very much, Bobby. Sure. Thanks for coming here and spending this time of your day to talk to our students, and we definitely appreciate it.
Thank you.
Thank you very much. Hello everyone. In this video, I'll talk about Spark streaming. It's a very interesting system, very interesting idea, and has been gaining a lot of attention and popularity in the open source community and also in the big data enterprise computation industry. So without further ado, let's jump into this. The whole idea behind why you would want to do Spark streaming is stateful stream processing. Now, what do I mean by this? right? Traditional streaming systems, we've talked about them a lot. We talked about Storm system. The whole idea of Storm is that it wants to guarantee very short latencies, right? It gets an event, a little tuple of information. It could be small, it could be big, it could be as small as 10 bytes of data. An input event comes in. The traditional event streaming system tries to process this information as soon as it gets there. If it needs to go through 5 machines, boom, boom, it sends them through different machines to process them right there, right then. There are implications of this design. First of all is the state. Each node along this graph of computation can have its own mutable state. And as this event goes through one node to another, it can modify the state of each processing node. The modified state can be updated and sent to new records to databases or whatnot. Now the one big issue here is that what happens if there is a failure in your system? If a node goes down, all the state along with it kind of goes down. Now, this idea resulted into the Lambda architecture design, as I talked in a previous video, where you say, okay, achieving fault tolerance in streaming system is hard, therefore I have a backup sort of a data processing pipeline in a batch mode, and then once in every 24 hours or whatever number of hours that you decide, I'll synchronize up the data, and the batch processing system becomes my source of truth. Making streaming stateful stream processing is really hard. Now, another method that a lot of people have been using is make the processing nodes in a Storm architecture, for example, in a Storm topology, make them stateless and keep the state somewhere else. For example, have a cluster of Cassandra nodes or Redis nodes that they keep the state and they try to provide fault tolerance for keeping the state, and then all the nodes in the Storm processing graph are stateless, idempotent, and we achieve state that way. Now, another thing that we need to figure out is that how existing streaming systems try to cope with node failures, because not only you have to think about the state, that, for example, you can say, okay, I'll make my nodes stateless and keep the state somewhere else in Cassandra or Redis. But there's also another thing, is that what do you do to the tuples that are in flight, to the events, the little bit of data, events that are coming into your streaming system? What do you do to them, the ones that have entered the pipeline? And when there is a system failure, what happens to those? Storm provides you, as we talked about in previous videos, with some acknowledgement, tuple hacking tree sort of mechanism, where it replaces an event, replaces a tuple if it's not processed by a certain timeout, right? And it has this tuple tree mechanism that puts creates a tree of events, and as they go through the system, it receives acknowledgements. Acknowledgement means that, okay, yeah, the node in the tree can be cleared. This mechanism provides at least once guarantees. So if there is a failure somewhere along the along the graph, we replay this. Each tuple is guaranteed at least once processing. But on the flip side of the coin is that since your event can actually go twice or 3 times through the pipeline, the states could be updated multiple times. And that's not necessarily something that you can handle. Sometimes the application is fine. Sometimes it's not. Again, necessitates the whole idea of Lambda architecture, is that my pipeline, my streaming pipeline, isn't necessarily very fault tolerant, and it's state could go out of whack, and after every 24 hours, I need to synchronize it. So again, this idea implementing is hard. So to answer an answer that Storm provided to this is a system called Trident. It used transactions to update state, right? So it tries to achieve this guarantees in updating the state by transaction. And if the transaction fails, kind of like databases, it tries to nullify everything and then do the transaction again. To be able to do this, it needs access to an external database all the time. And as a result, it becomes slow. So now, a different system, a different idea is to do this in a micro batch. And Spark has a very good implementation of this called Spark Streaming. So as we talked about in other videos, Spark was a project out of the Berkeley University around 2010, 2011 started, has become very popular. I think at the moment it's the most contributed big data open source project in its domain. And the whole idea is that you have RDDs, resilient distributed data sets, that keep a lineage of how each partition of the data is created, and it will try to recreate data, run the computations again if there's a failure. So the idea behind Spark Streaming is that you want to window a little bit of data. You have a stream of data incoming, right? So you want to take a kind of a sliding window, grab a little bit of data in a window, run that little window of data as a batch, as if it was a batch, and then repeat the process over and over and over again. The main idea here is called discretized stream processing. Spark streaming system calls these D-stream, as in discretized streams, right? So instead of having a live data stream coming in, we chop them up into smaller batches of, X seconds, and then Spark treats each batch of data as each little batch of data as an RDD and processes them using the RDD operations that we've talked about in previous videos. And then finally, the process results of RDD operations are then returned in batches after batches after batches. So you can feed them into another streaming system, or you can send them to HDFS or whatever you want to use them. Again, the results are one batch of results, then another batch of results, then another batch of results. Batch sizes are very important in Spark streaming. The choice of batch size has a huge impact on what sort of performance you can get out of the system, what sort of latency and whatnot. Practical latencies for Spark streaming are in the range of 1 second and up. The best it can really do is about 300, 400 milliseconds. Any lower than that, and the overhead of each batch just completely overwhelms the system. Here's a rule of thumb for you. If you're designing a system that requires very fast responses, low latency to your events, Spark streaming is not the solution for you, right? If you want an event to come in and be processed within 10 milliseconds, 1 millisecond, maybe sometimes you need even faster. Maybe sometimes you need you're fine with a little bit larger, but not as much as a second. Spark streaming is not the system for you. However, if your system that you're designing, if the application that you're designing to build can handle 1 second of latency, even better if it can handle 10 seconds of latency. So there is a new batch of results every 10 seconds. Then Spark streaming could be a very effective tool in your arsenal. The reason I say this is that, okay, Spark streaming has nice things about it, and I'll talk about this in upcoming slides, but it also allows you access to the rest of the nice batch processing features of Spark that we've talked in previous videos. Then you can, each of these streams, these discretized streams, is an RDD by itself. So you can do whatever you could do in regular Spark with them. kind of looks like pretty much like a regular Spark program. This piece of code is of course written in the Python language. What you need to do when you want to have a streaming program is first of all grab a streaming context, which you can get by calling the streaming context and passing in the Spark context object. And then once you have that, it's actually makes it quite simple, right? So in this case, for example, lines is a D stream, not quite an RDD, it's a D stream, discretized stream. That in this case, I'm saying that, okay, you can get the input data from this IP, in this case, localhost, and this port number. And then from this point on, I can basically deal with it like a regular RDD. For example, in this case, look at this. Pairs is a transformation on the words discretized stream by applying a map function and giving it a regular lambda function where it gets a word and then emits another tuple, word and one. I don't want to get too much into detail of this from now on. You had examples of how RDDs can be processed in Spark in previous videos, and I would refer you to those. But just the whole idea here is that a D stream can pretty much be worked on like a regular RDD. So now the question is, if you want to design a system using Spark streaming, how do you get data into the system? Spark streaming comes with a couple different already built-in sources of data that can connect to different sources and extract data from them. A very useful one would be Kafka, and in another video we'll talk about how Kafka is used as a PubSub model, basically a queue between different stages of a streaming pipeline. There's already a Kafka input source for Spark. There are other ones as well. HDFS, Flume, reading from Akka is possible. And it's pretty easy to write a receiver for other data sources. So it's not that hard to do that. Now, one interesting aspect of Spark streaming that I kind of mentioned in the beginning, but now let's talk about it in more detail, is stateful computations, right? So we talked about how hard it is to do, to manage state in a streaming system, because if there's a failure, if you manage the state inside the processing nodes in Storm or something like that, then the whole state can go down. If you want to connect to an external system like Redis, Cassandra, database, like for example Trident does, you have the overhead that you have to you have to pay for the overhead. Now, what Spark streaming provides you, and this is a side effect of its micro batch nature, is that it allows you to keep state inside the processing nodes. And if there is a problem with the processing node, if the processing node goes down, it can automatically bring up the state again. So the way that it does this is by giving you a function, update state by key. This way you can maintain arbitrary state while continuously updating it. And if there's a failure, the system will automatically get it back for you. Now, how to use this is that you define a state. So the state can be any arbitrary data type. It can be, a map of maps of queues of whatever. So it's basically any data type that you want can be your state. And then you also need to define a state update function, which this state update function specifies the function how to update the state using the previous state and the new values for an input stream. Now, what happens is that Spark streaming, every time it is processing one little batch of the D stream, like 1 second worth of data, it calls the state update function and applies it to the data type that you define as the state in every batch for all existing keys. Now, if there is an issue with the system, so you can imagine, okay, each of my processing nodes in the cluster are keeping the state by having this. Now, if there is an issue and something goes down, the state is now part of an RDD, right? So the system automatically keeps the lineage of it and frequently makes a checkpoint of it. So if there's a failure, it can load the checkpoint and then rerun everything that was run after that checkpoint up to the last point that it broke down. So this way, you can keep arbitrary state and try to get closer to that holy grail of Kappa architecture, knowing that this only works when you are not that much in need of fast processing, in need of low latency. Spark streaming gives you a huge bandwidth. It can actually process huge amount of data in a given time, more than Storm. But if you're limited by the latency, then of course you're limited to not using Spark streaming. So one last thing that I want to sum up this discussion on Spark streaming is that aside from the niceties of update state by key, keeping the state and everything, is that it allows you to get in touch with a rich ecosystem of other big data tools that are now part of the Spark system. You have access to Spark SQL, where you can just use SQL statements to query data. You can access Spark ML, machine learning library and machine learning, to do ML, machine learning, on your little bit of streaming data that are batched in, micro-batched in, say, 1 second worth of data. You can access to graphics, Spark R, the R language for statistical computation and whatnot. Again, the disadvantage is that it's not really streaming in the strict sense. So it really batches data and then runs that batch of data very quickly. Hello, everyone. In this video, let's talk about two terms that you might hear in the context of streaming applications. The two terms that have gathered a lot of interest in the past couple years started with Lambda architecture, and then within the past year or so, you might hear the term Kappa architecture. Now, what do I mean by Lambda architecture? Lambda architecture is when you want to do, of course, real-time processing of events that come into your data pipeline. The way they architect this system is by having two parallel data processing paths. The first processing path would use a stream event processing system, kind of like Storm that we've talked about before. Other engines are out there. You can talk about, Samza, Flink, whatever. Then on the parallel path, you have the batch processing system. In this case, for example, we have Hadoop. Now, why do we want Lambda architecture? The reason that people do Lambda architecture is because things in a computer system fail all the time. As we discussed this in previous modules when we were discussing about MapReduce and Hadoop and Yarn and these things, batch processing can handle failures just fine. Now, of course, this is an oversimplification. There are many different failure models, but batch processing is designed around this whole idea. I have a batch of data to process. If my machines fail, something in the distributed system goes wrong, there is a missing heartbeat at some point, I figure out, I restart the computation, things will work out fine. The issue with streaming systems is that the nature of events that come into the system. An event comes in, it's supposed to be processed. What happens if there's a failure? The event is gone, right? So you have to do something about it. Lambda architecture is one attempt at fixing this issue. They say, okay, achieving fault tolerance reliability in my streaming system is hard. I'll let things happen. I have my batch processing pipeline in the back as a backup. Every 24 hours, once a day, I synchronize the data, the models, the state between the batch processing system and the streaming system. So that's one architecture that has been that has had a lot of interest starting about 3, maybe 4 years ago, and it gained a lot of popularity. A lot of enterprises have their systems architected as Lambda architecture pipelines. You have your batch processing and streaming processing, and every once a day they synchronize to each other. Now, a more recent term that you might have heard is Kappa architecture. Now, the whole idea of Kappa architecture is let's try to fix the streaming pipeline to a point that it can handle failures. In Kappa architecture, they try to get away from the two parallel paths, batch and streaming, and they just do the streaming, but they try to do streaming good enough so that if there are failures, the state doesn't get messed up, right? So in the next video, I will talk about Spark streaming. Spark streaming tries to provide some features that gets you closer to that holy grail of Kappa architecture, which is one data processing pipeline that is handling real-time events and tries to do a good job with the state. It's not completely there yet, as we will see in Spark streaming. It has its issues, and I'll leave that to that video. Hello everyone. In this video, I will talk about a streaming ecosystem. Throughout the course so far, we have introduced some different tools to you. Some of the stuff that I'll talk in this video should be quite familiar to you. Some of them not as much. Some of you might be confused on at what point should you use which of these tools. Should I use Storm? Should I use Spark streaming? Should I use Kafka? Oh, what about OLAP stuff, OLAP style querying of my data? Are the tools that we've introduced enough to gather data from a large geographical interface? There's a good bit of confusion over this, and to be honest, a lot of these tools that we have introduced throughout the course have overlaps as well. Some of the functionality that are present in Spark streaming overlaps with Storm. I talked about Redis in a previous video. It has publish-subscribe model. Kafka provides publish-subscribe model. So there's quite a bit of confusion on when to use what tool. Each of these tools have their strengths and weaknesses, and it's best to pick and choose and use the right tool at the right time in the data processing pipeline, and not try to beat a framework to do something that is not quite optimized to do for it. Let me introduce you the idea of a streaming pipeline ecosystem. What you want to do in a typical streaming application is you want to gather the data from a large geographical set of users. They could be all over the planet. They could be spread across the country. So you want to be able to gather the data. So you really want a good distributed funnel sort of mechanism. Once you do that, once you gather, you want to put the data, funnel it into your set of servers that you have. For example, you have 10, 20, 100, 1,000 servers. So you gather the data, and then you kind of put them in some sort of a queue that takes care of all the nastiness of network communication. There is the momentarily bandwidth ups and downs and latency differences and whatnot. So you want to have queues between different steps of your streaming system that cancel out all the noise. Once you have data in a distributed queue, you want to do some real-time processing on it, or you want to do some semi-real-time processing. And then once that is done, you want to do some OLAP, OLAP style querying, and I'll get to that in a few minutes. So step one, gathering the data. I personally think these days Apache NiFi is a kind of a good distributed funnel. It was made in NSA, they were working on it for 8 years or so, and then they open sourced it back in 2014, picked up by a whole bunch of people. Well, it was very interesting. So it became an Apache project. Hortonworks is actively working on it among a whole bunch of other people. It has a great visual UI to design the data flow. Many processor types comes with it. I'll show you in a second how it looks like and what are the components and whatnot. The main decision point between if I want to use NiFi to process my data stream or something like Storm or Spark streaming is that, as you will see, in NiFi you design a graph that processes your data, but that graph itself is not distributed. The whole graph is copy-pasted across as many nodes as you give to NiFi. You can't do like heavyweight processing, the sort of processing that is spread across multiple nodes, like 10 nodes do database lookup, and then another 25 nodes do processing, and then you don't do that sort of stuff. Each event, each streaming tuple that comes to the system has to be completely processed in one single machine. Now that event can go to different nodes, but that one node has to complete the process. So NiFi has sort of a different vocabulary. You have flow file, which is really the unit of data moving through the system. I kind of interchangeably use the word tuple or event. It's basically just key value pairs. You have processors that you kind of connect with each other to process your incoming data in different steps. And then, of course, you have the idea of connections, which are links between processors and process groups. So let's take a quick look at what I actually really mean. So here I'm showing you a screenshot of NiFi graphical interface. So as you can see, I have two processors here. Processor 1 on the left-hand side is called getFile. Basically, what it does is just gets a file from another incoming data stream. And then the next processor that I have is called route on attribute. So it basically extracts some attribute from its input data, and then based on that, it sends the incoming data to different routes. And then I have a connection between these two that graphically shows data has to reach the get file processor first and then go to the route on attribute processor next. Designing these is kind of quite drag and drop. It's very easy to design one of these. You basically just click on the processor icon on the upper left of the graphical interface right next to the word NiFi. There is the icon of a process. You just drag that on your screen, and then a menu pops up, and you just say, OK, I want what sort of a processor type I want. And then once you design your graph on the graphical interface, you just click the green triangle button on the graphical interface, and it starts running. It's very easy. It's great for coming up with a proof of concept sort of style, gathering stuff. If you don't have too much of a heavyweight processing, it's mostly about gathering data or transferring files from somewhere to somewhere else. That's kind of like strength points of NiFi. Once you have that, you want to put stuff in a distributed queue. Something with publish-subscribe model. You want something that has producers coming in and putting stuff in queues and consumers getting stuff off queues. Of course, we talked about Kafka in a previous video. So Kafka is a very popular example, and it would be perfect for this sort of use case. As we talked in previous videos, in Kafka, you have producers, consumers, and then a whole bunch of brokers which synchronize with each other using Zookeeper. Kafka can provide high throughput cluster of couple Kafka nodes. 3, 4, 5 Kafka nodes can handle huge amounts of incoming traffic, and putting them, storing them in disks, and then so to make sure that it kind of buffers the ups and downs in the networks and noise and whatnot. It was originally developed by LinkedIn, but now it's an Apache open source project. There are a whole bunch of tools that you can interact with Kafka. There are a whole bunch of command line tools: Kafka console, producer, consumer, topics, and then there's some recent efforts to provide graphical interfaces for Kafka. There's a Kafka manager now. We talked about NiFi, and we said it's not really great for heavyweight processing of your streams. So what would be good here to do? So we need some sort of a platform that allows us to do heavyweight stuff. Filtering, joining from database, doing windowing logic so that I keep events from the last half an hour, and then based on those events and then joining with some things in a database, I do some sort of a business logic. I think two platforms are really good here, and it really depends on what sort of a real-time requirements you have. If you have a sub-millisecond to tens of milliseconds, Storm is good, and we've talked extensively about Storm in this course. It's now an Apache project. It was originally built in a startup called Backtype and was sold to Twitter, but now it's an Apache project. It's written in Clojure itself, but you interact with it in Java. Typically, you write your bolts and whatnot in Java. As we talked about before, a Storm cluster has a master node Nimbus and a whole bunch of supervisor nodes. So each node has a supervisor. The supervisors launch worker threads that really do the processing jobs. And this whole scheme uses Zookeeper to coordinate with each other. You write your Storm program as a topology, so as a graph really, that has spouts and bolts. Spouts is where data comes from. Bolts are where different processing is done on events. So the difference again here between this sort of a graph and a NiFi graph is that the NiFi graph is copy-pasted completely across all the nodes, while in Storm, a graph can be distributed across the cluster. So, 2 bolts can end up in just a couple machines, and then 3 other bolts can end up in like a whole different set of machines. So it's much more scalable. It's very fast from a latency point of view, so I'll show you a slide about that. As you've seen before, to write your program in Storm, you use the topology builder API. So as you see, you can have set spout, set bolt, and then you kind of connect them together. If you don't have sub-millisecond or 10, 20, 100 millisecond requirements for event processing, event handling, maybe what you want to look at is micro batch processing provided by Spark streaming. By doing batching of data, you can basically reduce overheads, right? Because now instead of receiving an event and just quickly putting it in a network packet and sending it to the next machine for processing of next bolt, you put a whole bunch together and then send over the networks, and that can reduce per event overhead. Since Spark does this whole idea of keeping the lineage of an RDD resiliency, it gets you closer to Kappa architecture, so you don't have to have Lambda, 2 different paths of processing. You only have 1 path of stream processing, and that is like your path. Depending on what sort of latency response you require, Spark streaming might be what you need. As we talked about before in our Spark lectures, it was a project coming out of Berkeley University in 2010. It's an Apache project now. It's become very popular. I think it's the most contributed open source project in the big data set of projects on GitHub. And the whole idea is based on resilience data sets. We talked about how Spark streaming works before in its own lecture, but just to recap, you window a bit of data, make it a micro batch. Maybe every second you create a new batch. It's an RDD. It goes through the Spark cluster and is processed hopefully faster than 1 second. Advantage of using Spark streaming, aside from getting you closer to Kappa architecture, It has it allows you to access a large ecosystem of big data tools. You have access to Spark SQL, Spark itself, RDD's programming is easy, Spark machine learning, GraphX, other things. The disadvantage again is that it's not really streaming, it's micro batch, so the latency is not that small. So if you want anything faster than 1 second processing, Spark streaming is really not the solution. Storm in that case, or some other streaming systems that I have not talked about in this course, but there are other alternatives. There is Apex, there is Samza, there is Flink. Those are good. So let me show you sort of a benchmark that we kind of wrote at some point to see how really these things differ. To do this, I basically want to simulate what a real business logic pipeline would do. So you have your data in Kafka, and then you want to have some sort of a streaming platform to do processing. Now, in this case, let's have you have an event that is type JSON, so it needs to be parsed in a JSON parser first, and then you need to do some filtering on it, select a few events out of all the stream of coming data, and then we want to do a projection transform on it so that we basically select a couple fields from this JSON data. And then kind of like a Lambda architecture, we assume that the state is not stored in the streaming platform itself. It's say stored in an outside database, in this case Redis, which we had a video about it. In this case, I want to go quickly to Redis, do a join with some key value pairs in Redis and come back, and then do a time window aggregation, and then finally I want to write the results back into, say, Redis and update some state in Redis. This slide, I want to show you the different nature of Spark streaming versus Storm. And I'm also showing Flink, which we didn't talk about Flink in our course. Flink kind of behaves rather similar to Storm. As you see, the red graph on my chart is basically the latency of Storm. The green one is for Flink. So as you see in this application, I wanted to make sure that every incoming tuple is processed in 1 second window. 99% of the tuples are handled in both Storm and Flink within the 1 second window that I'm looking for. Spark streaming has kind of a more stepwise response, which comes directly from its micro-batch nature. The other thing that is kind of evident in this graph is Spark streaming has much more latency compared to Storm. So in this case, for example, I had 150,000 events per second coming into a cluster of 20 nodes, and we wanted to process them. Both Flink and Storm managed to handle everything within 1 second latency. Spark streaming, while it has the potential to do more amount of work in the same time window, if you want to have a certain response time, it doesn't work very well, and you can see it takes up process 99% of all tuples coming in 1 second. Tells you the different nature of these things. Spark streaming, I'm not bashing on Spark streaming. Spark streaming is great for when it is suitable, but it's very important for you to figure out for your application what are your requirements. So side note, we talked about the importance of key value stores in Lambda architectures. We had a video and a demo on Redis, and we introduced Cassandra as well. In the previous benchmark, I showed you how Redis can be used as a data store for the business logic pipeline, the streaming pipeline. Finally, I want to move to OLAP query, online analytical processing. So the idea of online analytical processing is it wants to provide business intelligence when you have multi-dimensional data sets and you want to do data analytics on this stuff, and you want it to be fast. Hence the word online in OLAP, online analytical processing. So it basically wants to provide, we need a system that provides couple different basic operations on my data. Consolidation, which is really aggregation in dimensions. So by dimension, I mean, for example, column. So you can think of your data set and say a certain column, is talking about age of users, for example. I want to be able to quickly do aggregation style queries based on a column and say, give me the number of records in my data set that have users age larger than 30, for example. So we are looking for a system that can very quickly do this sort of online queries. We want to be able to do drill down, which is a fancy word for filtering, and we want to be able to do slice and dice, which is really looking at data from different viewpoints. The system that I think is very interesting for this sort of online queries is Druid. It was developed in MetaMarkets back in 2011. It's open source. The whole idea behind developing it back then was that for a business logic pipeline, streaming pipeline, real-time RDBMSs, relational databases, kind of like MySQL and everything, are not fast enough. They're too slow for doing online analytical, OLAP style queries. And they tried NoSQL key value stores like Redis. So that the idea is you pre-compute all sorts of queries that you want and then store the results in something like Redis. The issue is that pre-computation is very slow, and as you increase the number of queries that the user might want to do, the amount of pre-computation grows exponentially. So Druid is a system that tries to provide some neat tricks to process this sort of queries faster, and we'll see how it does that. So it's open source with Apache license. It's column-oriented, sub-second query time. The whole idea of Druid is using real-time streaming ingestion. So the data types that Druid likes to look at should have timestamps. If your data type, input data type that comes into Druid doesn't have timestamps, Druid doesn't even want to look at it. Timestamp events come in, and Druid kind of makes indices as data comes along and makes query access to this information much faster. So kind of like similar to a lot of other streaming systems that we've seen, there is a whole bunch of, this is a distributed system, so there's a whole bunch of different types of nodes that work with each other. In Druid, there is historical nodes that use data types that are optimized for reading. And then there's real-time nodes that are using data types that are optimized for writing stuff and appending as data is coming in. As a window of data comes in and the real-time nodes process them, once the window is full, they hand off that amount of data to one of the historical nodes, and then they're ready to process more real-time nodes. Druid uses bitmap indices, and basically, it's using an idea called dictionary encoding. And after the dictionary encoding, it uses bitmap indexing. So in this example, you'll see my column page. I have two different item types. Dictionary encoding says, OK, I can take the name of take all of the values in that column, assign numbers to them, and then bitmap indexing takes this and does a reverse operation on it and says, OK, I need to create a bitmap for each dictionary entry. A bitmap is just, a very compressed data representation for that column. And then once the user comes in and wants to do online queries very fast, all we are really doing at that point is logical and/or of a few thousand numbers for a query. So it actually results in lightning fast queries. And finally, so Druid is very good to provide that sort of functionality. The last step in a streaming ecosystem is I want to be able to visualize my data and get business intelligence. They usually use BI for business intelligence. There are different graphical interfaces. Druid comes with, there's a system that's designed for Druid. It's called open source. It's called Pivot. It's nice. It allows you to interact with the data. There are other tools that are quite common in industry. For example, Tableau is actively used in the industry. Druid doesn't directly connect to Tableau or some other visualization tools. Druid can work with Spark, so you can use Spark to look into Druid and extract data from Druid's index engine, which allows us to connect Druid through Spark to something like Tableau. I hope this video kind of showed you what strengths and weaknesses each of these tools have in comparison with each other, and how we can combine them so that we can get a nice system that works all in all.
So this next set of videos are talking about graph processing in cloud computing. And this is a big new area of big data and use of large cloud clusters. There's a huge amount of data to be processed. There's a huge set of different problems that would benefit mankind if we could solve them. And so graph processing has become very popular, and it has lots of businesses and lots of commercial implications, but also lots of social and scientific implications. And we're going to be just looking at how cloud computing at the moment is supporting that sort of graph processing. So we should define what we mean by graph processing. Lots of different ways to describe it, but essentially you're looking at some storage system and processing system. You're going to have a graph database with all the information in. It's going to provide some way of retrieving that data. And typically, a graph database is going to provide index-free adjacency. It's going to have adjacency elements and use pointers for them in some form or other. The nodes are going to represent entities, people, businesses, accounts. The properties are going to be pertinent information that relates to the nodes. And edges interconnect the nodes to nodes, or nodes to the properties, and they represent the relationships between the two. And there's all sorts of different formulations. The difficulty with it is that the databases that represent graphs tend to be very, very large and very sparse. And they're kind of difficult to process in a straightforward vectorized way, so new schemes need to be developed for them. We can talk about the relationship. Clearly, if you have a graph, you can represent it as an adjacency list. You can think of, oh, well, is that just a relational database table? And we can talk about the differences between them, and scaling is certainly one of the big issues. So a graph database has a bunch of associative data sets. So you look up one item and you retrieve a different item from it, like a node and its connection to an edge. And we look at the sort of systems that it applies to. For example, most of your object-oriented applications are consisting of objects that talk to each other. And so you have objects and you have interconnects, and they're represented by edges, and they have properties on those edges, and you can talk about, well, what is the structure of an object-oriented application? I represent it as a graph. Typically, when you're looking at that type of thing, it's, as I said, sparse data. You don't often employ join operators to take the intersection of two graphs to see what the result is. You're more exploring a particular graph and looking at particular patterns within the graph. Relational databases, on the other hand, you perform the same operation on large numbers of data elements. You often do the same types of computation on them. You can provide relations over the data that's being performed, and so they fit very nicely into sort of table operations. The entity type typically is represented by a table, and there are rows which are instances of the entity, there are columns representing values attributed to that instance, and then rows in one table can be related to rows in another table if you have some sort of unique key expressing the relationship of that table to another table. So in that case, it is all very, very vectorized, very sort of straightforward, and not huge databases. A graph database, for example, comparison, you might want to take the whole universe and stick it into a nearest neighbor description and allow people to explore the universe, in which case you would represent, a star, another star, and the distance between them as an edge, and you would have millions, billions of nodes and edges and so on, and allowing people to explore that would be very exciting, but it would also require a lot of interesting computation. So looking at a graph, the ways to represent a graph, typically it's an adjacency matrix. You have all the nodes, you have how they're related, the edges that relate them to other vertices. So in this graph, A is joined by an edge to BGH. Now you could just list AB, AG, AH, or you could make A and a list of BGH, or, well, you could have just a tuple of a vertex, edge, and another vertex, and then have A's connected to B, A's connected to G, A's connected to H. A lot of different ways to represent an adjacency matrix, but that's what a graph is. On the other hand, a relational database, typically table represents some entity, some relationship, and you have tuples and rows, tuples are rows and attributes are columns, and you can look at the system or look at the contents of the table in those two ways. Typically, the rows represent instances, and the attributes describe what those instances are, or might describe the keys, and so that's what a table is, nice and regular, and can be dealt with a sort of simple vectorization. So, looking at graph computation, a lot of people say, well, when you address this, when you're writing algorithms for graph computation, what you need to do is to think like a vertex. What is the vertex? What can the vertex do? How can it perform its operations? And the reason is because a vertex is a sort of locality. It's interconnected by edges, so it's your sort of focus of computation. There's two basic operations you can do on a vertex. One is you can aggregate information from neighbors, and that gives you a whole way of doing computation about your local neighborhood. The other is you can diffuse your local information to the neighbors. So diffusion is the second approach, and this is just a sort of diagrammatic representation. So you can take each node in turn and you can say, well, okay, it could diffuse data from its local vertex to other vertices, or it could fuse all the data from the local surrounding nodes into some properties that the local node has. And most of the graph algorithms are built up this way, and you view these networks of graphs as very, very large, that these localities can stretch over variable distances of numbers of computations, you might say, but they are sort of, well, the interconnections can reach across the graph, or they can just be very, very short. And how you lay out the graph obviously determines that, but there's some fair degree of flexibility in how that's all organized, which leads to processing and data representation problems. So an example of a graph problem, a nice simple one, is let's suppose you have a very, very large graph, and What you would like to do is just sort of return all sets of vertices with edges. So you'd like to go A, B, A, C, and then find an edge from C to B. And if you can find that, then that's something you're looking for, return the result. So that would require you a lot of computation. It's not sort of a straightforward, simple type of table-to-table operation, and you want specific types of graph algorithms and operations in order to be able to solve it in an efficient manner. Well, we can sort of move on to actual practical sort of processing of graphs, and a lot of that's occurred in social networking these days. First sort of example that everyone gives about graph processing is PageRank. That's about web-based computing and how people view the web. And what it does is to count how many nodes have incoming arcs, how big the number of arcs are, so that you find out the most popular nodes, vertices in that graph, and rank order them. And that algorithm is one of the ones that Google has made its name for. What it does is to allow users to do searches on all the data in the web, the whole web. It reduces the data in the whole web to sets of terms and indices, and then for the particular search, you try and get the best matches for the search terms in terms of what's on the web. But the problem is if you just provide a list, it doesn't help. So you try and rank what is provided to the customer, and PageRank allows you to do that. So the PageRank algorithm, counting the incoming nodes to a website, allows you to sort of rank which is the most important concepts in the web that relates to your search terms, order those terms and present them in a satisfactory manner to the user. Well, there's all sorts of other applications. Typical traditional one is to look at transportation routes, because those gets more and more dense as time goes on in the world. But what you're looking for very often is the shortest path, how to get from A to B using the shortest number of either links or distances. If they have distance attached to them, they could have times attached to them. So you're looking for the shortest path, and of course Dijkstra's algorithm is a good sort of example of an approach to deal with that. And again, it's not very amenable to sort of computing with a table, but it is very good with its own type of algorithm, its own processing. Another one would be citation relationships. Nowadays, all the faculty, when they publish papers, get cited, and those citations go into indices, and we have databases with citations in them now, trying to connect all of those groups together. So you could say, well, over here, here's the cloud group, and over here, here's the, let's say the grid group, and how do they interconnect? Do they interconnect? Where's the interconnection? Where's the people that interconnect the two groups? So you can have very, very complicated sort of type of graph algorithms working on how people interact on a networking basis, and this leads you to, if you like, the real sort of plum at the moment, social networking, trying to understand how social networks work, trying to understand how to categorize, classify, organize your social networks. That's really sort of what some of these, like Twitter and Facebook, are trying to do. They're using clustering techniques. They're using lots of other techniques to do this. They would like to find, everybody who needs a television, everybody who wants to buy a car, or they'd like to find what social group this person is in, or whether he's a leader in that social group, or whether she's the real conduit for information amongst all her friends. So all of this type of computation requires a great deal of processing, and it's all sort of graph-based, very sparse connections, and very sort of interesting futures. So this type of processing doesn't easily map into what we've been discussing so far. We've looked at MapReduce. MapReduce tends to work well if you know there's a large number of points that you want to actually compute over, but not if you're sort of have an enormous number of points scattered randomly over lots and lots of different database or over lots of different file systems. That can get complicated. Now, it doesn't mean to say you can't do it with MapReduce, and we'll be talking a bit about that, but graph processing really deserves its own sort of way of handling some of this data. So what are the scales of graphs in current graph processing? So you're looking at billions of edges and tens of gigabytes at this current time. And we can sort of just go through some of the examples here, illustrating. DBLP is a citation index for science, and it has about 0.3 millions of vertices in it, and it has about 1 million edges, and its size is about 10 megabytes. And you can download if you want to experiment with it, but that's an example where of a citation index which is, well, certainly I use it. It's very popular. Skitter is another type of system with 1.7 vertices and 11 million edges and 142 megabytes. Let's see, there's going down here, there's all sorts of different web items, but let's concentrate on Twitter because Twitter is very popular, everybody uses it, knows what it is. There, what you're doing is sending tweets. You have a handle on the tweets that you're sending, and people form these networks of forwarding their tweets and so on. Looking at that, you're looking at something like 42 million vertices and 1,470 edges, and that's about 24 gigabytes. Not something you can easily download and play with, and it's beginning to represent a real problem trying to compute with all of that data. If you go to Yahoo, the Yahoo web, and this is back in 2002, the web was then 1,413 million vertices and something like 6 million edges and represented 120 gigabytes. So we'll see it's grown a lot since then. But it's a scale that's causing the problem. If you get any of these problems and make them small enough, you can easily do them. And you can probably use any technique to do them. But as they get bigger and bigger and bigger, you have to use distributed computing because they won't fit in one machine. They won't fit in one huge memory. And then you have this distributed computing problem of actually looking at it. And if you get them large enough and they're being updated, then you have an update issue about how you actually process things. So you would like to look at the current state, but perhaps the data keeps coming in to update all of the graph, and you would like to make sense of that graph. So there's plenty of room for research, plenty of room for interest, and this whole area is very live. So what's the scale? What's the future scale of what we're looking at? And we can take some naive examples, but they illustrate our problem. So social network, you could expect, 1 billion people to be online, connecting together, talking to each other, sharing information. With 1 billion vertices, that's about 100 billion edges, interconnecting them. And the adjacency list, remember the way that one could represent that as a table, that will be 2.92 terabytes adjacency list. You would find it difficult now to actually hold that in memory. Could just about be done in modern day memory systems, but it would be expensive. It's not a cheap environment at all. And that represents, about 1/7 of the world's population. This is assuming that youngsters don't necessarily go on the social network, and the old folk may not necessarily go on the network. You could expect that 1 billion perhaps to get much larger, maybe 5 or 6. at some point, and then it would overwhelm our current computers. If we go on to something like the web, looking at all web systems, you're really getting a little bit out on the edge there. The reason multiple websites are created for multiple people, so you're looking at a huge difference between that and just social networks. So here we're looking at 50 billion vertices, 1 trillion edges, and looking at 29.5 terabytes adjacency list, which is a challenge. You buy disks in what, 4 terabytes, so you probably can't fit that on any one machine anyway. You'd probably have to have a large number of machines to actually deal with this. And so if you're going to do something like that, analysis, PageRank, so that you can answer queries, you're going to need the sort of clusters that Google has in order to be able to provide the response. And of course, if you want it fast, you need more. You're going to do even more work at getting it distributed. But even that just sort of touches on what is possible. And let's take the brain projects that are going on, both in Europe and here, trying to actually produce a map of what's inside any one particular person's brain in terms of neurons. And of course, it's thought that neurons represent the way that brains actually compose thoughts, and therefore understanding that connectivity is vital to understanding how people think, and a lot of medicine too. So if you go to brain scale, you see that we far exceed the web. We're into 100 billion vertices, 100 trillion edges, now into 2.84 petabytes of adjacency list, far exceeding even some of our supercomputers now. Supercomputers might be up to, say, 3, some of the more advanced ones, but some of the other ones in use today would be less than that. So you're really sort of stretching the limits of what actually can be computed. And this is just one human brain. There are pathways, there are chemical pathways inside the brain that you could also map and also include, and that would increase this. And then we have scientists, our own scientists working on bees, for example, wanting to relate behavior to both the neurons and the pathways through the brain, and perhaps some other interesting behavioral topics about biology. And there you're really exceeding any possible computation that could be done in the next 10, 20 years. So this scale of things is really flexible, really rather dramatic, and underlines the emphasis that we need better graph processing, and that in fact graph processing has a lot of uses. And so the next set of videos is all about what sort of computations can we do with this graph processing. And as we go, we'll be discovering algorithms and computer structures, looking at that in terms of cloud computing and how can cloud computing help. We're going to move on now to look at graph processing and what infrastructure you need for that graph processing. We've seen the need to do it, but how do you provide support for that? There's 2 ways to go. You can either have a supercomputer providing your graph processing, lots of memory, very high performance machines, or if you want to scale it to enormous sizes, you're going to have to look for a cloud solution with distributed processing. It's in general going to be more expensive to design this unless we can find a way to map graph processing onto our cheap cloud infrastructure. The supercomputing approaches will be more expensive. So, natural question is, can we actually use MapReduce, and would that work? Well, it tends to be inefficient because the graph state must be stored at each stage of the graph algorithm, and each computational stage will produce much communication between the stages. So if you do a MapReduce and you do a MapReduce on all the vertices, what's going to happen is you're going to have to visit all of the data structures, and it's going to be very expensive, even if your algorithm doesn't actually change all the data structures. And we'll see later that there's some algorithms that don't. Single computer and a library approach, well, that's not very scalable, although it works on a supercomputer up to some large extent. But once you reach out of memory, once you can't fit your graph in the memory, as we've seen, there's lots of problems with graph processing that won't do that, then you have trouble. So if we're doing a shared memory system implementation on a supercomputer, you do also have to worry about how you get fault tolerance, and if the computation runs for a long while and there's a chance that machines die, how are you going to make sure that the computation will continue? And one of the advantages of using distributed computing is that machines can die and you can have backup pieces, and you can keep going even in those circumstances. So we're running into the area where we may not be able to do the computations we want if we can't figure out how to map it on a distributed machine. And maybe we don't need it as efficient. Maybe what we will do is just use the massive approach to try and make the computation work, provide the fault tolerance, and provide the computation. And it won't be as efficient as we would really desire. So we're going to look at a parallel model again. The BSP model is still going to be, the Valiant BSP model is still going to be the direction that we're going to take. We're going to provide graphs, and often we're going to be sort of oriented towards a directed graph. I'm going to show you Pregel. Pregel was one of the first systems to do graph processing on a distributed system. It was running to show how you could actually solve the problem. What it's oriented towards, as you will have heard, as you will have understood from the first lecture, it's going to be vertex-based. We're going to do the computations around each vertex, and each vertex represents a processor. You're going to move the computation forward by processing a particular vertex. And we're going to keep repeating it on all the vertices that need to be processed until every computation at each vertex votes to say, okay, I've done what I needed to do on this particular stage of the graph processing. And once all those vertices vote and say, okay, and that may not be all the vertices, that could be a subset, what we're going to do is to return back to the directed graph and allow yet another iteration. And those iterations are going to be sort of like super steps in our method. So the primitives you will find in Pregel, they deal with vertices. They treat them as first-class entities, meaning we will be programming with the vertices. With this vertex, we're going to do this, this, and this. The edges aren't first-class. They're incidental. When we visit a vertex, we're going to be talking about the edges. And we will be exploring what's on the edges. What is the edges? Are the edges labeled? What are they connected to? We will allow both vertices and edges to be created and destroyed in the computation if we need to. So Pregel was based around C++. It has a C++ API. It moves ahead with a set of super steps. At super step, you look at the vertices, the application code using C++ and object-oriented programming. Subclass is an abstract notion as an abstract class of vertex, and it writes a compute method for that vertex. And in that compute method, you're going to say, well, taking into account all of the edges, what do I want to do with this vertex? You can set the vertex value, you can set the outgoing edges values, you can get them, you can send and receive messages generally, and you'll be reading messages sent to a particular vertex. You can either do it from the previous step in step S, So super step S-1, you can look at the edges or read the messages. You can send messages to other vertices that will be received at super step S+1, and that way sort of allowing you to go from computation or step to step, computation to computation. Each time you're going to be modifying the state of V and its outgoing edges, and they'll be available to the next super step. So the C++ API provides messaging. It has a guaranteed message delivery order. So it's like TCP. Messages deliver exactly once. So you don't have to worry about failures of messages to get through. And you can send a message to any node in the system at all. So if you want to wrap around or you want to have a broadcast or whatever, it's fine. If the destination doesn't exist, then there's a user function will be called to tell you that you've made an error and you need to fix the problem. Pregel. Let's have a look at an example, and we'll do a shortest path algorithm. We're going to look at multiple paths at the same time, looking for the shortest path in the system. Basically, we're going to use Dijkstra's algorithm. We're going to accelerate Dijkstra's algorithm by doing all the paths we can at the same time, and then try and sort of resolve all the parallel results we get to give us the shortest path through the whole network. And we've got a diagram here of how that will work. The edges are labeled with the distances. The nodes are initially labeled with the distance they are from the origin, and when we don't know, we're going to put infinity. As we learn what the paths are, we will put in the shortest distance we know about into each of those nodes. And as we go forward, what will happen is we will rewrite those nodes several times, those vertices several times, making the vertices more and more accurate. And you will find that we're going to pick the shortest path, obviously, so the numbers in the vertices are going to be decreasing. Now, as we go forward, we need to propagate the distance, the total distance of the node from the origin. The origin in this case is going to be the 0 labeled vertex in this diagram, and we're going to propagate a value through the edges to the different nodes, and at a particular node we're going to be seeing lots of different values coming to it at any particular time. What we're always going to do is to pick the smallest of the value of the vertex or the value coming across the edge. And we keep repeating this for every vertex that needs to be updated until all the vertices vote and say they're all happy. At each round, what we're going to be doing is to make sure that each vertex has moved to a new value if it can, or hasn't if it doesn't want to and it's happy with the state of the computation. So in that way, we have super steps going on, moving the diagram forward, and it can be parallel movement forward. At each of those super steps, several vertices will change their values, and we will sort of continue doing those super steps until the whole thing finishes and we have the shortest path mapped out across the whole of the network. So let's try that out, see how that works, and then we'll look to see what Pregel code is needed to actually do this. All right, so we're going to start out at this vertex. Now, the algorithm itself will be launched looking at all the different vertices, seeing which ones can change. So in this diagram, what we see is that we can propagate a distance value, taking the 0 and the 6, the 0 and the 6, and we can propagate that forward to the next node and tell it that there's a 6 distance from it from the origin. And similarly down here we can do the same thing. Now all these other nodes can also be evaluated, and they're not going to be terribly helpful but they would be evaluated too. So we will pass these values to other nodes. So for example, we can add 3 to infinity, which gives us infinity, and pass that onto there, and it's not going to do any good, but we can do that. So looking at how this goes, we're going to pass this 6 on to this node, and we're going to pass the 5 on to that node. And so at the next step, what will happen is these 2 nodes will change value, and we're quite happy now. We have the distance nodes of that vertex from the origin and this vertex. This node from the origin, this node, this vertex from the origin. We know what their distances are. And all of these other ones, if they operate, and we can optimize to make them not do anything, but if they operate, they would actually just sort of keep the same values. So these infinities would stay the same. So the next step, we've got the 6 and the 5. Now we're going to propagate the 6 down this way and the 12 this way, except we have to accommodate the extra distance here. So we're going to add 6 plus 12, and this is going to turn out to be this is going to turn out to be 18 and going along this right way. And down this side, we have a 6 and we have a 2, so this is going to be an 8 as we propagate it down that way. But what we're going to do is to do the whole thing in parallel, so we're also going to do this and propagate along here at the same time. In fact, we'll do that to all of the things in parallel as much as we can, but of course some vertices are not going to change. So here's the next diagram. What you see is the 18's being propagated, and there's an 8 here, down here, there's a 18 up there, there's a 13 down here, and over on this side, this 5 and the 11 propagate up here to be a 16. Now obviously if I was to choose 6 or 16 and say which is the shortest, I'm going to say 6, so I'm going to ignore that 16 entirely, and it's going to be the same. This propagated down here, 6, 1, 7. 7 is a lot longer than 5, so I'm going to forget about that one. If I look at any others, I can see, well, 18 is much better than infinity, so I take that one. 8 and 13, well, the 8's better than the 13, so I'm going to take the 8. So in my next diagram, I've updated those. Now what I've got is a much more sort of settled solution over on the left-hand side of the diagram here, and over the right I've got lots of activity going on. I'm going to pass now my 8 upwards, up this way, and I'm going to pass the 18 down that way. Of course I'm going to probably ignore that. I'm also going to be passing these values that way, and we'll see what happens next. Well, as you can see, passing the 11 up, I'm going to have a choice between 18 and 11, and I'm going to choose, well, the 11. Coming down this way, I got the 10. Coming down this way, I've already have an 8 there, so this is going to add up to 28 by the time I've got this 18 plus 10. So I'm going to choose the 8 coming this way. Coming which way? Coming this way. I'm going to use that as the shortest path. That's how I go up with that 8 in that node, that vertex. And you'll see that there's still some resolutions going on here. That particular node sees 22 coming from 2 directions, so it's going to turn into a 22. There we've got the next step. Now we've resolved these things. This is turned into, here we've turned into 11. Here we've turned into an 8, and the 8 has actually provided the 11. It's come up this way to, oops, no, it's come up this way to R11. That's the shortest path. So now when we sort of move forward and propagate again the values, what we're going to see is this 11 plus the 4 is going to be shorter than 22. So we're going to be changing this thing. So let's do that. Here we got 15 coming to the 22. 15 is shorter than 22, and so we arrive at the 15. Now we've got completion. Everything, you can't move everything forward anymore. There's no other vertices which would change no matter how much we sort of do this vertex evaluation. And you can see that this 15 is now the shortest path from 0, and it's quite a lengthy path. It's going whoa, down here, up there, and down there, and that's the way it works. And what does that look like from a programming point of view? Well, here's the code. What you do is to take this notion of vertex. As I said, what you're going to provide is a computation for that vertex. You're going to override the class with your compute method. Here's the compute method. We get an input message if we need them coming in here, and that will be the input message will be one of those updates, the total computation of the path by taking the vertex value and the next edge, adding them together and sending them on. And here, down here, this is where the vertex will be propagating a message out, say, to the next edge. That's done at this location. And then in here, what we've got is some code actually sort of providing your computation, your calculating of the edge, and so on. So that's the basic part of the vertex code. The vertex class for this algorithm is going to look like while we've still got messages coming into a node, pick up the next message and look at it and determine which is the smallest value to put into that particular vertex. And then we add that, and what you can see here is that we move on to the next iterator by sort of getting ready to transmit the value forward if as the algorithm progresses. So we've seen Pregel working on an example. Now let's go back and see how this maps into actually the infrastructure, how Pregel's programmed and supports that type of computation. So Pregel is based off a master worker model. There's a master which maintains the workers and gives them work and tells them when to work and when to stop. It recovers faults of the workers, so if one of the workers crashes, it will create another worker. It provides monitoring for the progress of the tool, so you can actually see how far you got in the computation. The worker, on the other hand, it's going to be working on these vertices. It's got processes that will process each of the vertices, and it will communicate with the other workers. All of the storage is, again, it's this distributed storage system. We're going to be using HDFS. In the examples you program on Giraph or whatever you're going to use, you'll be actually using HDFS. But if you're over in Google, you'll be using GFS or Bigtable. You can use pretty much any type of storage, but you need it to be a distributed store because of the vertices. The vertices are going to be distributed out onto lots of different compute nodes. Typically, one compute node will have multiple vertices, and so the worker on a particular node will actually go through all these different vertices and do those vertices, and then it will need to communicate to other machines to actually continue. So the organization of this is it looks at one vertex, does what it can for one vertex, does another vertex, does another vertex, and it's done all the vertices it can. Then there's sort of an exchange of information, and then you go on and do the same thing again in those steps. Any temporary data is stored on local disk because what I've shown you is that shortest path is not very much data, but some of these algorithms can have a lot of data associated with the vertices. So you get many copies of the program. They all start executing on a cluster of machines. Machine assigns a partition of the input to each worker So each worker receives so many vertices. It loads those vertices, marks them as active, and then it's going to visit each one and do the processing for each vertex. The master instructs each worker to perform a super step. Each worker loops through its active vertices and computes for each vertex the results. Messages are sent asynchronously. They're delivered before the end of the super step. And then once you've done that, and all of the processes have been done, then you need to exchange messages across node boundaries, get all of that sorted out. Then you repeat the step, and you keep then doing this over and over again until things are finished. And basically, that will be when none of the vertices have anything to do, when they all say, I haven't got anything to do, or when there's no messages in transit, then you're fine. After the computation halts, the master may instruct each worker to save its portion of the graph so that you can go back and look at what's happened. So we're distributing the vertices onto the nodes. Each of the nodes under instruction from the master is going to do the processing for the vertices it has. The messages that are produced will be sent to the next step, and they'll be all sort of completed before the next step is started. What about fault tolerance? Well, checkpointing is used to make sure that the computation can keep going. The master periodically instructs the workers to save the state of their partitions to persistent storage so that you get a copy of the vertex values, the edge values, the incoming messages. So if one of those processes dies, or one of the processors dies rather than nodes, you can then go back to the checkpoint and restart that checkpoint and let it take up where the previous processor died. Failure detection, because it's a distributed system, there's no clock, there's no way to actually see what's going on. So what we use, ping messages, keep alive to make sure that everything is actually responding and doing processing. The recovery, well, the master reassigns the graph portions to currently available workers, so you can share out what's the job that's not being finished. You can share that out to other workers that are alive and can process the system. And the workers just reload their partition state from the most available checkpoint and then continue. So in this way, you can build a very reliable, very well, not deterministic, but very well stepping forward, reliably approach to executing those graphs. It is inefficient. It is using cheap components. It's using a distributed cut setup, and it's going to get you the answer.